Welcome to the full end-to-end Solana blockchain and smart contract bootcamp. We're going to go through everything you need to know from a technical standpoint to get started building on the Solana blockchain and write your own full stack decentralized applications. Whether or not you have been in the cryptocurrency space for a while or are just getting started, we'll be taking you through your journey to learn how to become an expert Solana engineer. At the time of recording, Solana developers are in high demand. We're seeing a ton of jobs getting posted within the Solana ecosystem. Over the last 3 years, Solana developers participating in global hackathons have created companies that have received over $600 million in funding. And on average, blockchain developers right now are making more than $170,000 a year. While we cannot guarantee you a job, we're going to try our best to provide you with the skills you need to become a Solana developer. Whether or not you have any blockchain experience or have been building for a while, if you are interested in building in blockchain, this is the course for you. We'll be starting with blockchain basics, then going into full end-to-end projects, and finally finishing up with what it takes to get your new application to production. If you have already built some smart contracts or are familiar with blockchain, feel free to jump around the bootcamp to find which projects best fit your needs. You'll be able to find all the information you need to know about each project in the description, as well as in the GitHub repository linked below. You'll find the entire bootcamp in this GitHub repository, including any possible resources you may need, such as links to documentation or further reading on topics. Throughout this bootcamp, we'll be learning how to build on a blockchain and be using both Rust and TypeScript to accomplish this. Don't worry if you don't know these languages, as we'll be teaching you enough to get started throughout each lesson. As long as you have some software development background, you should do well. Even the best developers don't get it right the first time. If you do happen to run into issues at any point in this bootcamp, there's a Solana-specific Stack Exchange where you can get help. The Solana Foundation Developer Relations team and other developers from the ecosystem will be answering your questions there. Just make sure you search for your question first and provide enough information about your error you received while building each project. We will also post the full solution at the end of each step and in the notes below. It is incredibly important that you pace yourself while going through this bootcamp. This is a marathon, not a sprint. Take breaks so you can have some time to digest what you have just learned. Go back to different projects as a refresher. Take the course at your own pace. My name is Jacob Creech, and I'll be working with you on some of these projects throughout this bootcamp.
I'm Brianna Migliaccio, and I'll be leading you through how to build smart contracts and decentralized applications.
And I'm Mike McKenna. I'll be working with you throughout the bootcamp on key blockchain concepts. Before you start building, you should understand the purpose of blockchains and the problems that they solve. Fully understanding the value blockchain provides will help you leverage it to solve the right problems. So let's get started. So what is blockchain? Why is it important? And what can you do with it? At its core, a blockchain is a distributed database with some special characteristics. Unlike most databases, blockchains are unique in that they have no central authority, are fully open for anyone to use, and all data is completely transparent. Everyone can make payments on the blockchain, while no one entity is capable of stopping or reversing those payments. This is what we call censorship resistant. The transactions are irreversible, and the blockchain itself is a recording of those transactions. That's why blockchains are often referred to as a ledger. Unlike databases, which are typically stored in a central location, data on blockchains are stored on multiple computers across the world. Essentially, there's no single copy of the blockchain that can be lost or tampered with. Instead, the data is stored in multiple copies and verified by checking the blocks or bundles of transactions. This is called decentralization. What this means in practice is that blockchain allows people to transact with each other directly. Think about the last time you paid for something, or swapped currencies, or just stored your money somewhere. You might have used a credit card, or a money transfer service, or a bank. To facilitate that, there's typically a service fee involved. The seller pays a couple of % on every credit card transaction. You pay a little bit more for an international transfer. And your bank probably has a monthly fee just to hold your money. Blockchain allows people to transact with each other directly without needing somebody in between. Now, to understand blockchain, you need to start with Bitcoin. Back in 2008, Bitcoin was created by the pseudonym Satoshi Nakamoto as a way to make digital peer-to-peer payments. The white paper for Bitcoin outlined a way to make those payments without having a trusted third party, such as a bank or other financial institution. Blockchain uses digital signatures to let people transact without having to fully trust each other. Digital signatures give us confidence that the money sent is in the correct currency, that the amount is correct, and the amount was actually sent. Bitcoin was created more than 16 years ago, and these days it's less used for day-to-day transactions. People think of it more as digital gold. However, plenty of new innovations have been built since then. Modern blockchains, like the one that we'll be building on, Solana, support fast payments with lower fees than both Bitcoin and traditional finance. Not only that, but new creations, like smart contracts, have enabled a whole new set of capabilities previously not available to blockchains. Smart contracts are computer programs that run on a blockchain. Instead of having a cloud provider run your program, you run the program in the blockchain. Smart contracts are a little bit like APIs in the traditional tech world, except rather than being invoked by requests, they're invoked by instructions. And rather than sending responses back, they write their changes out to the blockchain, where anyone can read. Smart contracts extend blockchains beyond simple payments to allow complex transactions that could lend money without a bank, allow people to exchange items directly with each other at a price they both agree on, or even create a lottery without a lottery ticket issuer. We're going to build these in this bootcamp, so you can see how powerful smart contracts can be for yourself. Blockchain would not be possible without cryptography. Everyone that uses a blockchain has something called a key pair. A key pair consists of two keys, a private key and a public key. The public key is shown to anyone. It's used as an address people can use to transact with you. The private key you must keep secret. The private key is used to sign transactions, which proves that you made them. For example, want to spend some of your tokens? You'll need to sign the transaction using your private key. Anyone else can use your public key to verify that you, as the holder of the matching private key, made that transaction. Key pairs are pretty common in cryptography, even outside blockchain. Let's use the example of passports. Your electronic passport is signed by your government, using your government's private key. When you pass through the passport gates at the airport, they use your government's public key to prove your passport was really signed by your government. If the passport signature is correct, it must have been signed with your government's private key. If I make my own passport, it won't be signed by my government's private key, so I won't be able to get through the gates. In Solana, everyone has a public key they use as their address. Other people can use your address to transact with you. The most basic Solana wallet is just an address with a small balance of Sol. Users can pay their transaction fees and interact with smart contracts using Sol. Here's Alice's wallet. Here's Bob's wallet. If Alice wanted to send Bob some Sol, she would use her private key to sign a transaction that uses the system program's transfer function to send some Sol to Bob, and uses the memo program's memo function to write a little note to Bob about the transaction. If both these steps, called instructions, are completed successfully, the transaction completes successfully, and Bob receives the tokens in his address. If something goes wrong, that's okay. The transaction fails and nothing changes. Alice will still have her Sol. Blockchain technology allows for new applications to be built in this digital age. We can create systems where people transact with each other directly, make digital assets that can be sold or used outside of a game, allow art to be sold, and ensure artists get paid each time a piece of artwork is transferred. The projects we'll be building throughout this course will use the Solana blockchain to create unique applications that can only be built with smart contracts. Let's get started with your first application. The first smart contract we make will be simple. It's going to save our favorite things to the blockchain. We're going to learn how we can save, update, and retrieve information from the blockchain, and how signing is used to control access in our smart contract. In the previous lesson, we learned how everyone has a key pair. A public key that can be used as an address to transact with that person, and a private key that they use to sign transactions. In Solana, your smart contracts or programs can store additional data in what's called program-derived addresses. PDA addresses are not made from a public key. Instead, they're made from seeds, which can be whatever you, the programmer, want. Want to store some config for your smart contract? You can make a PDA from the seed config as a string. When you need to find your program config, look for the PDA made from that seed and you'll find your config. Want to store Alice's review of the movie Titanic? You can combine Alice's wallet address and the string Titanic to store the movie review. Need to store Bob's review of the same film? You can combine Bob's wallet address and the string Titanic to store his review. If you've used a key value store before, you might be thinking this is familiar, and yes, Solana PDAs are a type of key value store. If you haven't used a key value store before, you can think of a PDA as a row of data, with the seeds being the primary key used to find the data. So, let's build a simple app that saves someone's favorite things to the blockchain, and uses digital signatures to ensure only the wallet holder can update their own favorites. We'll use Solana Playground and Anchor, the most popular framework for making Solana programs. So we're going to be using a tool called Solana Playground, which lets us make Solana programs or smart contracts directly in our web browser without installing anything on our local machine. So open beta.solpg.io, click Create a new project, give your project a name. I'm going to call this project Favorites because it's going to save our favorite things to the blockchain. And we'll pick the Anchor option and click Create. There's a file made for you, but let's actually delete everything inside that file, that librs file. We're going to make everything from scratch ourselves. So the first thing you'll see in pretty much any Anchor program is importing what's called the Anchor prelude, which is the thing you'll see at the top of almost any file and allows us to access everything from Anchor just by typing its name rather than typing out the full path to it. So use Anchor lang prelude star. That pulls in all of our prelude into the current scope. The double colon is just Rust's separator for namespaces. Other languages would use a dot for the same thing. A program has a program ID, also called an address. I'm going to set up a program address for our smart contract. In Solana Playground, we don't actually need to fill this in. It will be done for us when we deploy our program. Also, just for neatness, I'm going to make a little constant here. And I'm going to call it Anchor Discriminator Size. The Anchor Discriminator is something that's written to every account on the blockchain by an Anchor program that just specifies the type of account it is. And that's used by Anchor for some of its checks. So that is a use size, and the value is just 8. So when we save things to the blockchain, we'll need 8 bytes plus the size of whatever we're saving. You'll see that later on. Now, the great thing about Anchor is that we can take a regular Rust program and with a particular macro, turn it into an Anchor program. So here is just a regular Rust module. Hub mod favorites, and it's going to use all those good things we just imported a moment ago, and it has a function. So hub function set favorites, which is going to return nothing. Return nothing. And here is its body. So this is just a regular Rust module. It's called favorites. It has some functions inside. In this case, just one function, set favorites. But the great thing about Anchor is that if we do this macro program, suddenly that favorites Rust module becomes a full Solana program or smart contract. This is the power of Anchor. It saves you from having to do boring things. And also applies a bunch of sensible safe defaults. So set favorites, that function, is now a Solana instruction handler. It will take instructions that are provided by clients and run them and then save the results to the blockchain. So let's think about what we're actually going to save to the blockchain. We're going to save people's favorite things. So that's going to be a struct called favorites. And inside, we're going to save people's favorite number, which will be a 64-bit or 8-byte number. And we will have a favorite color, which will just be a string. And we'll have a list of hobbies, which will be a vector of strings. So pub hobbies vector, it's a little bit like an array of strings. Now, because we're going to save this to an account, we will also put the account macro on it.
And to let Anchor know how big favorites is, we're also going to put this derive init space. That gives us that gives all of our instances of favorites the init space attribute, which is the total space used by all the items inside. We'll also need to specify the size of each individual item to get that. Obviously, strings could be any size at all, so we'll need to specify max length. That's max len, say 50 bytes, and I'll copy that for hobbies. Hobbies is nested because we have a vector of a certain amount of items and then strings which have a certain size. So for hobbies, we'll say 5 and 50 for the vector and the string, respectively. When people call our set favorites function, they're going to need to provide a list of accounts that they're going to modify on the blockchain. One of the things that makes Solana great is that if there's a bunch of people over here who are running a transaction involving their accounts, and there's a bunch of other people over here running a different transaction involving their accounts, those transactions don't block each other. There's no overlap in the accounts evolved. So Solana can process them at the same time without waiting for the other one to be finished. So we'll make a struct to store this information, and we need to come up with a good name for it. Now, this is the struct of accounts for our set favorites instruction handler. So the tradition is to call this struct of accounts the same thing as our set favorites instruction handler, just in title case. Structs in Rust have title case, and the convention is to name the struct the same thing as the function itself, just in title case. We could call this set favorites accounts, but it's good to get along with other people, and this is the convention. So pub user, we're going to need people to supply an account that we call the user, and that's going to need to be a signer. You'll see me doing this info stuff here. All that is saying these items will live for the lifetime of a Solana account info object. This is just Rust having rules about how long things should be kept in memory. This isn't a Rust course, so I'm not going to go into lifetimes fully, but we'll throw some links in the course description so you can learn a little bit more about lifetimes if you want to. So we're going to specify some options for this account. I'm going to say that the signer is mutable. Why? Because the person that signs the instruction to set favorites is going to pay to create their favorites account on the blockchain. You're going to pay to store that information. Also, we'll need the person running set favorites to specify the favorites account that they want to write to. It doesn't mean that we'll let them write to this account. We just need them to specify the account. So we'll call that pub favorites. And the type is it's an account. It goes for the lifetime of info, and it is an account, which is an account of this favorites struct that we made earlier. We're going to add a few Anchor account options as well to favorites. The first thing we're going to do is specify init if needed. Init if needed says make the favorites account if it doesn't already exist. We'll specify who pays to create the account, which, as we said before, will be the user, this person here. And that means the user is the person who signed the transaction. So the person who signed the transaction will be the person who pays to create the favorites account. We're going to tell Solana how much space this account needs. So every account in Anchor has 8 bytes, or the Anchor discriminator size, using that constant we made earlier, plus whatever the size for this struct. So when we made our favorite struct, which specified what favorites look like, their types and the different keys that we need, we said derive init space. That gave us this great init space trait, which we are using to calculate the size we will need for a favorites account. In other words, a favorites account is just an account that has an Anchor discriminator and stores favorites. We'll need to have some seeds. Now, the seeds are what's used to give this account an address on the blockchain. This is a program-derived address. Unlike regular user accounts, this isn't a public key. The address for this is actually made based on some seeds that we provide. So if ever you've used a key value store, this is a really similar concept. The keys, in this case, are whatever we have as our seeds. And I'm going to use, in this case, the text favorites as bytes and just the user's own key as well. This means that if I'm storing my favorites, I will store that under the address made from favorites as bytes and my own public key. And if I'm storing your favorites, I will store that under an address made from favorites as bytes and your public key. So what we're doing here is storing information under different accounts that are found based on the inputs we give, and the inputs we give are based on the users. Finally, we'll also specify the bump, which is just used to calculate those seeds. We have pub favorites, and it's an account of type favorites. That looks good. The last thing we'll need to, the last account we'll need people to specify is just the system program. The system program is used for so many things in Solana. If it's not the system program, it's the token program. So that will be a program. It lasts for the lifetime of info, and it is a program of type system. That looks good. So at this point, we have our favorites struct, which is what we're going to write into the blockchain for every user. And we have our set favorites list of accounts that people need to provide, which is also a struct. Let's go and fill in our set favorites function, which is our actual instruction handler, the thing that people are going to call from the instructions in their Solana transactions. We can do, let's do a little greeting message. Solana has this message macro that's built into it, or Anchor actually has this message macro that's built into it. We can do things like greetings from, and we can say context .pro. So message is kind of like console log or print line. It just writes things out to the Solana log file. If you use Solana Explorer, you'll actually be able to see these messages when someone has a transaction that makes a call to this instruction handler. Let's also make a little variable just to show the user's public key, the person who's calling our instruction handler. User public key equals context.accounts.user.key. That's good. Let's add another log message that just logs out the options that people have provided. User. Now I just realized that we needed to provide some arguments to set favorites, and we haven't done that yet. So let's do that now. Context. The first argument to our set favorites instruction handler will be a context, which is a context of set favorites. In other words, the set favorites accounts that we made earlier. And I will spell favorites using American English. So I'm consistent. We'll also ask people for all the options they want to save. So that's the number, that U64, the color, which is a string, and hobbies, which is a vector of strings. Save and let Solana Playground do its formatting, and that looks good. So yeah, our set favorites has a context, a number, a color, and hobbies. And you can see that we can access information about like what program we're part of or all the accounts that people have specified through that context parameter. So back to our message, we have user public key, and we're going to log that their favorite color is, or their favorite number favorite color is color, and their hobbies are hobbies. And just because hobbies is a vector of strings, we're going to add a colon and a question mark so it expands the items inside that vector of strings. The last thing we need to do inside our setFavorites function is go and actually write the information into the favorites account provided. So that is context.accounts.favorites. And if we do a set inner, we can write information into that account. And the information we write will be an instance of the favorites struct with the number, the color, and the hobbies that have been provided. That looks good. Finally, we will return just with OK and nothing, that empty brackets. And we don't need a semicolon on that last line. We omit the semicolon and Rust returns the actual OK response. This is how Solana instruction handlers work. They write information to the blockchain rather than returning it. So that's our completed anchor program. We import the prelude. We set up the ID or program address. I like to make an anchor discriminator size rather than adding 8 later on, because we know that's how much space that every anchor account needs at minimum. We have a Rust module that has functions inside, and we apply this Solana program macro that turns that Rust module into an anchor program. And then inside that module, each function becomes an anchor instruction handler. Each instruction handler has a context, which is all the accounts that the people calling that instruction have provided, plus any other arguments for the instruction. We're going to log a couple of things, and then we're going to save the information somebody has provided to the favorites account. We return OK, just to let calling programs know that this instruction was completed successfully. If all the instructions in a transaction complete, then the transaction is considered complete and everything is written out to the blockchain. If anything fails, then nothing changes. And we have 2 structs. We have our favorite struct, which defines what we want to write out to the blockchain. In this case, a number, a color, and hobbies. And also we're going to add this great init space macro so we can easily calculate how much space it will take to store that. And finally, we have our accounts struct, which I actually realized we need to add derive accounts to the top of so that Anchor knows this is our account struct. And that specifies the accounts that people need to provide along with the instruction. So in this case, it's just the user, the favorites account, and the system program. One of the things that is great about this program is that it already ensures that the person that is signing the program has to be writing to their own favorites account. And we'll test this in a sec, but I want to show you the logic here. In our account struct, we say we have an account called the user, who is whoever signed the transaction. And in our favorites, we say that favorites accounts, the seeds that are used to find its address, are made from favorites and that user's key. So if Alice signs this transaction and tries to write to Bob's account, it won't actually work because the address of the favorites account won't actually match her user account. We'll see this in a second, but it's a good example of one of the things that Anchor provides for us out of the box in terms of smart, safe defaults. Cool, so that looks good. I am going to build this program. So I'm going to slide this little doohickey at the bottom up. So let's click the build button and build our program. We might have some errors, we'll find out. Yep, and we do. It looks like I made a typo because I'm not very good at talking and typing at the same time. I meant to return a result. Instead, I wrote the word return. So let's go and fix that. That returns a result. of nothing. There we go. And let's build again. There's another error. Let's go have a look at the first one. I can see that's really obvious. It says on line 44, we have derive accounts, and that should actually be a capital. So if we build once more, you can see the syntax highlighting actually makes that look a little bit better as well for the accounts. You can see that completes successfully. That's great. Now we will need to deploy. When we go and deploy, Anchor will actually go and make a key pair for us. We can save this if we want to. I'm not going to use this again, so I'm not going to, but maybe you should save the key pair. And it says we don't have enough SOL to complete the deployment. I'm not going to request an airdrop. Instead, I am actually going to use the Solana faucet, which has some more features to get airdrops than the inbuilt Solana Playground airdrop tool. An airdrop, by the way, is just a way of getting free DevNet SOL. So if I open up that address, you can in Solana Explorer, you can see that it has no balance. It's a balance of SOL is accounted does not exist. Data size is 0, etc. So if I go and copy that address and then go to faucet.solana.com, paste in my wallet address, and let's ask for 5 SOL. Why not? And you'll see the message airdrop was successful. If I go back into Solana Explorer, you will see that I now have 5 SOL. Excellent. Great. So let's go and I'll clear those old log messages, and let's hit deploy again back in Solana Playground. Good. So it's deploying, and it says it can take a while, which it does. And you'll notice while it deploys, it actually takes a little bit of my SOL to do that deployment. And it's finished successfully. So let's go check this out on Solana Explorer. There's actually a transaction for deploying my program. And you can see that transaction was successful. My deployment was successful. Good things. Excellent. So back here, we have our Solana program, and it's been deployed on Solana DevNet at the address. You'll see, by the way, that Solana Playground actually added our program's deployed address inside declare ID, and in Solana Playground, we can actually go and search for that address and find our program there. It has some executable data. It's upgradable. There's the upgrade authority, which is the temporary key that Solana Playground made for us. In my case, it starts with F. Great. Solana Playground also has a test tab. It's this little test tube on the left. And this allows us to actually invoke any of our instruction handlers on the blockchain straight from Solana Playground. So in this case, I can go and set the favorites for the temporary wallet that Solana Playground made for me. I'm going to specify my favorite number, which is 7. Click custom. Color, which is red, custom. And hobbies, which is skiing and bike riding. That looks good. Custom. So as well as our favorite things, people calling this instruction handler will also need to specify the accounts that they want to use. So for the user, pick the current wallet. For the favorites, pick from seed. And the first seed will be what we had before, which is the string of the word favorites. There we go. Oops, sorry, I need to hit that string custom favorites. There we go. I'll add a seed, which is just the current wallet. And that matches what we had before, where we're calculating the seeds to find this favorites account from those inputs, the word favorites and the current user's wallet. Now, our program actually checks that the favorites account we write to belongs to the signer. And I'll show you what happens if someone else tries to write there later on. The program is already written for us. It's just the public key of our actual program. And I think that's it. So we can go, let's make that seed. Click that generate button. And if we hit the test button, we've actually made a transaction to our program. So let's open that up on Solana Explorer. So in Solana Playground, here is our transaction. And it had only one instruction, which is the call to our set favorites. And if you look in the logs here, you can actually see some really interesting things. And I'll make this font a little bit bigger as well so you can see that. It says, greetings from our program's public key, our user, our wallet address, their favorite number is 7, their favorite color is red, and their hobbies are skiing and bike riding. And you can see that that's actually saved that out to that account. The way you can do that, by the way, is you click on favorites. And if you just do fetch all, you can actually see that in Solana Explorer, we have for the public key of our user, we have a number, a color, and a set of hobbies. Now, what happens if another user tries to write to our favorites? So back here, if I pick for user, if I get rid of that and I replace current wallet with random, but I'm going to leave in the favorites account that was made from the previous user. So if I test that now, if I try and run a transaction where I'm writing to someone else's favorites account from a random wallet, you will see that a seeds constraint was violated and the instruction did not complete successfully. This is one of the great things about Anchor, is that these controls over what accounts people are allowed to write to are, really handled for us. Most of it was, this logic that we set up inside the set favorites account struct, where we said that the user is whoever signs the transaction, and the favorites account must be made from these seeds. If they specified a different favorites account that was not made from those seeds, that's why we get a seeds constraint was violated. So you've now made a program, deployed it to Solana DevNet, and seen how Anchor's account constraints allow us to control access to data on the blockchain. You've also, by the way, written data to the blockchain and read it back. In the next steps, we're going to install Solana on your own machine and create more programs that do more useful things. See you soon.
The next application we're going to build is all about voting. Traditionally, democratic governments hold elections and collect votes from the population. There's a multitude of ways that people can vote, but verification is still a very human process. Votes are added to a ledger, and after a long period of time, the results will be released. Using blockchain technology, we'll not only be able to immediately calculate the votes, but we'll also be able to instantly verify a user voting using key pairs. In this project, you'll learn how to manage accounts and build using program-derived addresses with best practices. Let's get started. Hello, my name is Jacob Creech, and we're going to be building the voting application. Before we get started on that, we have to build up our local environment to actually build our voting application. This is contrary to the previous application that you built, the Favorites app. We're going to build it locally versus all within the Solana Playground. So let's get started on how you set up your local environment. All right, so first thing that you need to do is you'll need to install Rust. And the web page that I'm looking at right here is the Anchor docs for installation, and it has a full list of all the different things you need to install. So first thing we're going to do is install Rust. We go to this website, and we just use this command. So let's go type it into our command prompt and let it run. So this will just make sure everything is set up on our computer to use Rust to compile Anchor and other Solana smart contracts. All right, so this is going to update my Rust home variable. It's just giving me all the information to do the installation. And so I want to just proceed with standard installation. And here we go. All right, so now we've had Rust installed, and the next thing we need to do, as it says, is we have to make sure that we reload the path variable. So we can see that here we need to make sure that to configure current shell, you need to source the corresponding environment variable under home cargo. It's usually done by cargo environment or cargo environment fish, depending on what you're using. You'll have to know exactly what your current installation is or whatever type of computer you're using, but this should give you the right information to do the correct thing. So let's go make sure that we have Rust up. I believe it's just Rust up. Yep. So we typed in Rust up, and we can do Rust up -- version, and it'll tell us that I installed Rust up 1.27.1. We're all good to go, and we can see my active Rust version is 1.79.0. So that is everything that you can see. They're like, oh, I have properly installed Rust on my computer. And the next step that we need to do is we need to install the actual Solana toolchain. This is so that we can do a bunch of different Solana-related things like creating key pairs locally or compiling our smart contracts and more. So we click here, and it'll take us to the page to do the installation. So we can see here that there is a CLI command to install. We just copy and paste it into our terminal. So let me paste it right here. And this will pull down the Solana binary in order to run the Solana toolchain locally. All right, so now we see that it was installed. We've installed Solana version 1.18.18, and it's telling us to do an export onto the path. So we can just run this thing right here, and it will export our binary using Solana onto our path variable. This just basically allows us to use the Solana CLI. So then we can open a new terminal. Let me make it bigger for you all. And we can type in Solana -- version, and it should give us the version number. And see here we have Solana CLI 1.18.18 installed. So we're good to go. We can also check in this other terminal just to make sure that we did everything correctly on the Rust. Version. There we go. And we have 1.27.1. So let's clear this and close out of this terminal. All right, so we're back to here, and we keep following the docs pages. The next thing that it has us do is we're installing Yarn. You can also install npm, you can install pnpm, you can use bun. You can do whatever flavor of package manager you use for JavaScript, doesn't matter. This one says install Yarn. I'm not going to show this because it's like there's pretty good documentation out there because it's outside of our ecosystem. So go ahead and install your favorite package manager for using Node.js or something, or JavaScript. The next thing we need to do is we need to use the Anchor version manager. This is so that we can have the correct version of the Anchor framework locally in order to compile smart contracts on Solana. So this just tells us to do cargo install. So let's go ahead and do that. All right, and that's Anchor installed. So you can see that it installed 0.30.1, and we can go open a new terminal and see if it actually worked correctly. So let's make this bigger for y'all. avm -- version, and we can see 0.30.1. And in order to set your current Anchor version locally, because this is just the version manager, you do Anchor or avm use. We're going to use 0.30.1 throughout this boot camp. And now we're using 0.30.1. So that should have everything that you need to get started, I believe. Let's just double check with the docs. All right, so this has some more information to make sure that you have everything right. It also tells you to do Anchor -- version to make sure we're using 0.30.1. And so we have Anchor CLI 0.30.1. So now the next step is what we're going to do is we're going to set up our project for creating the voting app. I'm going to just make sure I'm in a good directory that I like. I'm going to make a temporary directory for us. There we go. Let's make sure. Bootcamp temporary. All right, so here what I'm going to do is I'm going to do let's make sure it's bigger. All right, so here what I'm going to do is I'm going to do npx create -solana -dapp. And you just type in that and hit enter. And what this does is it will create a scaffold for building all your different projects locally on Solana. So here we first got to enter our project name. We're doing a voting dapp. We're going to use Next.js for this. We're going to use Tailwind. We might as well have the counter program. That's fine. And it'll start creating the workspace. And so once this finishes, we'll have a template or a scaffold in order to start building our voting app locally. This makes things a lot faster locally as well. All right, so we've created our template Solana project, and we can actually start running it. So if you go, we can do ls here, and we can see that there's a voting dapp folder now. We'll go cd into it. And if we do an npmi, I used npm locally, that's fine. So we can install the npm modules to get our web front end running, and then we'll do a npm run dev to run our actual website. So npm run dev, and it will open on localhost 3000. So let's go look at localhost 3000, see what presented us. All right, so this is basically a placeholder or a scaffold for us to create our application. This is what we're going to use completely to build out our voting application within Solana. We have everything here. There's a bunch of placeholder stuff that we'll remove later on. We're going to focus on the program side first, or the smart contract side, and build that out. All right, so let's go look at our other local stuff. So going back to here, we're going to open another new terminal. So another thing part of local is that instead of running things on DevNet or an environment that's not on your local computer, we're actually going to run a validator locally that has a lot of the same capabilities that you would see in a validator on the actual live network. And we can just simply do this with the Solana toolchain by running Solana test validator. So you want to run this locally also to test to make sure everything installed correctly. Just as a note, if you're using Windows, you will want to have this all installed on WSL. Otherwise, it might not work. And what you can see here, the JSON validator is running on port 8899, and it's processing slots. You can see it's at slot, what is this, 1,300,000. And the confirmed slot is moving forward, and we're all good to go. And it's running. And so actually, if I run this and I click here and click on local, you can do things on local. So you can probably, let's say we can see it accounts. I can see that I have an account with this much SOL on local, no token accounts and everything. This is the majority of your time is going to be spent using the local validator to build Solana smart contracts. Another thing is locally, you can use the Explorer to look at everything that's happening on your local validator. You don't have to go do some API calls or something to figure out what's happening. You can all do it via the UI on the website. And how you do that is you can go to explorer.solana.com, you click here, click custom RPC URL, and that should be set by default to your current local host, your current local validator. So we can just click that, and boom, we have that. We can see a bunch of live stats. So 1,300,915,916. We can see that roughly matches up. This will be basically off of the finalized slot. They're equal from the front end to the back end. And using this Explorer, you can see a lot of the different things that you're doing locally and making sure that you're validating your transactions. You're making sure that the instructions that you're setting are correct. This is the full local setup so that you can actually run all of your code locally, iterate a lot faster, and not have to worry about other environments. It's very important that everybody, and this is what we're going to be doing throughout the whole bootcamp, is everybody uses the local test validator and gets very familiar with how to use it correctly. All right, so we have it running. We have our developer environment running. We have the voting dapp running here on a website. We can see I'm connected to it. We're all good to go. Everything is ready for us to get started on local. This is all the setup that you needed to start building local development on Solana. What I like to do is before we build anything on the voting dapp, I want to make sure that we understand exactly what we're going to build. We're going to architect all the different things that we're going to build before we actually write the code. This is so that we kind of understand what we're thinking when we build out the application so that we don't have to keep rewriting the same code over and over and again. So I'm going to draw it up here, and we're going to give the full architecture. All right, so this is basically a whiteboard. I'm going to use this to draw out the voting DApp. We're going to create a voting application that's going to do two things. We're going to either be able to vote for an account. We're going to vote for crunchy or smooth peanut butter, basically. So if anybody wants to vote for their favorite peanut butter, say you enjoy crunchy better than smooth, vote for that one. And then if you want to do smooth versus crunchy, vote for that one. It's a very easy way to showcase. But you can kind of see like how this extends to real life applications, say like an actual election or your school representative election or something. You can actually decentralize this to where every single person has a public and private key, like you learned early in this boot camp, and that is their identifier. And you know that they voted, and you can immediately count the votes that they have for a specific candidate online. So let's draw this up. Okay, so part of this diagram or this architecture is we have to understand what accounts that we need for our smart contract before we write it. So here we'll be creating basically polls, right? So we're going to have a poll account. We know that. And then we're going to need candidates. So we're going to create another candidate account. We're going to have, I think what we're going to do is for each candidate, we'll have an individual candidate account. So there could be multiple of these. So let's just create a bunch of them so that it's easy to remember. And these candidates will have some information. So each of these accounts, since these are both different types of accounts, will have different information about what is the poll and what is the candidate. So the candidate, it makes sense to have candidate name as who you're voting for, and then maybe there is a candidate vote amount. This is so that you can keep track on chain via just looking up the account, how many votes a specific candidate has. And in the poll, we're going to have a different amount of data stored in it. So we'll have like a poll name. This can be like the question or the name, or yeah, this can be, let's call it poll question. That'll work better. Or we'll just call it poll. That'll work. So we have the poll, like what are the question, what's the answer, or the question that they're asking in the poll, like do you vote for, in our case, crunchy or smooth peanut butter? We'll have a description that kind of tells you a little bit more information about the poll so you can better vote what candidate you want. We're going to have a poll start time. So let's do poll start and poll end time. And then we're going to do one last thing that helps us understand more information about the poll and also do lookups later on. Because one of the things that we're going to have to do is we're going to have to do lookups on how many candidates there are within the poll. So we might have 5 candidates, we might have 2 candidates. In our case, we'll only have 2. But say we have hundreds or something. We want to make sure that we understand how to do the lookups correctly and very quickly. We'll call it candidate index or candidate amount. We'll call it candidate amount. All right, so we have our 2 accounts. And if you remember as part of the PDAs or program derived addresses that you used in the previous project, we want to figure out how to find these accounts and do lookups on them very easily. So we're going to have to derive these things differently so that it's very easy for us to do those lookups. So let's get into that. The way that we derive PDAs is we provide seeds. So in this case, for the poll, we will have a poll ID. This is so that we can get the poll and figure out which ID this poll is. So this is like if you have a list of different polls that you are doing lookups on, this helps you understand which poll ID represents whatever poll that you're pulling from. So there's 2 ways that we'll have to do this later on in the actual application. You can either do just a incremental ID where it's just like 1, 2, 3, 4, 5, etc. Or you can do UUID as the poll ID. I think we'll just do 1, 2, 3, whatever. And the way that we'll have to do lookups later on is we can either cache it server-side on the amount of IDs and what are the polls and descriptions, and then just do verify on chain, or we can just do like incremental lookups and figure out, okay, what are the first 10 polls? showcase them on the website. There's a lot of different things you can do with this. We'll do a lot of that later on in the bootcamp when we productionize this application. But for now, we're just going to have poll ID. It's going to be a number, and that's it. And that's how we're going to derive the poll. So this is the seeds for the poll account. The other one is we have candidates. And what I would like to do for this one is for the seeds, we would always want to make sure that it's identifiable based off the poll ID. So that whatever poll that we are pulling from with all the information, it's uniquely tied to that poll. This poll ID directly ties it to that poll. So we'll do poll ID, and then just so that we can do lookups based off of which candidate, we'll do the candidate name as well. So this ends up being our two seeds that we use to derive each candidate. So we have the seeds of poll ID and seeds of poll ID plus candidate name. The whole reason, and you have to make sure that you give these different accounts a lot of thought, but the whole reason why we're doing this is so that we don't have to redo our accounts later and redo the way that we do lookups later, because it's very important that we have good lookups at the beginning of building out our program or our smart contract so that we don't have any issues long term. All right, so here we go. We have our poll ID and our candidate name. And we have to also build out what are the instructions? What are the functions we're going to call within the smart contract? So let's go outline those out. So the first one that we'll need is, let's pull this over here. I'm going to move some things around so it's easier for us to view everything. The first thing that we'll need is we'll need an instruction. So we'll call these instructions. We'll need the instruction for initializing the poll. All right, so this will build the poll, take out all the parameters in order to build that poll, as well as the poll ID, and it will have everything we need to build that poll. So the next one that we need is we're going to have to initialize individually candidates on this poll. So this is initialize candidate. All right, so we have the poll, we have each candidate. The last thing, and the most important thing, is you can't have a voting application without the ability to vote for application. So we have everything we need. We have the instructions, we have each account. Now we can actually just start building. So let's go over to our local environment. You can open your favorite IDE, and you can just start building there. So I'm going to open Visual Studio Code, and I'm going to go open the specific folder that I created earlier with my voting D app. Okay, so I have the whole code base open now that we created earlier via the create Solana D app. We can see, just as a quick walkthrough of this actual scaffold, we can see here we have a web. This has just a basic Next.js app. If you're familiar with it, or if you're unfamiliar with it, that's okay. We will show you what's practical to get started. You don't have to go end to end. Basically, it just has a bunch of components, and within these components, you'll be able to see, so it was originally a counter page. This is the page for that. And then we have a bunch of information in order to get the counter. We have a data access. We have a feature which helps us actually showcase what that counter create is. And then we have that UI for the page. Don't worry about it if you don't know this too much. We'll just go through what's practically needed to build out the website. If you want to learn how to build websites or build the UI or the front end for any of these applications we build throughout this bootcamp, there's plenty of resources online that you can use. We're more focused on building the Solana side of things rather than the UI throughout this bootcamp. So we'll teach what's practical throughout this. All right, so this is everything that's in the web folder. And then what we're going to focus here is we're going to focus on the anchor folder here. So if we go here to programs, source, lib, we'll see that there's a counter program already based in here. We want to update that to our voting D app. So we're going to update this to voting. I'm going to just remove all of these instructions and then the rest of the accounts. So you end up having this very small file. There's barely anything in this file. I'm going to do a couple other things where we're going to change. We're going to change this one to say voting as well, this file. I believe in here it also says voting. Basically, you can change everywhere that says counter to voting. If you use this in the future, it should be automatic, and then right now it's not. So one thing to note is that we need to also double check our anchor laying is the one that we expect. Throughout this whole bootcamp, we're using 0.30.1. I don't know in the future what the new versions of Anchor might hold. So if you're ever in the future using this, say, I don't know, months in the future, and we're going through this bootcamp, and you're using 0.31 or 0.32, and something doesn't work, definitely make sure that you use the right dependency. Also, as a general note, if you ever run into issues, you can always double check the project link in our GitHub repository. It will be in the description below, and you can go to that and check all the code and make sure that you're all set up correctly. All right, so we have the right Anchor version. We have our librs. The first thing I'm going to do, just to make sure that I did everything correctly, is I'm going to go cd into Anchor, and I'm going to do an Anchor build. This is how you build your smart contract locally. And let's make this slightly bigger for people to be able to view it. And so this Anchor build will compile our smart contract, and I'm going to do it early just to make sure I didn't screw everything up. I often will say build early and often. You'll hear this throughout the whole bootcamp on whoever's teaching, so that you don't have to run into issues later on and be missing a bunch of errors. You would rather run into the error as soon as it pops up rather than working backwards in your code. All right, so this built everything. You can see that it gave me a warning. This is because I'm not using this yet. We'll use it later, but that's okay. We'll work through it. So going back to our diagram, we can see that we had three instructions actually: initialize poll, initialize candidate, and vote. So we can just actually build those out right now. So in order to build those out, we can see that, so I actually have Copilot installed. I will also be using Copilot throughout this. Highly recommend using it. It's really useful. You can already see that it's trying to get me to create an initialized voting instruction. I'm going to ignore it and just do it myself, but it's a cool thing to go through. So we know that the public function, and we had this as initialize poll, we have to initialize the poll first. And we grab the context. So this is context. We're going to call it initialize poll. We're going to give it a poll ID. We're going to make this like a U64, so you can just have a bunch of polls. And then we're going to return, right now we're going to return OK. All right, so that's a base instruction. I'm going to create underscores here. So these underscores are basically just to denote I'm not using the variables, just to remove the warnings. We're going to anchor build, make sure we do everything right. So we can see that something went wrong. Let us make sure that we do it all correct. Oh, it's because the initialize poll we haven't done yet. So let's get started with that. All right, so one of the things that it noticed actually before we get started is that the program result's not correct. It's actually result, and that is correct. So now if we do a clear, so let's do a clear real quick and then rebuild, it should just have the context error. So there you go. So you have the context of initialize poll is not found. Perfect. So let's go build it. So if you remember in the previous example or previous project we built, we used the account macro or the derive accounts macro. So derive accounts. And we're going to create this as a struct called initialize poll. You can see it's, Copilot kind of already knows what we're doing. Doesn't know entirely, but we're going to create it ourselves. So struct initialize poll. We're going to use a lifetime for this. And then we have to create a bunch of different accounts within this context. As part of this initialize poll, we're going to be creating accounts. So that means we need 2 accounts already. We need the signer and we need the system program. Now, Anchor is really nice. It'll actually pull in the system program already to you, so you don't have to worry about that. We'll just need the signer. So let's go build that signer. So it would be, because we're getting money from it, it's a mutable signer. And then we just have this as a pub. I'm going to call it signer because it's just nice. Signer info. So we know this is getting created. Perfect. Great. we have a signer that's going to be used to pay for this account. So next thing that we need to do, if you remember correctly, we had the poll account. So we need to create an account for the poll. So let's go ahead and create it. So account, and I'll fill everything in just a moment. We just want to make sure that we set it up. So poll, this will be account info poll. That works out. And down here, we're going to create that struct real quick. So I'm going to use account. We're going to do pub struct poll. And we're going to put everything in this. So we're going to have a pub poll ID. So it already kind of knows what we're doing. Thank you, Copilot. So we're going to have a poll ID. That's going to be U64 as we mentioned earlier. We have a description. So this is pub description. We're going to call this a string. We have a poll start. So pub poll start. That's also going to be U64 because that's how you measure. It's going to be a Unix timestamp. We have poll end, which is also going to be U64. And then we have a poll index. We can have this, or we had it as a candidate amount. So candidate amount. And we're going to have this as U64. So this is everything in our poll. This should be everything that we need right here. And so we should be able to create it right here, create the account right here. So let's go build it all. If you remember last time, and Copilot is giving us all the answers ahead of time, is that you can use init to make a account automatically initialize. The next thing is we're going to have the pair. We have to denote which pair it is, so we're going to have to give it the pair. We have to give it the space involved. And so we had some variable stuff here. We have a string, we have a bunch of U64s. U64s, we know how many bytes they are, but the string might be a different amount of bytes. So we have to use something called max length to give, it's in a macro, to give the max length that this string could possibly be. So I was going to give that right here. All right, so to do that, we're actually using a macro called max_len, and we can just give the number of characters that this string can possibly be. So I'm going to just put 32, and that should be good. I think that's good enough. We could give, I guess we can do like a Twitter post, 280 characters. You can put a whole bunch of description in there. That should be good enough for this. So we have the pair, we have the size, and we're going to do another thing. There's another thing called init space that allows you to automatically calculate the space, and you don't have to do some extra work or math in your head to figure out how much space this is called. So in order to do that, you do hash, it's going to be derive init space. And so this basically allows you to get the space very easily. So when we do the space here, you can do space, whoops. It'll be always 8 because the way that Anchor does in the current version is that it always has 8 bytes reserved to it. So 8 plus poll init space. I think it's actually init space. There we go. And then we need the seeds. So if you remember earlier, we have the seeds as the poll ID. So we can actually pull that in and use that as a seed. So we're going to do seeds. You can see it as poll as ref. It's not exactly what we're going to do, but that's okay. We'll update it. All right, so the way that you pull in different parameters that you use is you'll actually use a macro called instruction. And you can see it pulls in the poll ID as a U64. And then what you can do is you can then use the poll ID. I think it's as ref. To do a seed for this poll account. So this seeds sets up the poll ID as seeds to get that poll account. And then finally, as explained earlier, you always need the bump. So we always have the bump in the poll. We have the signer, we have the poll. And I believe we can just run this now. Let's go ahead and do anchor build. Build early and often. Let's see if we run into errors. We did run into errors. Let's go fix them real quick. So traits bump, blah, 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 poll. Okay, so let's see. Oh, let's keep going up. Not found in scope. So it looks like something is not set as the same thing. Let's see, I did use that correctly. Declared initialize. We always have to go to like the top error. Good thing about the Rust analyzer, sorry, the Rust compiler, is it actually gives really good errors. So it says here the program, okay, cool. Initialized poll is not found in the scope. So something is wrong with this initialized poll. And that's fine. We can get there. All right, so we can see here, just looking at the error, the top error is use program type to add a system program field to your validation struct. This is because I'm creating an account. I actually need the system program. So pub system program. It's going to be a program of info system. So let's go rebuild it. Should have one other error, and that is fine. Okay, so now we have another error. We can see that other error disappeared. We can see that, oh, I understand. I did pair. We actually called it the signer. So it's just, that's okay. There's some misspellings. We do anchor build, and it looks like it's building. So that wasn't that hard. Just as a heads up, if you ever do run into errors, definitely go to the Solana Stack Exchange if you can't figure it out, and ask a question about the errors. It is very important when you do ask a question, however, to provide all the code necessary for someone to reproduce your error. If you don't give all the code, they might not be able to have enough information to give you an answer how to fix your code. So right here we have anchor build, and voila, we have initialized poll. However, if you know right immediately, you can see we don't do anything with the poll. We have the context, we have the poll ID, but we just return OK. Now, note with Anchor, and this took me a while to figure out my first time, is that if you have this init, it does create the account. So that is OK. However, there's nothing in that. So we need to give some information to it. So some of the other stuff that we have is we have a poll start and end. So we actually have to have that passed in as part of the parameters. So let's go ahead and add those real quick. And I'm going to take out the underscores because we're going to start using it, using all of these different things. So next thing is we have a poll start. This is going to be the U64 we're going to pass in. And then we have a poll end. That's also going to be a U64. And then finally, we have this description that we talked about. And we're going to, for this last variable, this candidate amount, we're going to use that to increment later. We don't have to do that in the initialization, but we do need to make sure that it's set to 0. So let's go ahead and set it. So we're going to do let poll equals mutable context.accounts.poll. This is so that we can update the poll account. And we're going to set everything. So poll ID equals the ID we passed in. The description is the description we passed in. We will make sure the poll start is set. And the poll end is set. And then the candidate amount we're going to set as 0. So this is everything to initialize that poll. So we have our first instruction. We're all good to go. So an important part of local development is testing your smart contract. What we're going to do is each individual instruction that we build out on this voting application, we're going to test using a testing framework called Anchor Bank Run. So let's go pull that up. All right, so if you just look it up, it's called Anchor Bank Run. And you'll see that it is a testing framework that allows you to test your smart contracts methods or your instructions and make sure that you're expecting the right values to come out. So let's go test it out. So the first thing that you need to do is you'll have to do this yarn add anchor bank run thing. I'm using npm, so I'm just going to do npm install. Use whatever your flavor package manager for Node is to install it. So it is called Anchor Bank Run. All right, so we've installed it, and now we have to get started. So if you go over here, there is a counter spec.ts. You go click on that, and there's already a test in there for the counter program. We're not using a counter program anymore, so we're just going to remove all of the information within it and create a new test. So let's go remove the whole thing and remove some more of the code. And I'm going to call this, or let's remove the counter because it doesn't exist. I'm going to call this voting, and we're going to call this initialize voting, or initialize poll, because we're initializing the poll with our instruction that we just built. So going back to the actual code, there's a few things that you need to do ahead of time in order to make sure these tests run. So one of the things is you'll have to go grab the program the smart contract binary and paste it into a folder called fixtures so that it knows what smart contract to use. We're going to do this manually now. However, later we'll do some things to make a trick to where it automatically copies over whenever you do build. So right here in target deploy, you'll see a voting.so file. We're just going to copy it and we're going to paste it into a fixture. So create a new folder called fixtures and paste it there. The next thing that I'm going to have to do is I'm going to have to pull what's called an IDL, which is kind of like an interface to help build and generate language-specific format for calling smart contracts. It's, if you're familiar with like Ethereum or something, it's similar to the ABI in those ecosystems. So I'm going to go grab that. You can see here, this is the voting IDL. It is under target IDL. It's called voting.json. We can see here in the example here that it is const IDL equals require the Puppet JSON, which is Puppet is the smart contract that they're using in this example. All right, so let's go copy it over. So we're going to do const IDL equals require, just like the other one, except we're going to grab voting.json. So it grabbed it immediately. The other thing that we're going to have to do is we're going to have to grab the program type. So our program type is under the types folder, which is under target. So let's go grab that. So we'll just import it. Import, it'll be called voting in our case, from target types voting. And so we have the IDL and voting. Now we can create what's called the context and provider that allows us to interact with our smart contract. So let's just copy these and we can get to using them in just a moment. So I'm going to put them right here. You can see it's erroring out. That's okay. It's because it doesn't have start anchor. We can just import it real quick. Let's say import. We can grab it over here and import at the top. Perfect. So it knows what it's talking about. Our tests are local to our folder instead of this test, which are in a specific test folder. So we just leave this as nothing because it's just going to test what's there. And then there's, if you look here, there is extra program, which is added programs and accounts. We're going to not do anything for the added accounts, but we'll do something for the extra programs. We're going to need the program ID, so I'm going to create a public key right here. This is going to be voting smart contract address, or voting address, let's call it that. And we're going to call it, it's a new public key. And we're going to copy the same public key that we have within our code. So if you go over to your lib.rs, you can copy over the ELY. For my case, it'll probably look different for your voting contract. So now we have the address, and we can put that in our thing. And if you look at start anchor, added programs, it has a name and a program ID. So we have to go add this right here. So we're going to do name. I'm going to just call it voting. And the program ID is just going to be our voting address. There we go. So we have the context, we have the provider. Now we have to create the program object. So you can see here that the program object is just created using the program type. So our type is called voting with the IDL and the provider. So this one's going to be called voting program. All right, so we have everything to get started. And Anchor makes it very easy to interact with different smart contracts using the IDL, because with this voting program, and you can already see Copilot telling us what to do, is we can actually just do await voting program dot methods dot initialize poll, and then give our parameters. All right, so we have initialized poll, and that's our method. And if you look at our previous, our actual instruction, it has poll ID, description, poll start, and poll end. So let's fill that out. So in order to do a U64 in TypeScript, you have to do new, and you can see it already knows what to do, anchor.bn, and we're going to have the ID of 1. The next type that we need is we need the description. So we're going to create this, what is your favorite type of peanut butter? The next two U64s that we're needing is the poll start and poll end. So these are actually Unix timestamps. So let's just go pull a Unix timestamp real quick. unixtimestamp.com, copy the timestamp, and we're going to do another new anchor bn, big number. I'm going to do this at the beginning of existence at 0, and then we're going to do another one we'll just add a bunch of time at the end. So let me go didn't grab this, so let's just grab that real quick. There we go. So I'm going to add a bunch of time at the end. This is just increasing numbers significantly. This will be much in the future. So if I were to like copy this and paste this to convert to see what time it would be, this is in 2027. So it's years ahead of our current time, and we're good to go. So now we do the initialize poll. The last thing you need to do is you actually have to call the RPC with it. So this .rpc after the methods call actually will call the RPC to execute the instruction within the program. All right, so we've done that. Let us test it and see if it all works. So anchor test. All right, so it tested. It ran, looks like it ran, found test screen. Error configure port is already in use. So one thing that we need to do is with anchor tests, we're already running both a validator, a Solana test validator behind the scenes. So we actually needed to skip it. So skip local test validator, I believe, or maybe it's local validator. It's always good to read the manual beforehand to see if what you're doing is correct. So you can see it's skip local validator. And then we also need to do skip deploy because we're using anchor bank run, which allows us to skip a bunch of steps and run directly within the validator, or what's called the bank part of the validator, instead of running on a very heavy lift of the local test validator. So let's all run that. So anchor test skip local validator and skip deploy. And so this will run our test. You can see here it's found our test script. It's loaded our program. The one thing that we'll see right here is that it's going to fail because it doesn't know what this voting program is. And the reason being is you can see here that it says counter. And that's not running one of the recognizable program names. So let's go update that. If you go over to anchor toml, you're going to see that in here we have programs.localnet counter equals that address. So we need to update that. So let's go update that to our current program, which we called voting. Then we run the test, and if everything is done correctly, it will pass successfully. So we can see here, it tested our voting program from our binary file, and everything looked like it worked correctly. It did the initialize poll check. Now, note, this is not a good test. It doesn't do anything. It doesn't check anything. So we actually need to go pull that account and make sure that we did everything correct. So one thing we're going to have to do is we're going to have to go grab that poll address. So this is going to be the poll address from our program-derived address, because if you remember, our seeds for the poll account is the poll ID. So we have to do this dot public key dot find program address sync, and we have to give the seeds. So the seeds will be it'll be buffer. It'll be new anchor dot bn of 1. So that is the actual .2 array-like buffer, little Indian 8 bytes. This is how you grab the buffer from a U64. So we have that, and then finally we have to give the program address. So this requires the seeds and the program address. So that will be the voting address. Perfect. So this should be a poll address that is going to be created based off of this initialized poll instruction. And let's go verify it. We're going to first console log it. We're going to grab the poll account and then console log it. So const poll equals await voting program account poll fetch poll address. So this is saying, hey, fetch the poll account off of this address. And now we're going to console log it. All right, let's go see what it looks like. All right, so we can see it passed. And we can see right here, we have our poll ID of 1. We have the description there. Poll start is at the beginning of time. Poll end is this number. And then candidate amount, there's no candidates yet, so we have 0 candidates. So we've tested it, all looks great. It's fantastic. Now we can do some expects so that this test is actually a good test, because currently it doesn't actually test anything. So let's do some of those tests. So right now, we can do 2 of them because we have the poll. We can go grab it, and you can see already it says poll ID to number equal 1. And then we can do another poll. It's not the question. Whoops. It's going to be the description. Equals this, what is your favorite type of peanut butter? And then we can also do, just for good measure, we can expect that poll description, poll start to be less than, so let's go grab that. To be less than poll end, because we know that it should always be under that amount. So let's go, also we have to change these to numbers, otherwise it won't work correctly. Poll start to number. All right, so let's test it. Make sure that our test actually passes. All right, so our test passed. You can see the poll got logged, and the poll account was actually initialized. So we've done everything to initialize the poll. Now we can get to initializing candidates, which will be very similar to what we just did to initialize the poll. So let's go back to the program and start building that out. All right, so the next instruction, if you remember from this diagram over here, is we have the initialized candidate. So let's go build it out. It's going to be initialize candidate. We have to create a new context using different accounts. Context initialize candidate is the context name. We're going to have the candidate name. And do we need anything else for a candidate name? We don't need candidate votes because they're going to be set at 0. We also need the poll ID, otherwise we can't pull the right poll that this is related to. It's going to return. We're going to just have a OK return first. So let's just return OK. All right, so we have that. Now we need to go create the actual account struct. So let's once again, we're going to do derive accounts. We're going to use, if you remember, one of the seeds is the candidate name, and the other seed is actually poll ID. So we need both the instruction information. So this is going to be instruction candidate name poll ID. One thing to note, at the current time, you need to make sure that they're in the same order, because it'll actually pull the parameters after the context in the same order that they are listed in the actual instruction. So if you don't have them in the same order, you'll actually get the wrong data. So just a quick note, this will be pub struct initialize candidate. All right, so there's a few things that we'll need. So as we saw last time, we absolutely need the system program because we're going to be creating a candidate account. Same thing, we're going to need a signer because someone has got to pay for that new candidate account. We're going to need the poll because we have to use it to increment the amount of candidates that are within the poll. And then finally, we need the candidate account, which we'll do in just a moment. So one thing you might have noticed is that in our poll account, we originally had payer, signer, space. Because we don't actually need to create it, we're just referencing it, we'll just do seeds equals the seeds and the bump. Finally, let's go create our other account. So this will be a new account. This will be a candidate. You can see it already started pulling everything. We'll have the poll ID and the candidate name, so it's just a separation or switch of these two, and those are our two seeds. Then we have the bump. So then we go to pub candidate account info candidate, and now we have to go create that actual candidate account. So once again, account, pub struct candidate, and it's going to have candidate name and candidate votes. All right, so we have the candidate. We have all the information for the candidate account. One thing that you note, we used init space again, so we're going to have to derive init space yet again, like we did on poll on candidate. And let's do an anchor build, just to make sure. We've done a lot of code. Build early and often. You can see I made a error here. It's because I used string, so we must use a max length. We can do that again and grab this on the candidate name. So I'm going to say the candidate name, the names are normally not longer than 32 characters, so let's lower that to 32 characters. Probably lower it even more to like 16 after a little bit of testing, but that's okay. You can see that we got a bunch of warnings. These are just because we didn't use these different parameters yet, but it did build successfully, which is a good thing. That's why you always build early and often, otherwise you have to go redo a bunch of code. All right, so we have a candidate name, we have the poll ID. Poll ID is actually never going to be used, so we make sure that it is underscore. The candidate name will be used, but it's not. It's going to be used like this, so we can actually make that underscore as well to get rid of that error. It's going to be used in the instruction down below. The final thing is we have the candidate. So some of the things that we're going to have here, actually the candidate name will be used. All right, there we go. So we're going to set the candidate name in the account. So let candidate equal the mutable context accounts candidate. So we grab the candidate account, candidate name equals candidate name, and then candidate votes equals 0, because you need to always start with 0. Let's go build that, make sure it works all right. All right, cool. So it pulled this. We have the initialized candidate. All right, so now it's time to test initializing the candidate. So what we're going to do is we're going to create a new test right up here. It's going to be integration test initialize candidate. And we're going to test making sure that we're actually initializing our crunchy and smooth peanut butter and everything works as expected. So we have this. I'm going to also create, just for the future reference, because we're going to have to vote, I'm going to create a vote test because we know it's going to happen, so might as well have it there. So we have a vote test. And now, because we have multiple tests, I want to make sure that I pull this context provider and voting program out so I never have to use them again. So we're going to quickly set them over here. So this is context, let provider, and let voting program. And we're going to do a before all. And we're going to create a function that runs and sets these so that we always have them before every integration test. And we just pull these guys right back up there. Oops. There we go. Copy and paste. Remove the const. This is an async. And we got to remove these consts as well because they're always going to use the provider and the voting program from above. Actually, we don't even need them at all, so we just remove them. Perfect. All right, so let's run it, make sure that it still runs. So we don't want to have to have done all that and it breaks. That wouldn't be great. All right, so we have all our three tests passing. The initialize poll, as expected, is doing what it needs to do. Initialize candidate and vote don't do anything yet, so I hope those passed. It did. So now let's build the initialize candidate one. So it should be very simple. We should just be able to call the initialize candidate instruction. So if you remember the vote program or the initialize candidate program, it took a candidate name and then a poll ID. So we have to go put those both in there as parameters. So this one's going to be, we're going to switch it to be smooth first and then the number. Make sure you set the name first or set the same parameter order that you had in your instruction. Otherwise, you will get an error. And so this is our ID of our poll for smooth. I'm going to do this twice for both crunchy and smooth. I'm going to see if it runs. Let's make sure it runs correctly. All right, cool. So I was able to create the crunchy and smooth candidates. And I believe if we run it again, okay, so it's doing the initialize candidate. Perfect. Okay, so we've initialized those two candidates, but that doesn't really mean anything unless you actually grab the candidates. So let's go grab them real quick. So const, we need to go get the crunchy address. It's going to use find program address sync. And if you looked at our actual, our seeds, our poll ID and candidate name, so one of the seeds is already there. The first seed is poll ID. Let's just verify with our lib.rs, our actual smart contract. The first seed is the poll ID, then is candidate name. So let's set that up correctly. So poll ID should be first, which is new anchor, let's just comma, anchor.bn. And it's what we had earlier. So if we can just pull the same code that we had earlier to array like buffer, LE, or the little Indian 8. And crunchy, so that's the crunchy address. And then we can just for before we move forward, let's go grab that candidate. Crunchy candidate equals await, get the candidate count, and let's go console log it. All right, so let's test it. All right, so you can see here the candidate name is crunchy, candidate votes is 0. Let's grab the other candidate. So I'm just going to copy and paste this code and change everything to use smooth. And then once we have all that set up, it should be ready to go. There we go. So I've copy and pasted it. Now we have all smooth. And we should be able to see the console log for both smooth and crunchy. There they are. They both have 0 votes. Perfect. So we have all those things. Now let's actually do some real tests. So you have to, I'm going to set them all because we just initialized them. The most important thing is that the votes should equal 0. So if you look over here, the candidate account, let's go grab him real quick. His candidate votes should be 0. So it's going to be candidate votes equal to, I guess it's 2 number, is equal to 0. New BN, new anchor, because we have to make sure it's equal to the U64 big number format. Let's make sure that works as expected. Perfect. Okay. So expected 00 got 0. So it's equal to the same. We just have the wrong format. So let's update that. Candidate votes to equal. I think it's because it's already a beak number, so we have to make sure it equals the same. There we go. Let's see what it got. 0, 0, received 2. Interesting. Let's see what we did wrong here. So received, expected, received was 2. Okay. So it's probably because we did the, let's see, candidate votes, big number. So I think we can just do 0 here, actually. Let's check. There we go. Because we send it to number. There we go. So we set it to number, and it's equal to a number versus the big number equivalent. So this expect, we can copy and paste it right over here. And we can use it for the same smooth candidate. And so now we have 2 tests to make sure that their votes are 0, because that's the most important part, that whenever you initialize, they initialize as 0. Because if they initialize as more than 0, then it's basically cheating the system. You're getting more votes for your candidate than you previously had. So next thing, we're going to create a vote instruction. So let's go create that right here. So it's going to be pub function vote. See, it already knows what to vote. We're going to have, it says candidate ID. It's not actually a candidate ID. We're going to be voting for a specific candidate name. And there's our string. It's going to output a result. One of the things that we actually didn't do in initialize candidate, now that I just remember, is that the poll, if you remember correctly, the poll had a candidate amount. So we actually have to also increment the poll. So let's go do that real quick. Equals reference poll, and then do poll plus equals 1. All right, so that's set up. Our vote amount is we have to grab the candidate from the candidate accounts, because we're going to set up this vote context in just a moment. We'll call it candidate, so it's all the same, and just plus equals 1. So let's go create that vote context. So once again, drive accounts. There is nothing, is there anything? Okay, so we still need the candidate name. It needs the poll address, because you have to vote for a poll address. So let's grab that as well. It's going to be the same thing as over here, actually. There we go. So candidate name, poll ID. So it's going to be the exact same thing. We're going to have to pull a lot of the same accounts, except for you're not going to have to create any accounts. So we can remove the system program, because we're not creating accounts. You can remove all of these initialize things. So you just have the seeds and bump. Do we need we need the signer, because there's still a signer on the address, but it's not mutable, because it's not paying for an account. And then we need the pub struct. So we called this the vote context. So we need to make sure that we set that correctly. So pub struct vote, and let us anchor build it. Let's make sure I didn't mess up anything. It looks like I did run into an error, so let's just double check. Oh, it's because I don't have the lifetime set up on the struct correctly. So that got rid of some things. And then let's see, the public account could not resolve. That's specifically the signer, because I'm not doing anything special with that. Remove that, and it should all work. There we go. One thing that it said is that it didn't know what to do with candidate name. I think it's because it's in here and doesn't actually use anything. We're just passing it in so that we can derive the account successfully. So now, since we added the underscore, it should compile with no error or no warnings. There we go. It works. So what we need to do, once again, you copy and paste. So copy that voting.sol over here. Voting.so over here into fixtures. And then we should be able to write the spec, the test for it. So let's go vote for one of our candidates. So what we can do is we can do an await voting program dot methods dot vote, and we have to vote for our specific candidate, and we have to always remember to hit the RPC. All right, so what we need to do is make sure that we're always going to pass the same thing. So candidate name, then poll ID. So the first candidate name will be our same ones that we did earlier. So right here, I'm going to vote for smooth because that's the kind of peanut butter I like. It's going to have a poll ID of 1, and that is fine. And then we have the RPC calls it, and let's see if that worked. Let's see if this part just worked, because that'll tell us whether or not the RPC worked. So let's do anchor test. Remember always to skip local validator because we're using bank run, and then skip deploy because once again we're using bank run. So we get to skip a bunch of steps and see if it worked. So it worked. However, we don't know what actually happened. We can see that the vote actually was working here. So we know that it's actually voting, which is great. We know that the vote instruction is being called. We don't know actually what it's doing though. So let's go grab that vote account and verify exactly what is happening there. So we'll have to go and get the address. So const, we'll have to go get the smooth address. So it's actually, we can copy and paste this up above and then just pull it from there and expect it equal to 1. So let's go grab it. So the smooth address, it is the same address as before, voting address. We have the smooth candidate, and we need to make sure the equals to 1 now because we have voted for smooth at exactly 1 time. So it ran into an error. Let's see what it expected. Expected received 0. Okay, so let's figure out what happened here to where it did not increment 1. Did we actually +1? Candidate votes to number, smooth candidate. So this is fetching the smooth address. It should have incremented because we did a vote RPC. That should have worked. Let's say expected 1, received 0. So something happened to where it did not increment. So let's figure out what happened. So we have the candidate. We have the candidate votes. We did a plus equals to 1, and we sent an OK. So why did this not increment? Let's figure out. So one thing that you can always do is you can actually send messages or logs to figure out how many votes something has in your smart contract. So we're going to anchor build this, and I'm going to pull this over and verify that this logic is working as expected. If it works as expected, that's great. We're good to go. And we just going to need to figure out what else might have happened. So let's go copy over the .so again. We copy and paste. And let us test it. And we should be able to get logs, the program logs, that it tells us exactly what happened. So we go up here. We can see the votes for 1. So something was being pulled that did not happen as expected. So it got voted for 1. That's great. It came back. It was 1 vote. We did get it afterwards. I wonder if let's go pull the actual account address. So smooth candidate, fetch account address. It should have happened after the vote. It's perfect. All right, so this is actually a really good point to make. It did not increment earlier because even though the library was saying I incremented whenever we did this message. And this is because all accounts by default are immutable on Solana. So unless you say that the account is mutable, it will not actually update the account, even if you pull in the candidate account as mutable. It doesn't matter, because by default, this candidate account will also always be immutable. So we actually have to go here, and we have to make sure we declare the account as mutable. And we didn't do this earlier, so actually the poll account also didn't update. So I'll add those 2 things. So now that we added mutable, so let's do an anchor build. All right, and then we got to copy over our .so file again. Copy it over to our fixtures. and then let us run the test. Perfect. So all three passed. We can see that the candidate vote for smooth is 1. We can see it's not the errors, but the logs went from 0 to 1 here, as expected. And from here, what we have is we have a fully working voting smart contract. We have tests that test it. And that's all we're going to do for this project. We have all the stuff on the smart contract side. Everything's interacting. We've run tests on local. We've run everything locally on the local test validator. We have our full local environment set up for success. In the next project, we'll actually be using this vote smart contract and putting kind of a front end on it, but making it more social. So look out to the next project. And for that, I will see you next time. For this next project, we're going to bring the previous voting application to people's favorite websites using Solana Actions and Blinks. Solana Actions are a specification for an API that can return a transaction on Solana to be previewed, signed, and sent. Whether it is a button, website, or QR code, Actions make it simple for developers to integrate the things you can do throughout the Solana ecosystem right into your environment. Blinks are blockchain links. They turn any action into a shareable link, allowing any website that supports links to be the starting point of a Solana transaction. As a result, Blinks transform websites or social media into a platform for executing transactions, all without taking the user elsewhere. Any website could be the surface for your new application, creating both a decentralized and user-friendly experience. In practice, Actions resemble a typical REST API call. A user interacting with a website would trigger a GET call to retrieve information about what actions are available. Following the list of available actions, the user can then choose an action to execute, which will then start the transaction signing process. We will be making all our votes in our previous application be actions, allowing them to be executed without a traditional front end with the help of Blinks. Now that we've had an overview of Blinks and Actions, let's get started building them. All right, so with the project that we just completed, the voting application, we're going to add something called Blinks and Actions. There is a lot of different amount of work that you'd have to do for Blinks and Actions. We're going to go pull up the docs right here, just kind of go through all the ins and outs of the technical know-how. So first off, we can see this is Actions and Blinks as the title here. We can see that to get started, we need to do npm install @solana/actions. So let's go ahead and do that right here. So we're going to have to go outside of our Anchor folder. We'll have to start with the voting dapp and install our @solana actions. And with what we're going to do, we're actually going to need to add a couple steps that we didn't do in the previous project to make sure that the Blinks and Actions work for this project. So one of those steps is we never deployed our Anchor smart contract to our local test validator. We were just using a Solana bank run to do all the testing. But now we actually have to test on a local test validator to bootstrap some UI on top of it. So let's go into the Anchor folder, and we're going to do Anchor deploy. Now, this might be different based off your Solana config. So actually, you might need to check that first. So if you do Solana config get, you'll get a bunch of data based off of what environment you are set up with. If you want to set your config environment to local, you would just do Solana config set -ul. That will set everything to local so that you can just do Anchor deploy. So let's do Anchor deploy. And what this will do is it will actually deploy that voting binary that we used yesterday to our local test validator. And we can see here the program ID is that. And let's go check it out in the Explorer real quick. So we go to explorer.solana.com. We go set ourselves up on local. And we go to our program. We can see our smart contract has a program account. The address is here. We can see what the balance of SOL to store it was, and then when it was deployed. And we can see a bunch of information of like, this is the upgrade authority of myself who deployed it. and a bunch of other information of whether or not it's upgradable, it's executable because it is a smart contract, etc. And now that it is deployed, we also will need to start setting up the actions to interact with that smart contract on our local test validator. So we installed this actions SDK, and the next step will be that we have to set up this GET request and this POST request to actually do something on chain. If we don't have those, it won't actually do anything on chain within these blinks. So there's a life cycle diagram here. Basically, what we'll have is that someone will do something or click a button. It'll send a GET request to get metadata on what are the available actions that this user can do to your server. This will show up on the UI. The UI will then allow them to click a button to perform an action, which will make a POST request with their specific account public key to the action provider or our action server. We'll then respond with a serialized transaction. We'll show the transaction details to the user, allowing them to sign that transaction. And then they can approve it if they want, and it will actually interact with the Solana blockchain. So that's the full end-to-end of how Blinks and Actions works. So first off, let's create this GET request to get the right information to do our actions. So let's go pull down here. We can see there's a bunch of information about Blinks. We'll get to this in a moment. But ultimately, our GET request has to have a Solana action URL that describes an interactive request for the signable Solana transaction or message. So let's go ahead and do that. So what we can do is we can go into our web app API and create a new folder we'll call it vote. I'm just going to copy and paste this route so that we have a single GET request. That's fine. And if we ran this successfully, which if you're not already running your server, you would just do npm run dev, and that will run both your front end and your server side. We can go ahead and check if this GET request actually exists by going to our local host and going to, API vote. So let's go ahead and check it out. So if you go to localhost 3000, should be API/vote, and this should return some information, hello from the API. This is the very basic Next.js server-side work. Just as a note, we are creating quite a heavy application for these Blinks. Next.js server-side is quite heavy for this usage. Recommend like a Node.js server if you can, like an Express server. But because we have our scaffold and we'll later on in this course build the actual front end for the voting application, we're just going to use this back end and bootstrap it with this voting action. All right, so we got some information from our server using the API vote. Next up, we need to actually return valuable information in order to display the blink on any social media. So let's go ahead and do that. All right, so if you go to the Solana documentation, again, for actions, you can see that the metadata expected is this action GET response. It has an icon, a title description, your label, has some links and linked actions, and then an error. So there's a bunch of different information that you can respond via this GET request. So if we go over here, we can go ahead and create that. So we can do a const, we can call this the action metadata equals of type, this is actually type action GET response. Equals, and now we're going to start filling in our metadata. Action metadata is required. Missing properties, yep. So it's just saying, hey, you're missing some properties, icon, title, description, and label. So we're going to fill those in real quick. I'm going to fill them with nothing just so that everything will play nice, and then we'll actually fill in with the real information. So action, it's icon, title, description, and there's one other thing, and it's label. All right, so we have some basic action, get response, metadata. Now we actually need to fill it in. So first off, what we're doing for this is we're creating a voting application that can be viewed, and we need to create an icon that is choosing between crunchy and smooth peanut butter. For completeness sake, or being able to get it done really quickly, we're just going to look up a peanut butter icon image and pull it from the web. So if we go to just a peanut butter image, I can just go grab some peanut butter. This one looks fine enough to me. And I'm just going to copy the address, and we're going to use that as the icon. All right, so now we have the title. We're going to say vote for your favorite type of peanut butter. That's going to be our full title, and then the description is vote between crunchy and smooth peanut butter. All right, so now we have this label. We can add something. This will be for a button. We'll just put it as vote for now. We're gonna have to do some extra work in order to make it actually usable on the Blink, but I just want to showcase what it looks like. All right, so in order to return this response, we're going to return response.json and give back our action metadata. So there's our response. Everything's good. Now, we have this get response, and let's go test it real quick. We can just refresh this get request. We can see, hey, there's a nice little JSON that got returned. It has an icon, a title, description, label. Perfect. We have everything there. Now let's actually see it in the Blink. So in order to do that, there's a website called dial.to, and you would do to test locally. The query parameter is action, Solana action, colon, and then whatever your localhost API is. Ours is localhost 3000 API vote. So let's go look at it. All right. So this is what's going to load your actual Blink so that you can view it and see what it might look like on a social media like Twitter or Reddit or whatever. Now you can see it's not loading. Now I meant to go run into this error, and you'll see that it says something about CORS. Look at that. All right, so the vote ran into a CORS error. This is because what is it? Cross-origin resource sharing. It's to help protect you. We're going to do some things to get rid of this error, and this is just a common error people run into with Blinks. So let's go ahead and add that. What's really cool is we can just add this as headers, and it should be part of what is in the Solana Actions SDK, which provides a very nice headers for you to already use. All right, so what you would do is you would have headers, and you would have actions, CORS headers. You can see it's coming from the Solana Actions SDK. And so that should now give you all the information to properly serve your action via a Blink. All right, let's go look at it within our dial.to. There we go. So we can see right here is we have our nice little image of the peanut butter. We have the title, vote for your favorite type of peanut butter. And then the description, vote between crunchy and smooth peanut butter. You can see that this part says the action has not been registered. Part of the whole system for onboarding Blinks today onto social media is you have to actually get your action registered via some kind of registry out there. There's one that's managed by Dialect. There might be more by the time this video is live. Basically, it's not registered. It's, hey, use at your own risk. We don't know what this actually does. That's okay for now. So we have our Blink. This is what it looks like. Looks really great. If we hit vote, nothing's going to happen. It's going to say failed to fetch. And that's because whenever you do the vote, we can see here via the network tab, it's going to try to, well, one, it's going to do a CORS error, and then it's also trying to do a post, and it's failing. So let's go ahead and go through that. So one thing to note is that As part of the full end-to-end for getting the post, we're going to also have to create an options return request. And what we can do with that to make it very easily is we can just make it equal to the get so that it knows everything that it needs to do. So let's go ahead and do that real quick. All right, so in order to do that, you would do export const options and just make sure it equals the get. And so now when we go back over here and we refresh, let's go inspect, it should just fail the post now. There you go. So the post failed, the method's not allowed. It's because we haven't created the post yet. Perfect. We're running into all the errors that we expected. Now we actually have to create the post. But before that, you notice that our get request just has vote. This is actually not voting between crunchy or smooth peanut butter. It's just vote. That's not enough information to present on your blink for someone to make a good enough action. So what we're going to have to do is, if you look in the actual documentations, is there's something called links, and there's these linked actions that basically give a list of related actions for this user to possibly perform. So let's go ahead and add that real quick. So we're going to do linked actions, and it's a list. So links. It's going to be a list of possible actions. So let's create a actions list as well. This is going to be linked actions. Whoops. And let's go ahead and look at that and see what it's supposed to look like. Just as an example, it's always good to figure out what these things are supposed to look like ahead of time. So you can see here the interface for a linked action has the endpoint for the action, has a label. This is different from the original label we had, and a parameter for acceptable input if you want to give input on the actual blink. So we're going to have the action, and we can see it's a list of linked actions. We can see here it's already bringing some things up. We can pull these out because it's only, let's say it's only href and label. And we have this vote crunchy and vote smooth. So we're going to do vote candidate equals crunchy as our query parameter, because we're not going to create different posts for each of them. And vote candidate equals smooth. Close the bracket, and we should have everything else. If you're not find name action, that's okay. Let's figure out what's going on. Property of missing action, required type linked actions. So let's go ahead and update this so that the compiler is happy, and that'll just be fine. So the way that it's actually supposed to be is it's just because I had a bracket instead of curly brace. So now we have the total actions that some user can perform. We have the label, the original label of vote. It's not going to be used anymore. And then we have the links and actions of what someone can actually do. So let's go ahead and do that real quick. Let's double check. Yep, we can see all the extra information. And let's go look at our blink, see if it's updated. And you can see right here, we have a vote for crunchy button and a vote for smooth button. So now our blink looks as expected, and we have everything set up on the metadata in order to execute our blink correctly. Now, as you probably can guess, still will fail with a 405 on the post because we have yet to create those posts. So let's go ahead and get started on that. So we're going to create one single function, export async function post. And we're going to get the information from the request from specifically the URL parameter so we can understand whether or not the candidate is going to be a crunchy or smooth peanut butter. So you can see there's already Copilot is already trying to give me some information. I'm going to ignore it because I want to write my own. All right, so the way that we do this is we would first grab the URL, and this would be grabbed from the request that came back.
Next, we're going to grab the search parameter, which we had as candidate, as we saw up here, the candidate equals crunchy. And now we need to make sure that the candidate given is actually a valid candidate. So let's make sure that the vote is either crunchy or smooth. That way we have a good return back to the user. And if they somehow enter something wrong, it's not going to give them a weird error. We don't want to surface strange errors that don't make sense to the user. All right, so we're going to do if candidate is not equal to crunchy and or smooth. We want to say invalid candidate, return status of 400, and headers will have to also, once again, be those action course headers. Otherwise, it won't work. All right, so we've done all of our testing or our validation of input. We now have our candidate. Now we have to actually create the transaction to send back. So in order to create transactions, we're going to have to need a few things. We're going to need a block hash, we're going to need the message, and we're going to need any signatures that we possibly need to be added to that transaction. Thankfully, this transaction does not need any signatures on the server side. Sometimes maybe you want to sign something server side. In this case, we don't care. So I'm going to create a connection. This will be part of web3.js. And we're going to have a connection off of HTTP. It's going to have to be 127.0.0.1 at 8080.99. This is our local test validator, and we're going to use the confirmation status of confirmed. And so what it's a commitment status. So commitment status, what that means is we have a few commitment status levels. There's a process level, there is a confirmed level, there's a finalized level. So those levels are telling you how certain they are of a transaction making it on the cluster. The processed ones, hey, I found it. It's not yet confirmed. Confirmed means it's confirmed by 66% of the actual cluster. And then finalized, it's confirmed by 66%, and there's been 31 blocks afterwards that were also confirmed. So finalized takes a lot longer. Confirmed is generally safe. At the time of recording, there's never been something that was confirmed that didn't make it to finalized. All right, so next up, what we're going to have to do is we have to grab all the information that we need to from the URL, namely the account that the user signed with on the Blink, in order to create the transaction successfully. And so the body of the post request, if you go look at the post request that is being built over here, so let's go look at the body of the post request. Payload. You can see that it's giving my public key that I have tied to this wallet to be used. So we have to go grab that right here. So it's going to be body of type action post request equals request.json. And I believe it's going to be, this is a promise. Yeah, so it returns a promise. So we need to await it. And so now we have the body. Now we need to go grab the account. So const voter equals body dot account. So this will have a type of account on the body. Now we want to make sure that this account is an actual valid account. So one thing that we can do real quick is we can do new public key, because we know it should be a public key, on the body of account. If it's not a public key, this will error, and that's fine. That's to be expected. So cannot find quick fix, just import it on web3.js if you haven't already. Now, if this does error, we want to make sure that it errors gracefully. So let's go ahead and add it over here. So I'm going to do if, we're going to do a try catch right up here. And I want to make sure that the voter is actually a public key and give back an error that makes sense. So we're going to return right over here, or we're going to try to make voter equals new public key body account, just like we did up above. We'll move it right over here. So if that passes, we can just move on. If it doesn't, we want to make sure we return a valid response. So it's going to be invalid count, 400 battery request. Same once again with the CORS headers. All right, so we have that error. Perfect. Now let's actually start building that transaction. Now, if you remember from testing, and I can just pull this up real quick, we used basically a vote program in order to initialize the candidate. We did some information on, let's say, on voting for the candidate. What we're going to need to do is we need to grab specifically this method right here, and we need to pull the instruction. This right here right now just sends it out as an RPC call. We don't want to do that. We want to actually use it as an instruction. We also need to make sure that we are adding the signer correctly and it equals the account versus us signing on the server side, because in our case, we don't care about signing on the server side. So we have to do exactly what we did with some additional differences to create that voting program. All right, so like here, where we are creating a provider, we're grabbing the IDL, the voting type, we're going to have to do the exact same thing over here. So let's go ahead and pull that out. So we're going to pull out IDL equals your voting JSON. I'm going to make sure that that's actually where it is. I don't think Copilot gave me the right answer. So this is going to be backwards, backwards, backwards. I think one more actually. Yeah, backwards, anchor, target, IDL, voting, JSON. So you can think of that, like this is a lot. What's great is about on Next.js, you can just do this and it will pull you back to the web folder. Then you can just go back and move into the anchor. So we have the IDL, perfect. Now let's go also import voting, the voting type. And it's from target types voting, just like we did in the test. So now we have the voting type, we have an IDL, and now this is where it kind of it's a different thing, because we need to create a provider to create this program. And we don't actually care to have a bank run provider, because that's used for tests. We need to make sure that we use the right anchor provider in order to create our program on our specific post request. All right, so up here, what we're going to have to do is create the program. So program of anchor.program voting, because it's our voting program, equals new program. Don't actually think we need to do this anchor thing because we already have it imported, which is nice. Let's pull it in. New program of IDL, and it's asking for a provider. Our provider is just going to be our connection. So we need to make sure that this is after when we create the connection. All right, so let's go look at what the error we got. Looks like it doesn't really know what this is. So let me go, expression is not constructible, no construct signatures. So this is probably something to do with Next.js. So part of Next.js, what you're going to have to do is you actually have to go update the Next.js config in order to properly do it. Also, I have two news here. Oh, it just worked out of the box. So normally, in case you run into this error, because sometimes you will, you're going to have to update the Next.js config in order to properly compile this correctly. This one we didn't have to because it seems to have recognized it perfectly. It's great. But just as a note, if you're running into problems with this specific one, you can just look it up. It's a common error. You'll just copy and paste your error, and you will be able to find it very quickly. But we have the program. Now we need to grab the instruction for voting. So we're going to grab the instruction right here, and it's going to be program.methods.vote. And if we remember from our counter spec, our test earlier, we're going to need to vote, we're going to need our specific ID and the actual smooth or crunchy. So let's just double check, smooth and crunchy. We want to make sure that it says crunchy capital and smooth capital, otherwise it won't be pulled in correctly via our smart contract. So we have crunchy and smooth. So we're going to go put that in there. That's going to be the vote. It's going to be the candidate if we set it correctly. Yep, candidate. So we're going to vote the candidate and then new anchor dot, dot bn of 1, because that's going to be the same thing as we had earlier. Anchor bn of 1, so that we have the right information of the poll ID to give. So it's saying that I haven't imported it, so let's go import anchor real quick. Actually, we can probably just pull in bn. Let's just pull in bn from anchor. That would be even better. There we go. So we have the vote. The last thing is we need the actual instruction, because we're not going to be calling the RPC. All right, so we have an instruction. This returns a promise of instruction. Let's just await it because we don't want to just have a promise. So there we go. We have our vote instruction with the given candidate. Now the one thing that we don't have on here is we don't have the accounts. So one of the accounts that is required is we're going to require the signer. And the signer is going to be the voter. And so that's all we need to add is the signer account. This is so that the instruction knows that, hey, I'm not signing it here. You're going to be signed somewhere else. And we should validate that the signer equals the person that passed in the original request via the blink. All right, so we have the instruction. Now we need to get a block hash. So let's go ahead and const block hash equals, it's going to be await get recent, not get recent block hash, but it's going to be a different RPC call. Let's go pull that out real quick. So not get recent block hash, but get latest block hash. And so this will give us some context. You can go look at this return. It has basically it tells you whenever this block hash expires. If we haven't learned already, block hashes expire after 150 confirmed blocks. So if you're trying to use it and it's too late, it's gone. This is to prevent replay attacks on Solana. It's all good to go. All right, so now let's create our transaction. So const transaction equals new transaction dot add instruction. And so this is a new type of a new transaction. It's going to say that I need it from web3 address. There we go. We have the instruction. Now we're missing some things on this though. We have to be able to say, hey, what am I expecting and what's my block hash? So let's go ahead and add that as well. So the way that you do that is in here, you're going to add some information. You can see that it already knew some of it. It's going to be the block hash and the fee pair, but you can see, oh, this is not a valid thing. It's because it's a deprecated constructor. The one that we're going to be using is, I believe it's this one. Let's go pull that. So we need the fee pair, the block hash, and the last valid block height. So let's go ahead and add that. So we have block hash equal to that block hash, and last valid block hash, block height, which will be block hash, and there should be a last valid block height on the block hash we got earlier. There we go. So we have the transaction now. And finally, we have to return it as an actual response back to the user on the blink. All right, so let's go ahead and do that. We're going to do const response equals await create post response. This is a thing from actions. This is going to be a different type. So let's go ahead and pull that out and see what it expects. So it expects your fields. This field is just going to be the transaction. That's all we care about. So this is going to be of type fields. Transaction equals our transaction. All right, so we have our response. This is the fields that we have in it, just the transaction. And finally, we need to return it. So return response.json, and we always remember to add the course headers. Otherwise, it's always going to fail. All right, let's go ahead and test it out and see if we did everything right the first time. All right, so we'll go refresh this blink. We can see here it has the vote for crunchy and vote for smooth. And if I click one of them, it should pull up my wallet in order to sign for the transaction. There we go. All right, so we're here signing for the transaction. If you run locally, there's going to be a lot of information here. What you find usually with wallets is that they're not doing any like caching on local, they're just skipping it. We can just confirm it because we know that we're working on local. Oftentimes, if you do see these errors, though, I would not confirm your transaction, just as a general FYI. So let's confirm it. And you can see there's a bunch of errors showed up, but that's okay. The response got back as 200 OK. And these errors are just the wallet was unable to figure out what was going on. And so we have now an end-to-end blink. So let's go ahead and check that on our Explorer. So let's go pull up the transaction history. And we should be able to see different transactions on this program. So looking at the program, let's see if we can refresh a few times. All right, so let's go ahead and figure out what might have went wrong. All right, so the reason why this did not work is because what's happening is we're doing this transaction. Everything is correct here. We have all the correct information. However, we have a poll ID of 1. Now, if you remember, we just deployed our program earlier, our smart contract, onto our local test validator. We don't actually have any information about this actual smart contract or this poll or these candidates. So we actually have to create those. And a very easy way to create those is you can just run your test. And if you write your test correctly, which we did earlier, this should be able to create the correct candidates of smooth and crunchy for people to vote on. So let's go ahead and run that real quick. And the way that you would do that is anchor test, skip local test validator. Skip local validator. We'll allow it to deploy. That's fine to me. So it's going to deploy to our local test validator, and then it's going to run all of our tests. And these should set up our specific poll onto our local. So it looks like that they're not pulling. Oh, it's because it uses a different program ID than the one that we actually deployed. So we can go pull that right here. So you can see it's not ELY, it's actually 6RM. So we just have to replace that, and that's fine. So let's do that again. Anchor deploy. And then we'll run the test suite. And we can see, let's see what would fail this time. Declare program ID mismatch. So this is saying that something did not match correctly to where the program that was provided did not equal. So the reason why this vote for crunchy and vote for smooth button does not work is because we never set up our poll ID or our poll and candidates early on. If you remember correctly, we were using Solana Bank Run in the previous project to do a bunch of tests. We then, early on in this project, when we started, we deployed our smart contract onto our local test validator, but we have yet to actually set up any of the configuration in order to create our votes. So let's go ahead and start doing that. So I'm going to do it via the test. We're going to change some things. I'm going to remove this code right here, and we're going to use the test to set up our configurations. So we have the vote program. This vote program is going to be equal to a new thing for our anchor, using our anchor workspace. So what we do here is we do it as anchor.workspace voting as program voting. So this creates our correct program. And the second thing is we're going to have to make sure that we're setting the provider correctly to run locally. So set provider. This is going to be a specific different provider because we're doing it locally. So this provider is going to be anchor.anchorprovider.env. All right, so now what we can do is, and sometimes if you don't do this, you'll have to do an anchor clean. This will clean up your workspace, make sure everything is set up for success. I'm going to go ahead and do that as well. And then we have to run it to where it's building the program, deploying it, running the test, and creating our configuration. So let's go ahead and do that. So once that completes, you should have a bunch of test paths. And the test, you can see that, hey, we have all these crunchy and smooth peanut butter set up. And you can see here that there is all the program ran their instructions correctly. If you do run into error, make sure this public key is equal to the deployed program. You can always check what program and public key that you are set up. But make sure it is always equal, otherwise you're going to run into issues. So let's go ahead and test our blink real quick. All right, so let us vote for smooth. It'll pull up here, and it will send the transaction over to our account. Let's go over to our program account, and we should be able to see, if we did everything correctly, a new transaction that at the very end, it's voted for candidate smooth. Currently, I have 3 votes on my local one for smooth, and everything was created successfully. So that is how you use blinks and actions, a very quick tutorial of how you create blinks and actions with a application on chain. So we did, to recap what we did, is we took over our voting app from the last project. We extracted a lot of the code of how to interact with the program. We created a server-side component via Next.js to serve the actions and allow people to get these serialized transactions. And then, finally, we were able to view the blink via Dialect's blink tester website and interact with it to test everything out. Everything seemed to work correctly. We were able to vote for our different peanut butters based off of what we liked, and it was all done via this blink. Now, if you wanted to take this to production, the specific blink, you would have to go through the registry and register it. And also, I'd recommend deploying this to an actual environment, maybe DevNet or even mainnet. And that way, other people can interact with it via whatever social network they please. But yeah, that's everything for this project, and we will see you in the next project.
Our next project will be a CRUD decentralized application. CRUD stands for Create, Read, Update, and Delete, which are the 4 basic operations of persistent storage. This is foundational and will help you understand data handling, smart contracts, front-end integration, and blockchain transactions. These skills are not only essential for blockchain development, but also highly adaptable to various real-world applications. These skills can be transferred to any sector needing decentralized solutions, like finance, healthcare, and more. Understanding CRUD operations on Solana allows for innovation, as you can modify or extend your application with more complex features in the future. So let's get started. Okay, so we're going to get started with using the npx create Solana dapp command because we're going to be creating a backend connected to a frontend. And this scaffold has your anchor program with a basic counter program, and it's already connected to a frontend for you using Next.js and Tailwind. So let's start that. We'll type into our terminal npx create Solana dapp, and you'll be prompted to enter your project name. So we'll just name this CRUD app. Oh, already exists. I've done this before. So we'll name it CRUD app 2. So we'll select a preset, Next.js, and we're going to use Tailwind for our UI library. And then here you can select an anchor template. So we'll do the anchor counter program with tests. And now it's going to be creating the workspace for you. This is going to take just a second to load, so we'll just wait for it to load. Okay, so now you can see that your scaffold is loaded, and you can actually see there's a command here that says found anchor version 30.1, please upgrade. So this scaffold currently is set to anchor 30.0, so we just want to make sure that we're on the latest version of anchor. So let's open up the scaffold. And here is your anchor folder, and the anchor folder is going to have all of your backend smart contract code. And for the front end, you'll have the web folder. So we'll touch the web folder later on. We're going to focus on anchor right now. As we just talked about, we need to update our anchor version. So we'll go into the cargo toml and update to the latest anchor. So here you see anchor lang is set to 30.0. We'll just update that to 30.1. And now looking through the anchor directory, if you go into programs, counter, source, lib.rs, that is where your smart contract lives. And what we're going to do is just update the counter to our CRUD app. So we're going to rename this to be a CRUD app. And then in the librs, with this preset, you have a working counter. So you have close, decrement, increment, initialize, and set instructions. Since we're updating this to a CRUD app, we don't need it. So we're just gonna delete all of our instructions here and just have the basic layout for a smart contract using Anchor. And if you see all of these data structures underneath, they're all related to the counter program, so we can delete that as well. And now we have a basic layout. We're using anchor lang from our crate. And then this declare ID has a generated public key. This public key is going to be the program ID of the anchor program that you deploy on chain. So this will always be your program ID. When you run anchor build, it's going to update accordingly. Inside the program macro is where all of your instructions are going to live. So that's where we'll write the CRUD app instructions. But first, anytime I write a smart contract, I always want to start with the program state. And the state is where you're going to hold all of your data. So as you know, smart contracts on Solana are stateless. So all of the state is stored inside program accounts. So we're going to create an account for the CRUD app and define all of the data that we want to store. To do that, you can use the account macro with Anchor. So we're going to specify an account here. And then we're going to define the data structure. So I want this to be my journal entry state. Okay. Now, we're doing a journal here just because that's a very basic example of a CRUD app. In a journal, you want to create journal entries, you want to be able to update them if you need to, and be able to delete them if you need to. So we're just using a journal as our example. And let's see, what do we want to save to the state of a journal? We want to know the owner of the journal, so we can save that. And an owner is going to be of a type pub key because it's connected to your wallet address. When you're writing a journal, usually title it and you have a message. So let's save those as well. And these will be of type string. Okay. Now, when you're creating a account on chain and you have storage, you have to pay to hold that storage on chain based on how much space it takes up. So the rent is directly correlated to the space on chain. So we have to calculate how much space our state data structure is going to take up on chain. You could do this manually. Each type has a different number for how much space it takes up on chain, but Anchor actually does this for you. So we can use the derive init space macro to be able to calculate how much space is on chain. And you can see when we do this, we generate 2 errors, and the errors are for the string types. This is because strings can be infinitely long. So that's a little hard to calculate space there. So we need to set a max length for each string value. So for the title, that can be a little smaller. I'm going to set the max length of 50. Okay. And then you can see the error goes away. And I'll set a max length for message as well. And we'll say 1,000. Maybe you want a really long message. Okay, and now that error went away. So this is our state. Our state's defined. This is everything that we'll need to store for a journal entry, and it's going to live inside our journal entry account. We need to create this account. We need an instruction to initialize a journal entry account. So that's what we're going to do next. That will be our first instruction handler. We're going to do a pub fn create journal entry. Whenever you're writing an instruction for Anchor, the very first parameter that needs to pass through the instruction is going to be your context. The context macro is used to define a struct that encapsulates all the accounts that'll be passed through a given instruction handler. So we're going to write a custom struct for this instruction. So we'll write the context, and then we'll name the struct create entry. Just setting up the instruction here, we'll write the logic after we define our struct for this context. So we can go back down here and define that. Now that we have the instruction, we're going to define the struct for create entry. So pub struct create entry. When you're defining your context data structure, you need to define all of the accounts that are going to be passed through the given instruction that you're writing. So the first account that we're going to need is the journal entry account, and that is for the state that we just defined earlier. So to do that, you can use the anchor account macro, and then we're going to add some constraints on the account for how we want to handle this account throughout the instruction. So the first thing we want to do is we want to initialize the account. We're initializing the account because it doesn't exist yet. So we'll use the init constraint. And then we want to have a PDA on this account. So we're going to define the seeds for this PDA. So there's about infinite ways that you could define a PDA. Here, I think that the best way for us to do it is specifying the owner and then another parameter. And that's because we want to know who each journal entry belongs to. So having the owner connected to the PDA is a really easy way to derive that. If we just had the owner wouldn't be able to create more than one entry on chain. We need to add another parameter to allow them to create more than one entry. So we can do this by adding the title. So if we add the title, the owner can go in and create multiple entries based on the title. We're just going to add that for our seeds. We'll do title as bytes. And then we'll add in the owner's key. As ref. And now our seeds are defined. Anytime you define a seed, you always have to add the bump, so we'll add that here. And now, since we're initializing an account, we have to be able to calculate the space that it's going to take up on chain. This is needed so we know how much rent that we have to pay. So we're going to define the space. And whenever you're calculating space, you always start with 8. 8 is the anchor discriminator. So we'll add 8. And then for the rest of the values in the given journal entry struct, we can just calculate that by using init space, since we use the derive init space macro here. So we'll do journal entry state, init space. Okay. And now, lastly, we just need to define who's going to pay the rent. So we need a payer. And we'll make the payer the owner of the journal entry. And then all that's left here is to name this account. So we'll make this a journal entry of account, and it's going to be using the journal entry state. Now that we define that the payer is owner, we haven't specified who the owner is yet. So we're going to do that next as the next account in our create entry struct. So we're going to once again use the account macro from anchor. And we're going to specify who the owner is. So in our case, we want the owner to be the person who's signing the instruction. So it's just going to be the signer. Now, if you look at how our accounts are set up, we have the owner being the payer when we're initializing the journal entry. Because the owner is going to be paying, it's going to be changing the state of the owner's account. When that happens, we have to define that the account's mutable. So we're going to add the mute constraint here on the account. And this is just because in Rust, all variables are immutable by default. So whenever we want something to be mutable, we have to specify it. And then lastly, we just have to define the system program. So system program, and we're good to go. So now you can see we have one error showing up on the account, and that's for title. Now, why is that happening? It's because we haven't specified what the title is yet. And we don't know what the title is going to be. So the title has to be a user input parameter. So we're going to go back up to the instruction, and we're going to add a parameter for title. And that'll be of type string. Okay. And now this is being passed through the instruction, but it's not being passed to this create entry struct. So to be able to get this data down here, we're going to have to specify that you're pulling the title from the instruction. And we can do that by using the instruction macro. So instruction, and we're passing through the title that's coming through from the instruction user input parameter. So now we're good to go for everything needed for our context data structure for the create journal entry instruction. Now we can go in and start writing our logic. So if we look at the instruction, we're passing through the context, always the first parameter. We're passing through a title, which is a user input value. And then there's one more thing that the user is going to be inputting on the front end, and that's going to be the message for their journal. So we're going to add that as another parameter. And that's everything we need there. So all that's left is just defining the logic for the instruction. And what are we doing when we're creating a journal entry? We're just saving information back to the account state. So that's all we have to do here. To do that, we're going to load in the journal entry account. So we'll let the journal entry equal. And we're making this account mutable because we're going to be changing information in the account. So mutable, and we can load that in through the context. So we'll do context.accounts, and the account that we want here is the journal entry. So you can see here, this is the journal entry account that we're loading in through our context. And Copilot knew what we were doing and just finished everything. So we'll talk through what Copilot just did here. We have our journal entry. And then all you're doing is updating the fields on the journal entry. So the journal entry owner, we're referencing the owner's key. And the owner, as we've defined here, is the signer of the instruction. We have the title and the message, which are both user input parameters of the instruction. And that's everything we need to save. So our very first create instruction is completed. So we can move on to the next. So a CRUD app. Create, read, update, delete. Read is just querying the blockchain. So we're going to move on to update. And we're going to do an update journal entry. Okay, so as you can see here, Copilot is really great and already knows what needs to be done for this instruction. So I just tabbed over through the Copilot suggestion, but we have the update journal entry. The very first parameter that's being passed through is the context. Now we need to define what this data structure is for the context. So let's go down here and do the same thing we did earlier, but now we're going to be doing it for update entry. So derive accounts macro, and then we're going to do, oops. Update entry. Okay. Here, with the data structure, you want to define all of the accounts that are correlated to the instruction that you want to have the data structure for. So we need to pass through the first account. That account is going to be the journal entry account. So let's define that here. And we'll use the account macro. And we'll add some constraints to it. So here the constraints are going to be a little different. It's already been initialized, so we don't need the init constraint, but we're going to be changing the state. So we need it to be mutable. So we'll define mute as a constraint. And then you always have to add in the seeds so it's able to derive the correct PDA of the account. So we'll do the seeds and the bump. And here the seeds should be the same as above, title and the owner's public key. And now there's one more thing that we have to do. As we talked about earlier, the rent for storage on chain is calculated based on how much space it takes up. So if we're changing the length of the title or the length of the message, it's going to change the amount of rent that a user needs to pay for space. So let's say we had a message that was only 10 characters long, and I want to go in and make it 100 characters long. I now have to pay more rent. And vice versa. Let's say I deleted 100 characters. Now I'm paying less rent and I want to get those extra land ports returned back to my account. So to do that, we're going to use the realloc constraint. And this is just reallocating space for a specific account on chain. So we're going to calculate the space here. So we'll do realloc equals and have the new space calculated. So 8 is the discriminator. And then we'll do the journal entry init space. And then whenever we're doing this, we still need to specify who is going to either receive the extra land ports that are being returned or pay more land ports that need to be given for more space. So we'll do realloc payer. And that payer is once again going to be the owner. And there's one more thing. So we can do realloc 0. And what this is doing is just setting the original calculation of space back to 0 and then recalculating everything. So we'll set realloc 0 to true. And then lastly, we're just going to define what this account is. So it's our journal entry account. Okay. Now, if you remember from before, this data structure doesn't know what title is. So we're going to have to do the same instruction title. So we'll pull that macro in. And then we're going to add that as a parameter here for updating journal. So title is also going to be a user input parameter for the instruction. So now we specified the owner, but we need to pass that account through as well. So we'll add that in. Same thing as we did earlier. So it needs to be mutable because it's going to be paying. And it'll be the owner, and the owner is the signer. And then the very last thing we have to pass through is the system program. And now our data structure for our update entry context is completed. So we can pass that through here for our update journal entry instruction. If you look at the instruction, we have this little warning under title. And that's happening because title isn't actually being used in the logic of this function. This is just a little Rust thing. We're going to just add an underscore here to say, hey, I know that this parameter isn't being used in the logic, but I need to use it somewhere else. So I still need to take it in. Everything here is done. We have our update journal entry. We're passing through both the title and the message. We're updating the message in our journal entry state. And we're passing through all of the corresponding accounts in our update entry data structure for our context. Creating the journal is done. Updating the journal is done. So all we have left is to delete a journal entry. So we can go in here and we're going to write out our instruction for deleting. Okay. So this time, Copilot has been doing pretty well, but this time it's not correct. So we're going to delete what it suggested here and just have this instruction returning an OK value. And that's going to happen because all of the logic for deleting an account on chain is going to take place inside the delete entry data structure for the context. That's because all it's doing is handling accounts. And all of the account handling takes place inside the data structure. We'll go down here and make another struct for deleting an entry. Okay. First account we're loading in, just like before, is our journal entry account. So we'll do the account macro. We're changing the account state so it's mutable. We need to specify the seeds and the bump so it's able to derive the correct PDA. So seeds, the same as earlier, bump. And then there's one last constraint we're going to add, and we're going to add a close constraint. So what close does is if you run this instruction, it's going to close the account. But it's only going to close the account if the public key that I specify the close to be equal to is the signer of the instruction. So I want the person that can close this to only be the owner of the account. So close equals owner. And we'll do define the journal entry. And then we're going to specify who the owner is, which is the signer. Okay. And then lastly, we pass through our system program. And then one last thing to pass through is the title, just like we did earlier. So we'll pull this macro down here and then make sure title is passed through, which it is. And look at that. Our program's done. So if you go here, you can see the create, update, and delete entries are completed in our program instructions. And you can see this little warning here for context, and that's coming up just like earlier with title. It's because context isn't being used in the logic. So we're just going to add an underscore here and say, hey, I know that, but I'm using it somewhere else. And then we have all of our context data structures for create, update, and delete. And then we have our state. And that's everything we need for our CRUD app. So we'll go in and we're going to build the program. So if I cd into my Anchor directory, I can just run Anchor build. Make sure everything builds correctly and compiles. Okay, so now you can see our program compiled, everything finished, and we didn't have any issues. If something goes wrong within your program, the Anchor compiler will be able to pick it up, give you a warning, show you how to fix it most of the time. But we have everything correctly done and built. Now that that's built, what happens is it builds and sends an IDL to your target folder here. So you can see that this is my new IDL. And this is named a counter still because I did not update the name in the cargo toml. So we're just going to go in there and update it to CRUD app. So we're just rebuilding with the name CRUD, just so we can have everything named the same throughout the application. Okay. Now we're good to go. So once we build the program, we're able to now deploy it on chain. Throughout this bootcamp, we're going to be using everything local. So I'm going to open up my terminal and run a local validator so we can deploy to our local host. So here's my terminal. And to get your local validator running, you're just going to run Solana test validator. And we're now initializing an instance of the local host. And you can see that the validator is running on my local host right there. So now that this is running, I can go in to my terminal within the CRUD app directory and do anchor deploy. And I'm going to specify that I want it on local. So we're going to do provider.cluster local host. Okay, it's actually local net for anchor. So if you're using the Solana CLI, it's local host. If you're using Anchor, it's local net. That's one fun fact to remember there. So you can see it's deployed. We have our program ID here. One thing to always double check is to make sure all of your program ID keys are synced throughout the workspace. So now that it's deployed, we're just going to run anchor key sync. And you can see all program ID declarations are synced. Now that it's deployed, we're able to connect this program to a front end. So let's go into, we can close out the anchor folders and we're going to go into the web folders. So in our web folder, in the npx create Solana DApp scaffold, we have app, we have components, and we're going to be working between those two folders. So first, we're going to go into components and we're going to go to counter. And we'll go to data access. So we're just going to make some updates here. This was previously created for the Anchor counter program that comes with the scaffold. So this is just updating. It's fetching all of the information from the state. So we're changing the state from counter to journal entry. And we're going to do that everywhere. You can see that we have instructions from the counter, like close and increment and decrement. All of those can be deleted, and we're going to rewrite them for the instructions for the CRUD app. So we'll go in here, the close mutation can go away. The decrement mutation can go away. And you can see that it's returning an error because it's not finding these instructions in the corresponding IDO. So TypeScript knows that something has changed, and we just have to update those changes. Okay. There you go. Now we can just go in here and we're going to do our create entry. And we're going to use a mutation. And now we're going to be collecting information from the front end that's a user input value. So we're going to need to specify what's being collected. We're going to need to make this an async await so it's able to take everything from the front end and then pass it through. So we'll do we'll set up our create entry args, and that's going to have to be an interface that we're going to define outside of this. We'll do an interface for create entry args. And that is going to be the title that we need to pass through, which is a string type. The message, which is also a string. Then the owner, which is a public key. This initialize can also go away. Everything that's related to the counter can just be erased. Okay. So since creating the entry is part of the overall journal program and you're initializing a new account, we're actually going to have that in the use program. So we can go in here and do const create entry. We're going to use the mutation with the create entry args. We'll need to specify the mutation key. Oops. This is just a journal entry. And then we have create and we have the cluster. And then we'll define the function. And this is going to be an async function. And what we're grabbing from the front end is going to be the title, the message, and the owner. And now all we're going to do is return the program method for creating a journal. We can delete this return that happened earlier. Create journal entry. And then RPC to send the transaction. Okay. So that's what we're doing. We have the program methods. We're calling the create journal entry instruction, and we're passing through the title and the message from the user input parameters that we're grabbing from the front end. Now, since this is an async function, we just want to have an on success and an on error. So we'll add that in. Success. So if this is successful, it's just going to sign the transaction. And then refetch all of the accounts for the program. And then if there's an error, we'll add the logic in for that. And just make sure we return the error message. Okay, so that's everything we need for create entry, and then we just need to return that. So we're returning our program, our get program accounts, and our create entry. So everything's set up to be able to use the program. Now we want to go into using a specific account. So what this use program is doing is just initializing a new account. If you want to update an account that already exists, we need to derive it from the PDA and then be able to go in and update it. So that's going to be this second function here, which is using an account. So we'll update that. We're able to query specific accounts. And now we want to be able to update an entry. So once again, we're taking the user input from the front end and adding in the create entry args that we specified earlier. And we'll need, let's see what Copilot did. So we have the mutation key for the journal entry. We're specifying that it's update and we're using the cluster. Now we need to specify the function. It's an async function. We're taking in the title and the message and the owner from the front end. And then here we're doing update entry. And actually, in this case, we don't need the owner, so we can delete that. And we're just taking in the title and the message. And then we want to have an on success and an error case, and that's defined here. If it's successful, it's going to sign the transaction. If it's not, it's going to return the error. And looks like that's good to go. Okay. And then last, we just want to do the delete entry. So we'll add another constant in here for delete entry. Okay, let's see what Copilot did. We have the mutation key, we have journal, delete, and the cluster. It's an async. However, yeah, we don't need to take anything in from the front end. We're going to take the program. This should be program methods, not RPC. Copilot was close. Delete journal entry. And we're going to need to take in the title from the front end, and the title is needed to be able to derive the PDA. So we'll take that in. Okay. So we have our function of the delete entry. It's taking in the title as a parameter. That's part of our async function here. Actually, there's a way we can do this without making it an async. If the card already exists on the front end, it will have what the title is. So it can just pull that without needing to be a user input value. So we can remove the need for an async here and just have the title. So the title will be already on the front end. You'll have it on the card. And when you click delete, it'll know which journal entry it's corresponding to. So we have the title, the program methods, delete entry, passing through the title here. And then there we go. So we have our signature. On success, it's going to be a transaction. And accounts refresh, we don't need an error. And we actually don't need this. This is what Copilot generated. But since we're only passing through the title, we don't need the create entry args. So yeah, we're good to go there. Now all we need to do is return these constants. And now everything's updated on the front end. So in the front end, we have things separated by accessing data through our smart contracts. All of the data access is completed. Now we just want to update that data on the UI side. We'll go into the UI file and we're going to update all of the information here. So let's see, we still need our key pair connected. We won't need the memo. We can get rid of that. Okay. So we're going to change a few things here. So this first counter card, it's actually going to be for creating a journal. So we're going to want to have the user input fields here. This is where we're actually going to grab the data from the front end. So we're going to want to have our title and a way to set the title. And we'll import useState from React. And we'll do the same thing for message. And then we're going to want to use our create entry instruction that we just created from the data access file. So we'll pull that in. And then we also want to be able to use a public key. So and this we're going to use from use wallet. And this is coming from the wallet adapter library. We have our front end. We need to have the title and the message be a user input. So we want to make sure that these values are actually input correctly from the user. So we're just going to have a check here. So we're going to do is form valid. And that's going to make sure that the title exists. And the message exists. And then we want to be able to handle the submit of the information on the front end. So we'll make a function for that. So if there's a public key connected on the front end and the form is valid, then we're going to be able to execute the create entry logic. Okay. And that's all we need there to handle the submit. So we need to do one more error handling, and that's going to be if there isn't a public key connected, we need to return that the user needs to connect their wallet. So we'll do an if there's no public key, we will return connect your wallet. Okay. Great. So now all we're doing is just handling the UI side of things. So when we return, we can delete everything that came with the counter because we are not going to need that. Okay. So when we return, we want to have an input for text. We want to have a text area for the message. And then we want to have a button for someone to submit. So we'll do a div have an input, and that input is going to be of a text type. Oh, there we go. So Copilot has it. We need the text type, we need the placeholder is going to be the title, the value is going to be title, and on change it's going to set the title by using the useDate from React. So that's good for the input, and I'm just going to add in the class name actually, just so it sticks with the styling for the rest of this. We have our input bordered. I want it full, and I also want max width extra small. There we go. Okay, so input is done. Now we need a text area input as well. So we'll do text area. And then Copilot has it. We have placeholder message. The value that the user is going to input is the message. On change, it's going to set the message in the state. And then we have our class name. So we have a text area bordered. And then I also still want to add in the max. There we go. So text area is done. And then lastly, we need a button. So we have our button, and let's see. On click, we want to handle submit. We want to have it disabled if the form is not valid. And we also want to add in if create entry is pending. Oops. So is pending or is form valid, it'll be disabled. We have the class name is going to be a button. I don't want it to be a primary button here, so let's change that. So we'll do a small button. There we go. Okay. And then we just need to close our div, and then this section is good to go. So okay. So this is done. So what this is doing here is the card to be able to create new journal entries. Now we just need our last UI update, which is going to be the card of a specific journal entry and how to update a specific journal entry. So that's our create. Now we'll go to the list. So in the card, you can see it has all of the counter information from before. So we're going to delete that. And we'll delete the memo because we don't need it. Actually, we'll delete all of this. Just get rid of it. Okay. Great. So in the card, we're passing through the account query. We're going to pass through update entry and delete entry. And that's going to be from the program account. And it's going to be passing through the account. And now we're going to have the public key. So we'll do the use wallet just like we did earlier. This is public key. There we go. Okay, and now just like we did earlier, we need to set the message because a user is going to be able to go in and update a message. So they need to have that space to update it, and we need to be collecting it on the state. So const message and set message. And we'll do use state. Okay. This was the optimization we talked about in the contract. It doesn't need to be a user input value. We're actually just querying it from the account, and the title cannot be updated. It's just there because it's part of the PDA for an account. So we'll just add in title, and that's going to be an account query. Okay. And I spelled const wrong, so we'll fix that. Great. So we have our public key, our message, our title. And then we'll do the same is form valid check. So we'll just copy that over. We don't need to retype it. But actually here we're not having a title. So we'll just update this to only be for message. Okay. And then we also need the handle submit. So we can copy that as well. Just some less typing. And we'll need the public key, so while we're up here, we'll copy that as well. So here we go. Handle submit, public key. And now, let's delete this. Everything related to the counter, we're just deleting. Now we can do our return. And this is going to be an account query. And it's just going to load all of the accounts associated with the program. This is just going to be a lot of UI work. So we're going to span class name loading. There we go. And then else we're going to return the card. So let's actually see what Copilot did. So we have the class name card. We're going to just make this a little fancier. So let's make it a bordered card. Bordered base, let's do like 300. And then spelling things wrong. Okay. So class is done. And now we're going to do the card body. We'll just center things here. Okay. We'll do this a little differently. Okay. So we're going to do the class name. We'll just add a space in here. Okay. And now we have our header. We have a card title. We'll center the card title. Okay. And now we're also just going to want to add in a refresh here. So on click, it's going to refetch all of the account queries. So on click, we're going to do accounts query, refetch. There you go. And if you're following along and see things auto completing here, it's just Copilot. I'm going to change what Copilot did a little here. So this is actually going to be an account query for the title. Okay. clean up some code a little bit. So we have our title here for the card. And now we have the title. We're going to want to add in the message. So we'll just add that underneath. So let's delete this Copilot recommendation and just add in the message. And this will be an account query as well. Okay. Great. So that's done. Now just visualizing the card, we have the title at the top of the card, we have the message displaying. Now, since we want to be able to update a journal entry, we want to have some space for a user to type in their updated message and a button to click that. So we're going to add that in. It looks like Copilot did a pretty good job here. So let's just go over. We have our card actions. We'll just add a justify here. Just clean up the UI a little bit. And then we have our text. We'll change this to a text area. Text area is going to have a placeholder for message. It's going to have the message value. On change, it'll set the message. And then we'll do a class name. And there we go. So there's our text area. And then we have the button to handle submit for the updating an entry. And that's going to be labeled update. We can just specify a little more, update journal entry. Okay. And then we have delete entry. So this will be a delete button, and we can just do an account query here for the title. There we go. And now since title could be undefined, we're just going to add in a little check here for error handling. So we'll do this, and we're going to do if So we'll just change this a tiny bit. Okay. So we'll do a const. There you go. So if it exists, then it'll actually execute the instruction. Okay. Clean that up a little bit. So now we'll clean up our imports that we don't need. Okay, and then we need to find the name for query entry because it looks like we didn't name it that. So let's go back and see we have update, delete. We have create entry, so let's just make sure it was imported. Okay, so this should actually be update entry. There we go. And then we're gonna have to do the same thing from earlier because title could be undefined. So we're just going to add in a check there. So if title exists, then we'll actually do this. So, and title. There we go. And it looks like this is good to go. So one more check, we're gonna check in on the feature. We just need to make sure we're returning program ID, which we're not. So we'll add program ID in here. And we're good to go. So let's try to build this. So we're going to navigate into our web app. And we'll run npm run dev and see what we've got going on here. So let's open up a browser And we'll go to our local host. And you can see our web app is now running on our local host, port 3000. And here's our app. So this is what the front end looks like when you're using npx create Solana DApp. You have this basic UI. You have the accounts. This shows you your connected wallet account. So this is my DevNet wallet. You have your clusters. Right now I'm connected to DevNet, but I built and deployed my program on LocalNet, so I'm going to change that connection over to local. Okay, and we're just going to request an airdrop, make sure I have funds on local. Then we can click over to our program. And you can see here, program not found. So we're going to go back here and just make sure we have everything correctly updated. So we'll open a new terminal. We'll cd into Anchor. We'll do Anchor build. And then Anchor key sync, make sure all of the program IDs are connected across the workspace. So, and then we'll just do Anchor deploy, specify the provider cluster to be localhost. So it deploys to local. Local net for Anchor. Localhost is Solana CLI. Okay, so here's our program ID. Let's just refresh this. Okay, so you can see here the program IDs don't match up. So that means something in our data access is pulling an incorrect program ID. So it's probably coming from the counter. So we're going to go back over here to our use counter program, and where is it finding the program ID? So get ID, cluster, devnet, public key. So this public key needs to match the public key in our Anchor program. So we'll go back to our Anchor program and just make sure it's connected. So see how they're different? That's where we're going to update. So in the npx create Solana DApp, the one part that doesn't update with Anchor key sync is right here. So you go to your counter exports and you just want to update, you want to update the public key to the new public key. Okay. So now let's see if this updated. We're going to close out this instance and just rerun our we'll cd back to our web. And then we'll run npm run dev. Okay, so now we're on our local host. We'll go here. I'm going to refresh. Okay. So we're just going to find where it's generating this account. So I'm going to copy this over and Command-Shift-F. And search this. Okay, so here it is. This is what we also need to update. So here you have these TypeScripts, and it has an address that is our old public key. So we'll go in here, take in the public key that we want, that we actually deployed, and I'm going to go into, let's see, how do we do this? We will just paste this here so I have it. We'll go back here, copy this, Command-Shift-F. We're going to paste one we don't want. We'll click in here, and then we'll paste this one in. Okay. Make sure all of this goes away. Save. Okay. Now we'll go back over here, refresh, and here we go. We have our updated public key. So this is our account. Now we're just going to create a message. So I'm going to do bootcamp. And I'll make the entry learning Anchor. And we'll just submit that. It's going to pop up your wallet to sign the transaction. So I'll confirm, and there you go. So there's my entry. It's titled Bootcamp. My message is Learning Anchor. Now I have the option to either update a journal entry or delete. You can see the update is disabled because I don't have the correct information in the message. So once I start putting something in that field, it'll pop up. So let's update it to I learned Anchor because now I know what I'm doing. And now you can see the button shows up. So I have the ability to update, my wallet comes up, sign the transaction, we'll refresh, and now we have a new message, I learned Anchor. And now last thing, delete. So if I don't want this anymore, I'm gonna delete it. Now it's gone. So that's everything. We created, we updated, we deleted, and we're able to read on the UI. So we have our fully working CRUD app. We have it connected to the front end, and we're able to play around with the UI and test everything. So we did it. Good job, guys.
Let's talk about tokens and also make our own token. So far, the only token we've discussed is Sol, which we use to pay transaction fees when making our favorites and voting contracts. Sol is the native token of Solana, which means it's built into Solana itself. But if you use blockchain in the real world, you've probably used many tokens other than Sol. On Solana, these are called SPL tokens. If you're wondering about the name, SPL is the Solana program library, a bunch of smart contracts which include the program you use to create and transfer tokens. For the rest of the course, we'll just refer to SPL tokens as tokens. Tokens are used to represent everything apart from Sol. There are tokens for stablecoins like USDC, NFTs, and real-world assets like equities, metals, commodities, dog tokens, and nearly anything else. Tokens are produced by token mints. Token mints are factories that make a particular token. The factory is run by a person called the Mint Authority. The Mint Authority must sign all the transactions that mint new tokens. Each distinct token on Solana has its own mint. For example, when I purchased my beer earlier, I paid with USDC, a popular stablecoin, a token whose value is tied to a fiat currency like USD. USDC is made by a company called Circle, and they have the token mint address published on their website. The company Circle is the mint authority for USDC. When we create our own mint with the token program, we'll set ourselves as the mint authority. The Mint Authority can mint, i.e. create, new SPL tokens into any address, including their own. When an account receives the tokens, it will need somewhere to store these tokens, since regular accounts only store Sol. So we'll create an associated token account to store that. An associated token account is just a PDA with the seeds made from the wallet address and the token mint address. For example, I can always find Alice's USDC token account by looking up the PDA based on her wallet address and the USDC mint. And I can always find Bob's USDC token account by looking up the PDA based on his wallet address and the USDC mint. And I can always find Alice's dog token account by looking up the PDA based on her wallet address and the dog token mint. You get the idea. Let's make a token.
So let's make a token. We'll be using the command line tools here, but the concepts are exactly the same as if you were using the JavaScript or TypeScript tools. We'll also be using the new token program called Token Extensions that features a bunch of useful features that we can add to our tokens. One of those is the metadata feature, which allows us to have our metadata, all the things you see about the token, like a name and a description, directly inside the token mint. And if you don't know what that means, that's fine. All it means is that we'll be taking less time because we have less things to work on. So let's open a command line. Let's see that we have Solana command line installed. Great. Let's make a new directory called new token. And let's change into that directory. We are now in a big old empty directory. And the first thing we're going to need to make is what's called a mint authority. If you think of a token mint, like the actual physical mint that prints tokens, you can think of the mint authority as being the boss of that mint. They're the person that needs to sign all the transactions to mint new tokens. If you're not the mint authority, you can't mint tokens for a given mint. So let's make that. We're going to make a key pair for our mint authority. And we're going to run the command Solana key gen grind. And we're going to say -- starts with. And we'll say BOS, BOS, and then 1. And I'm not a good typist, especially when I'm recording. Solana keygen grind starts with boss1, and if you give it a moment, it will go and make a key pair file. So there we go. Our file is called boss something.json, whatever the public key is that matches the private key inside. So we now have our boss something or other.json file. Let's make Solana use that key pair to sign all our transactions. So we do Solana config set -- key pair BOS something.json, whatever your JSON file is called. And it'll respond immediately, and we can see that our key pair path has now changed to be whatever our BOS file is. At the same time, we should also make sure that the Solana command line tools are using devnet, because that's where we're going to make our token. That is Solana config set -- URL devnet. And you can see in the response that the settings are now updated to use Solana devnet. We can also double check that if we just do a Solana config get. At any time, we can always check what key pair file and what network we're connected to. So we've created our mint authority, but because this account's going to be writing to the blockchain, they need some SOL to make those accounts. So we have our boss something or other is the public key of our mint authority. Let's go to, say, faucet.solana.com, paste in that wallet address, and look, 1 SOL is fine, 0.5 SOL is fine, and we'll ask for that SOL on DevNet, and we can get some free DevNet SOL. Excellent. That says airdrop was successful, and if we do Solana balance, we can see that our balance is 0.5 SOL. So we've made our mint authority, which is going to be the boss of our token, the account that has the permission to create new tokens or mint new tokens. And we've given our mint authority a little bit of SOL to make new accounts. Great. The next thing to do is to actually make the token mint. So we're going to give our token mint a fancy address. It's just going to start with MNT, just so we can remember it's our mint. So we'll run Solana keygen, and we will say grind an address that starts with MNT, and we only need one of those addresses. Give it a moment, and it will create an address that starts with MNT something.json. So that address is where we're going to put our token mint. Let's put a token mint at that address. That is SPL token, create token, and we're going to specify the program ID of the token extensions program, which starts with token and then a Z and then all this other stuff. So I'll just paste that in. And we want to use the metadata extension because it makes our lives easier. Enable metadata. And we will say our address to use to make our new token. Great, that's done. So we've now made a new token on Solana. The address of our token is the same as the one we ground earlier. It has 9 decimals, which means that if you've ever transferred SOL before, you'll notice that to send 1 SOL, you send 1 billion LAM ports. It's the same with our new token. We've specified 9 decimal places, so you send 1 billion whole minor units to send 1 major unit. This is actually not even a blockchain thing. It's a financial programming thing. Whenever you send someone $2.50 in the real world, you probably actually send them 250 cents. And it's because computers don't handle decimal very well. They work in binary. So if we always send whole numbers of whatever the minor unit is, cents, LAM ports, your own token's minor unit, it makes it easier for the computers. So we've made our new mint. Let's go check it out in Solana Explorer. So I'm in Solana Explorer, and I will say devnet, thank you very much. And I will paste in our token mint address and check it out. It says unknown token. It says a token 22 mint, which is using token extensions. There haven't been any tokens minted yet. 9 decimals, as we just talked about. And there's not really that much here. There's no kind of metadata or anything yet. And it says unknown token. So let's fix that. Let's add some metadata. Now to do that, you're going to need to upload firstly an image and then a JSON file somewhere public on the internet. If we were making a token for mainnet, a real serious production token, we would probably want to use a decentralized storage service, somewhere like Arweave or Iris, that is basically kind of like a blockchain, but for JSON files and images and all that kind of stuff, rather than Solana is a blockchain for transactions like traditional blockchains. These decentralized storage services are designed to keep things online for a really long time because they're not owned by anybody, and they're resilient to attacks and all this kind of stuff. They're a good place to put something that you want to be around for a really long time. In our case, this is just a test token. So we're going to use GitHub, and we'll just be using those raw GitHub links. The important thing to realize here is that our link has to just open our image file or our JSON file directly. No HTML, no anything else around. Make sure that when you visit that link in your web browser, it just shows an image file or some JSON, depending on the image or the JSON. So upload the image first, add it to a metadata file that looks a little bit like this. You'll just have a name, a symbol, a description, and the image that you uploaded earlier. Take that metadata file and upload it to somewhere public as well. Make sure that you have a URL that loads your metadata file directly in your browser. For example, I have one right here. There we go. So I can now add that metadata to my token. So SPL token, and we're going to say initialize metadata, and we're going to specify our token. I'm just going to get it from the file name, our MNT file name. And we're going to specify a name for our token and a symbol like. And then finally, that URL to get to that JSON file. And then Solana will go and take that JSON file and put that data, directly inside the blockchain. You'll see everything has gone successfully. And if we go back to Solana Explorer at this point and reload our token, you'll see unknown token has been replaced by example, as we specified before. And now there's a whole bunch of metadata, our name, symbol, the URI with the image. That's all now showing on Solana Explorer. So great. We now have a token mint and it looks nice. So we can use this token mint to mint tokens. Let's mint some tokens, and as the mint authority, we can mint them into anyone's account, but let's mint some into our own account so that we can transfer them out to other people if we like. SPL token. We're going to need a token account in our personal mint authority account just to store these tokens. So create accounts for this mint. So we're just making a PDA or an associated token account to store just these tokens in our own personal account. Once we've done that, we can go and mint some new tokens. That's SPL token mint our token, which is MNT something or other. And how many tokens do we want? Let's say 100, maybe 1,000 tokens. So that's good. Done. Let's go and look at, firstly, our token mint and then our own personal account to see what's changed. So if we go back to Solana Explorer and look at the token mint again, you can see the current supply, which is the amount of tokens that have ever been minted, is 1,000. In fact, let's mint another 1,000. You can see Solana Explorer updates again, and you can see 2,000 tokens have been minted. Also, let's check our personal account as the mint authority, which we called, what was it, BOS something or other. There we go. And if we check in our own account, we can see that 0.5 SOL that we gave to ourselves earlier, minus a few transaction fees. But more importantly, if we check in tokens, we can see that we have 2,000 of these tokens, and the type of tokens is our token mint address that we made before. We can transfer these tokens, we can burn them, we can delegate them, we can do all the normal things we do with Solana tokens. So there you go. You now have your own token. I hope you enjoyed this, and I'll see you in the next chapter.
Now let's make an NFT. And here's the good news. You already know most of what you need to make an NFT. NFTs are just SPL tokens, exactly like we made in the previous lesson. Just like other tokens, they are minted from token mint accounts, stored in associated token accounts, and transferred with the token program. However, NFTs have a few characteristics that are distinct. Firstly, they're unique, i.e., each NFT only has one ever minted. Also, they can't be broken up. In other words, each NFT has 0 decimal places. Additionally, the metadata for an NFT contains links to another file, stored on a file storage service like Iris or IPFS. This off-chain metadata file has links to media files like images, videos, or 3D objects, any traits the NFT has, links to the project that made the NFT, and more. Authenticity is also handled differently with NFTs. With regular tokens like USDC, we know they're authentic because their mint address matches the official USDC mint address. Since each NFT has a unique mint address, we use the concept of collections to verify that each NFT is actually minted by the right project, and not a forgery some person created. Let's go make an NFT.
All right, so let's make an NFT. We're going to start by making a folder called new NFT. We will change into that, and we will run npm init-y to create a blank npm project, a package.json, and all those things. We're going to install a couple of packages as well. We want to install from the Metaplex Foundation a package called MPL token metadata, and also a package called, also from the Metaplex Foundation, UMI bundle defaults. UMI, by the way, is the Japanese word for sea. You'll notice a lot of things in Solana, like sea level, like anchor, have names based on seas or oceans. Cool, they're all installed. I'll just clear my screen. And let's go make a new file, and we will call it create collection.ts. So we have our create collection.ts here, and we're going to start, oddly enough, by making the collection. As I mentioned before, NFTs, unlike regular tokens, are unique. So whereas normal tokens have multiple tokens, many billions of tokens in some cases, or with a single mint address, each NFT has its own mint address. So there needs to be some way to bind all those NFTs together and also confirm that any new NFTs are actually produced by the owners of that collection. So that's why we have collections. So we'll start by making that collection, and we're going to import a few things. We'll take create NFT. Collections themselves, by the way, are also NFTs. Fetch digital asset, and what else? MPL token metadata. MPL is Metaplex. That's the company that maintains the Metaplex NFT tools. From at Metaplex Foundation, MPL token metadata. That looks good. It's just shown up as gray because we aren't using it yet. We're also going to import a few things from Solana helpers, and I should install the helpers as well. npm I at Solana developers helpers. So let's import a few things from that helpers file. That's airdrop if required. Get explorer link. Get key pair from file. From Solana developers helpers. That looks good. There's a few other things as well. We also want create UMI. Our UMI instance is just a way we can talk to Metaplex's tools. We can talk to other tools with UMI as well, but nearly all of the time, in fact, people just use it to talk to Metaplex tools. Metaplex Foundation, It is from Umi bundle defaults is the name of the package. There we go. We want a few things from Web3.js as well. That's actually already installed for us because it's a dependency of some of the other packages. We want connection, and we want LAN ports per URL from at Solana web3.js. Oh, and I haven't spelled connection properly. And LAN ports per URL, LAN ports per sol. I don't know why I thought LAN ports per URL. That looks good. Excellent. So we're going to create a connection. And we'll connect to whatever the URL for DevNet is. So cluster API URL for DevNet. And probably also want to import cluster API URL as well. Oh. And we'll also want to import cluster API URL from Solana Web 3. So we have our connection. We'll want a user. So get key pair from file. If we don't specify the file to use, it's just going to use the id.json that's in our home folder. So that sounds good. And let's give ourselves some sol if we don't have any. So go await, airdrop if required. Connection to whose public key? The user's public key. Oh, I just realized I forgot the await. There we go. Await get key pair from file user dot public key. And we want to get one Solana, so one lamperts per sol if our balance ever falls below 0.5 lamperts per sol. That looks good. Excellent. Let's also just console.log loaded user, and then we'll just say the user.public key. And probably want to say to base 58 so it prints out in the usual string of letters and numbers that we're used to seeing Solana public keys as. So let's make our Yumi instance. This is going to be, as I mentioned before, how we talk to Metaplex's tools. So const Yumi equals create Yumi. And we'll create our Yumi instance just using the same endpoint as our connection. So it's a Yumi connection to DevNet. We'll tell Yumi the programs we want to use, which in nearly all cases, as I mentioned before, Yumi is pretty much a Metaplex thing. So the programs you'll probably want to use are MPL token metadata. Sounds good. So MPL token metadata is actually a function. So we go yumi.use and then we run NPL token metadata. So we're going to make a Umi version of our user key pair. So Umi has its own format for key pairs. So we'll just call it Umi user equals Umi.eddsa dot create key pair from secret key. I'm going to just say user.secret key. So this is just a copy of user, but it's just in the format that Yumi uses for secret keys. Again, Metaplex has their own ways of doing things, so these might be a little bit different than the normal Web3.js ways that we've been using in previous lessons. So we've made our Yumi key pair, and we'll go yumi.use key pair identity, and then Yumi user. And I think we need to import key pair entity, and we need to import key pair identity so we can get that from Metaplex Foundation Umi, and that looks good. Excellent. Great. So we've console log say set up Umi instance for user. I always like adding console logs, just if we're making command line tools, it's nice to have a little bit of feedback. So we've loaded our user, we're connected to DevNet. We've given the user some DevNet Sol if they needed to. We've made a Umi instance so we can talk to Metaplex's tools, and we've set that Umi instance up to use our user as the default signer for any transactions. That's good. Let's go make the collection. So we're going to do const collection mint equals generate signer Umi. So it's going to make a key pair using Umi. And this is our transaction that is going to create our collection for us. Await create NFT. As I mentioned before, collections themselves are NFTs. They're just NFTs that point to other NFTs. You can even do fancy things like collections that point to collections. Go check out Metaplex's docs for that. And we'll say Umi and then the options for our collection. Mint will be the collection mint, which is just that key pair we made earlier. The name, let's call it, my collection. Symbol, MC. I don't normally like using symbols for connections, but Solana Explorer says no symbol if you don't have a symbol for your collection. So that's the only reason I like to do it. A URI. I'll talk about this in a second. URI, pardon me. Add that comma. What else? Seller fee basis points, which I will say is a percent amount. Of 0. Seller fee basis points are a way for artists to make money on secondary sales. So if an artist sells an artwork to somebody, then a couple of years later, particularly as that artwork has increased in value, that person transfers it to another person, then the original artist can make a royalty on each of those transactions. That's actually a really good idea. But these days, we actually have newer, better ways of handling this, because this basis points on NFTs used to just be enforced by marketplaces being nice. These days, we actually have things that are built into the protocol, like programmable NFTs and like transfer hooks that can be used to provide a mechanism for artists to get those royalties and enforce them, so people can't actually transfer that artwork without paying the original artists. Very cool, particularly for people who make money as artists for their living. And yeah, if you're interested in that, you should check out Token Extensions. There's a lot of really good things in there. Seller fee basis points and is collection, let's say true. Great. And it looks like we need to import percent amount. That's percent amount. Where do we get that? It's from, Metaplex Foundation Umi. Key pair. So just after key pair identity, let's add percent amount. There we go. And that all looks good. So after we've made our transaction, we can do await transaction dot send and confirm, and we'll use our Umi instance to connect out to Metaplex's tools on the Solana DevNet, and that looks good. So we've loaded our user, given them some Sol, connected to DevNet, created our Umi instances, and created our NFT to represent the collection. We're going to actually fetch the NFT that we've just made. So const created collection NFT equals await fetch digital asset Umi, and then we say collection mint dot public key. Yeah, fetch the NFT for the collection at that address. And then we are done. So console.log. Sometimes it feels like VS Code is heckling me when I type. And I will say, what will I say? Created collection. I will pick a nice emoji for a box because the box has the collection in it. And I like logging emojis. The address is, and then let's use Get Explorer link. And what do we want? We want a link for the address of our created collection NFT dot mint dot public key, and we want a link for DevNet, please. So that looks good. Let's just run through our script to go through it again. We have our connection to DevNet. We're loading our user from id.json. We're giving them some DevNet sol if we need to. We're creating an instance of Yumi, which we'll use to talk to various tools. And we're saying the specific tools we want to talk to are the MPL token metadata program. In other words, Metaplex. We're creating a Yumi version of our user and saying that Yumi should use that to sign all our transactions. Just making a key pair, then creating an NFT, which is going to make a mint using that address. And that NFT is a collection NFT. So you'll see, is collection true? That is our collection NFT. We're going to send that transaction and then refetch it from that address. We can run this, but first we need to talk about this URI. So that URI should be a JSON file that you've uploaded somewhere and that you can access directly via that URI. For this case, I've just used GitHub's raw URLs. So that's when you upload a file to GitHub, you can click on it and see the raw URL. What you want for that URI or URL, they basically mean the same thing, is that when you load that in your browser, you just see the JSON file. You shouldn't see any HTML or anything else around it. So if you look at my screen right now, it's just straight up JSON. All it has is a name, a description, and an image. Also with that image file, let me show you the same thing. When I load that image, the image just loads itself. No surrounding HTML, no anything else. You'll need both the JSON file and the image file mentioned inside the JSON file to be able to load up directly without anything else around it. Again, in GitHub, you can just use a raw URL, which is fine for our purposes. There's quite a few of these permanent online file storage services. You can pick the one that works for you, but the thing that makes them permanent is they're, like Solana, decentralized. So they can store your JSON file or your image online for a really long time. They're not reliant on any individual cloud provider. So when people buy your NFTs in production, they can know that the JSON and the image will be around online forever. So we've got our image and we've got our JSON file. And when we load either of those URLs, we just see the image or the JSON file. Let's take the address we've uploaded our JSON file to and paste it into our URI field for our collection. So that looks good. We probably also want to install ESRun because we're about to run it. So npm I ESRun. ESRun, if you haven't seen it before, is just a really easy way to run TypeScript on the command line. You don't have to set anything up beforehand, it just works. So now that we've installed ESRun, we can just run our TS file. That's npx ESRun create collection.ts. So we've loaded our user, we've set up an Yumi instance for that user, and you can tell it's thinking. It's going to go make our collection for us. Beautiful. So it's made our collection, and because we did that at Get Explorer link, it's even given us a beautiful link to click on. So we can see in Solana Explorer, make that a little bit bigger for you, that our collection has loaded. The symbol is MC. The master edition is a way of saying that this is a collection. And you can see a bunch of different information about this. There's only one of the collection. There'll only ever be one. And it has a bunch of other fields that are common to regular tokens. Things like a mint authority, like who's allowed to make these, a freeze authority, who's allowed to stop them being moved around, and an update authority, who's allowed to change this, which are all just public keys. The update authority you'll see is the public key that matches our ID.json file. And if you scroll down, you can see when this NFT was created in the history, you'll see 2 minutes ago that that transaction ran. So that was our transaction running through Yumi. Great. So we have our collection. Let's make an NFT that's a member of our collection. And then let's also verify as the collection owner that that NFT belongs to that collection. We're going to make another script here. And what should we call it? We'll call it just create nft.ts. And I'll save that. I'm going to just copy all the imports and probably the user and the airdrop and the UMI user, because we can reuse all of those. We might not use all the imports, but we can just delete the ones that we don't use. So in create NFT, we've pasted in everything from our previous script all the way up into we set up the UMI instance. The next thing we'll want to do is save the address for our collection, because we're about to use it to make the NFT that belongs to that collection. So let's do const collection address equals, we'll say new public key, public key. And we will get the address from our collection. I'm just going to use our Explorer. We could also get it from the command line. New public key, and that address. It's complaining about public key. That's just because it's unused, but that's okay. And we'll need to import public key from Solana Web3.js. We could also, if we wanted to, do it this way as well. Because UMI has its own format for public keys, we can also just go public key, which is actually a function that comes with UMI, and there we go. That also works. If we do the normal Web3.js method of doing new public key, then later on we'll have to convert it to the UMI public key anyway. So we may as well, which is actually done with the same function. So we may as well just use the function in the first place and just go collection address equals public key, the function, and then the address of our collection that we got from Solana Explorer. So we've got our public key. Let's go make our NFT. Console.log creating NFT. Oh, sorry. VS Code gave me a great suggestion, which I also don't care about. Creating NFT. The NFT has its own mint, as again, I mentioned each NFT has a unique mint address because they're unique. Generate Solana UMI. That's going to be just a new key pair that we make. And then let's actually make the transaction to create an NFT. So const transaction equals await create NFT. We'll say our UMI instance, and here's the options for our NFT. The mint will be the mint address we just made. The name of our NFT will be my NFT. The URI will be another off-chain data file. I'll just put ... in there for now. Seller fee basis points, same as earlier. We'll just say %amount 0. And we'll add some information about our collection. We'll say the key of our collection, the public key of our collection, is collection address. If we, actually, I'll tell you about that in a second, and we'll say verified false, just because when we first make this NFT, verified will be set to false. In a second, we're actually going to sign or verify that NFT being part of our collection. And that will change verified to be true for us. Then we'll do await transaction, send and confirm using our Yumi instance. So we've made a transaction to create our NFT. We've said that it's a member of the collection that we made a moment ago. And we've sent that transaction off to Umi to be processed and make everything for us on the blockchain. Let's go fetch the NFT we just made. So const created NFT equals await fetch digital asset. And using our Umi instance, we're going to fetch the asset that it's at, the NFT's unique mint address, mint.public key. And then let's make a pretty console log. So console log, and I'm going to add a little artwork emoji because that's cool. And we'll say created NFT address is, and then we'll do get Explorer link for address using created NFT .mint .public key, and we want a link for DevNet, please. That looks good. So that's our whole file. I'll just go and remove any of these imports that we're not using. We ended up not using public key from Web3.js. We ended up just using the public key from Metaplex Foundation Umi. It's a little bit weird, Umi having different formats for public keys from Web3.js, but hopefully that will be fixed in future. I think everybody's moving to the new web crypto style of public keys, so that will get better in future. So finally, before we run this script, I wanted to talk to you about that URI. So just as we saw with the collection, that URI needs to be a file, a JSON file stored online, and that when you open it in your browser, you just see the contents. So I'll open up another tab here and show you. For an NFT, it's just a name, a description. You can add a symbol if you want to. I don't feel like adding a symbol for this one. And an image. The image inside also needs to just load directly when you load it up in your browser. So it's this cool ball with energy bits. That looks nice. Same as before, if you're making NFTs that you are selling in production, use one of these like permanent online file storage services. That means that your JSON file and your image will be online forever. So I will paste in my uploaded, not the image file. I want the JSON file. There we go. And I will run our script. So just clear my screen. npx es run, and then create nft.ts. Let's make our NFT. So it's loaded our user, set up our Umi instance, and it's making our NFT for us. Give it a moment. Great, we've made our NFT. So if we click on that URL, I use a Mac, so it's command click to open up a URL. We can now see our NFT. It has the artwork, that is the artwork that we uploaded before. This actually, NFTs can have a bunch of different files. This just happens to be an image, but we could also use an MP4 video. We could use a 3D object like an FBX file or an OBJ. The name of our NFT is the name from the JSON file. We didn't set up a symbol, so it says no symbol was found. And yeah, it's a bunch of other normal token options, like there's a maximum of one of them, and there's only one of them supplied because NFTs, if you look at them as being regular tokens, are unique. Seller fee basis points is 0%, as we said earlier. And you can see that it was created a couple of minutes ago, 2 minutes ago, in fact. We didn't set up any attributes on our NFT. And if you look on metadata, you can see a bunch of things like where the JSON file is, which is where it got that image from. And you can see the creator is 0, the first creator is our address from id.json. And you can see the collection, which is the collection that ch file, that ch public key that matches our collection that we made a moment ago. You'll see that verified is 0. Let's verify that NFT as being part of that collection so that it turns that verified to 1. Also, art tools, particularly wallets or galleries or art marketplaces, really like it if you have verified set to 1. There used to be that people would run around and make an NFT that was a fake NFT that looked like it was a member of a real collection. So having verified NFTs is a way for the collection owner to say, yes, this NFT is a part of my collection. So let's do that now. We're going to make a new file and we'll call it verify nft.ts. And because I don't like typing, I'm going to steal everything from that first file again. So just loading up our user, giving them some Solana, setting up our UMI instance, and all the way to set up UMI instance for user. So I'll just paste that in. And to verify an NFT, it's actually pretty simple. It's only yet another, just a single transaction. So we've made our create NFT script and we've pasted in everything all the way up to setting up our UMI instance. We'll need to set up our collection address. I will steal that from our create NFT script. And we also need to set up our NFT address, NFT. And what was our NFT address? I'll get it from Solana Explorer. 84 something or other. That sounds good. And it looks like we need to import that public key, that function, which is part of UMI. There we go. Cool. So we have just a pretty default UMI script with a collection address and NFT address set up for us. So we've pasted in our collection address and our NFT address into verify nft.ts. The only thing left to do is actually make that transaction that verifies that this NFT is a member of this collection. And that will flip that is verified to true on the NFT. So let's make that transaction. Const transaction equals await. And it's called verify collection v1. And it takes an UMI instance and a bunch of options. The options are the metadata. And this is the metadata for the NFT that we want to verify. We'll actually use a little helper. It's called find meta PDA. It comes with Metaplex. And we'll just give it the options. Find the metadata PDA for this mint, which is our NFT address. NFT address. Beautiful. The collection mint, which is our collection address. Nice. And an authority, which we'll actually just say is the user running UMI. So if we do UMI.identity, that is our authority. We could also say authority is UMI user. Same thing. It just means one says it's this particular key pair. The other, it says it's whoever is running UMI, which is also the same user account, the one from our id.json. So we do transaction dot send and confirm UMI. Beautiful. And then we'll do console.log. And let's use some cool emojis. I will use a big old tick for being verified. And we'll say NFT verified. And let's give it the NFT's address. NFT as member of collection. And we can say collection address. And let's also say C Explorer at, and we'll say get Explorer link for an address which is the NFT address on DevNet. That looks good. Excellent. I'll just save it and format it. And everything looks good. I can remove some of those unused imports. Don't have to, but I just want to keep our file nice and ensure there's no dead code. Let's go and run our verify nft.ts. I'll clear my screen and do npx esrun verify nft.ts. Give it a moment to run. And it looks like it's finished already. That was really quick. Let's go check our NFT. And what we're looking for here is in the metadata. There we go. Verified is now set to 1. Explorer actually updated while I was looking at there. I was worried for a second. Yeah, cool. Great. So our NFT is now verified as a member of that collection. So now we have a beautiful NFT. If we click creators, our wallet address is shown as being the creator. That NFT is verified as being a member of a collection, which means that wallets and galleries and art auction sites will show our NFT nicely because it's important that NFTs are verified as being parts of collections. We have a beautiful collection. And yeah, we can transfer this NFT to people. We can set it up on auction sites. We can make dApps that use this NFT to like token gate access to something. That can be a real world experience or a digital experience. If you want to learn more about Metaplex's tools that we were using in this lesson, the tool we were using is called MPL Token Metadata. So if you Google that, you'll find all the documentation about that tool. And if you want to learn more about Solana, I will see you in the next lesson.
Our next smart contract allows users to offer an amount of one token to exchange for a desired amount of another token. For example, Alice wants 100 dog tokens and is offering to swap 10 USDC. Without our program, the users would have to swap with each other manually. But what if Bob promised to send Alice 100 dog tokens but took the 10 USDC and ran? Or what if Alice was dishonest, received the 10 USDC and decided not to send the 100 dog tokens? In the traditional finance world, when Alice swapped with Bob, there would usually be someone in the middle holding the funds temporarily and taking a percentage of the transfer for themselves. But in blockchain, this is solved with a swap program, also called an escrow. Our program will transfer the funds provided by Alice into a vault account and store details of her offer, like the amount and type of token she wants, in another PDA. When Bob decides to take the offer, our program will transfer Bob's tokens to Alice and transfer the funds in the vault to Bob. Now remember, in traditional finance, someone would sit in the middle, taking a couple of percentage points of what Alice and Bob are offering. But with our smart contract, Alice got 100% of the tokens Bob sent. Bob got 100% of the tokens Alice sent, and they got what they wanted without having to trust each other. Fees were only a fraction of a cent. That's the benefit of decentralized finance. Let's get started.
So let's make a swap program. First thing I'm going to do is run anchor init swap, and I'm going to use the multiple files template. Because this project is a little bit larger than, say, our favorites program, multiple files will split our program up across different files and directories just to organize our project a little bit better. So --template equals multiple. Give it a moment to install. Great. I change into that directory. And let's open up our editor and have a look around our new project. So here's our project. The actual anchor program is in the programs swap directory, and the TypeScript tests are in the test directory. Programs swap is also a little bit more interesting than the normal single file layout. There's still a librs, but helpers that are specific to each instruction handler live in the instructions directory. There's a state directory for storing basically the structs for the accounts you're going to make. A constants file, I should say. And yeah, it's just this will make things a little bit neater for us. So the first thing I'm going to do is add some dependencies, because we're not just using Anchor here, we're also using Anchor SPL, which helps us do things like transfer tokens around. So let's do that.
let's pop open cargo.toml, and just where it has the anchor lang, we're going to change that to look kind of like a little object. We'll say version equals 0.30.1, and we'll also turn on the features equals init if needed. Init if needed allows us to create an account, add an address if it doesn't already exist. We'll also add our Anchor SPL. And what version? The same as our version of Anchor. So 0.30.1. And we may as well just say the current version of Solana program as well. It was 2.0.3. Great. So we now have our program with Anchor and Anchor SPL installed and the init if needed feature turned on. I'll just fix that typo. Great. Something else is we should probably also look at setting up our constants. I'm a big fan of avoiding magic numbers when I program. So if someone else is reading my code, I don't want them to see 8 plus 32 plus 32. I just want them to see variables that make sense to them. So in Anchor, I'm often adding 8 to things to get the true size of an account on chain. That 8 bytes is the anchor discriminator. So I'm just going to do pub const anchor underscore discriminator, and that will be a, what is it? A U size. So just whatever the size is for the platform. And it's 8 bytes. It just saves us having to reference that anywhere else as well. Oh, and I'm missing an equals sign there. There we go. Great. We're also going to be transferring some tokens in this project. So let's create a helper function that just does that for us. That way we don't have to cut and paste everywhere. Instructions, new file, and we'll call it shared.rs. And in this file, we will create our transfer tokens function. So that's just going to be pub function transfer tokens. And we're going to take this generic, which is the Rust lifetime specifier. This is telling Rust how to hold onto a bunch of the variables inside this function. And what we're saying with this lifetime of info here is just hold on to them for as long as you need to hold on to the underlying Solana account info object. If you don't know what that means, that's fine. This is not a Rust course. This is a Solana course, but you can read up about Rust lifetimes in the Rust book. Cool. So we're going to say from, and that's going to be a token account. Token account is fine if we wanted to make our project specific to either the old token program or the new token extensions program. But if I wanted to make my program work on both of those, then there's a thing called interface account, which is just a way to have our program work across tokens that are made with the older token program or the new token program. That will last for as long as info does. And you can see here how we wrap around our token account. We're also going to borrow that value as well. We should add a return type for this function. So it's just going to return a result of nothing. That looks nice. We should probably also, for our share.rs, we should actually expose it from our module because I can see that everything is a little bit dark and gray here. Let's do that too. So we've got pub mod initialize and pub use initialize. Let's change that to pub mod shared and pub use shared star to expose everything inside shared.rs. And you can see that the gray has gone away now. You can also see that interface account is red if, anchorlang prelude interface account. That looks good. Yeah,
think we want that. In fact, we can just import all of the anchor prelude because it's kind of a bit of a normal anchor thing just to import the entire prelude. That gives us all the what people often call the goodies from anchor without having to type the full path to any of them. We'll probably also need to import a bunch of things from anchor SPL. So let me do that, like token account. And we want to import it from anchor SPL token interface because that is the magic that allows our program to work on both the older token program and the newer token extension program. That is looking a little bit better. I'll just fix a little typo there. And I will also turn on word wrapping so you can see what I am doing. There we go. Cool. So it's still a little bit of red there, but it's just saying that we're not returning a result yet, which is true. We're not returning a result. I'll also neaten this up a little bit. There we go. And let's add more of these options for our transfer tokens function. So we have a from, which is an interface account. We'll also have a to, which is an interface account, also wrapping around token account. An amount, which we will also borrow, and that will just be a U64. A mint, which will be a pub key. Same thing, we'll do interface account. Oops. And we will, it's going to live for the lifetime of the account info object, and it will be a mint is the anchor type we're using there. We'll have an authority, which will be signing this transaction. So borrow signer, and that has a lifetime of info. We'll also have the token program be one of our options as well. And the way we say that, to say that our token program can be the older token program or the newer token extensions is interface. And that lasts for info. And then we say token interface. There we go. That looks good. So the way we actually transfer tokens is we call the token program's transfer checked function. Transfer checked just does a little bit of logic, making sure the mints are okay, and a bunch of other useful safety features. This is the reason we use Anchor, because it provides us with this good stuff right out of the box. So the first thing we're going to need to do is specify all the options we want for transfer checked. We'll just get them from the options we had for our argument. So we'll say transfer accounts options, and that's a type called transfer checked, a struct called transfer checked. So in Rust, sometimes you have structs, which would be interfaces if you're familiar with, say, TypeScript, that have names that kind of seem like functions. All that means is that that struct is an object that is used as an argument for that function. So we're about to call a function called transfer checked. The options for that function are called transfer checked in title case. Just a bit of a kind of cultural thing in Rust. I would probably call this, if I was writing this in TypeScript, I would call this something like transfer checked options. But in Rust, it's just transfer checked in title case. That's the options for the transfer checked function. Because we're calling just a program in raw Solana, we're not doing any anchor magic here. We're going to turn everything into the low-level Solana account info object. So you'll see it's transfer checked. From will be the same as from and just to account info. And mint will also be mint to account info. You might be surprised to find out that to is to account info. And our authority is also the authority dot to account info. We do this once because we don't want to have to run dot to account info a bunch of times throughout our program. So that is our options. So we should just call it transfer. Yeah, that looks good. We can call it transfer accounts options. That's fine. So our CPI context. A CPI context is just a really the program you're using plus the options. That's a CPI context new, and we have our token program. And guess what? It's to account info and our transfer accounts options. And that looks good. We've got a little bit of red here. I think it just wants us to import mint, and we want to import mint from the token interface option. So that one there. Likewise, transfer checked. We want to import that also from the token interface as well. So, SPL, token 22. Just see if that looks right, because it that should just be transfer checked. There we go. We don't need any special magic there. Anchor SPL, token interface, mint, token account, token interface, transfer checked. So there are similar imports in other places. We want to make sure we're always importing the ones from token interface. So we have our CPI context, which is our program that we're about to call plus all the arguments. Let's actually call our program. So we do transfer checked. And the CPI context, the amount, and the decimals, which we'll get from the mint. And that looks pretty good. We just need to import transfer checked. And again, we want to import it from probably from token interface, I think. So we'll just do it manually. Transfer underscore checked. And that looks good. No red. Everything is importing from either Anchor Lang itself, just for the prelude, and everything else is imported from Anchor SPL token interface. Great. So we now have this reusable function wherever we need to transfer tokens, and we're going to call it a whole bunch. So that is useful. Let's also think about what we're going to write to the blockchain. As we talked about before, there's really two parts to this. There's a make offer instruction handler, which will send tokens into a vault and write information about what the person wants in exchange for those tokens. And there's a take offer instruction handler, which will allow somebody to take the tokens from the vault and also send their tokens directly to the person that made the offer. So in state.rs, we're going to make a little file that talks about what that offer should look like. And we're going to call it offer.rs. And we're going to import our Anchor Prelude again. Oops. Use Anchor Lang, ding ding, Prelude, ding ding. Star ding ding is just a personal thing I use to refer to the double colons. And then we're going to talk about what that actual offer looks like. So that's going to be a struct pub struct offer. This is going to be an Anchor account, obviously. So we add our hash account macro. Also, we want to easily be able to work out the size of what an offer is, because we're going to have to write one of these out to the chain at some point. So there's actually a useful thing in Anchor that's called init space, which is the size taken to initialize or create this account on chain. So if you add derive init space, our offer struct, or any instances of our offer struct, now have an init space property that is added to them, or an init space trait that is added to them in Rust terminology. As we said before, this is the offer where we save details about who's making the offer and the tokens they want, etc. So it's going to have an ID, which we'll just use a numeric ID. U64 is fine. A maker, which is who made the offer, and that will just be a pub key. The mints of what they are providing and what they want. So we'll call that token mint A, and that is a pub key. And I will copy that line down, Shift Option down. Token mint B is also a pub key. We have token B wanted amount, which is how much they want in exchange for what they've put into the vault, which is a U64. And also, because this is a PA, we want a bump, which would just be 8 bytes. Add that missing pub, and everything is gray because I haven't actually exported the contents of offer.rs. So back in state mod.rs, I will add pub mod offer, and I will say pub use offer everything inside. And you can see now that offer.rs looks a little bit better. What is that? Oh, I've got a semicolon on the end there. I don't need that. There we go. Nice. All the red has gone away. We are ready to move on. So we've just made our offer, which is what we're going to write to the chain. And we should probably get started on our instruction handlers. So let's open up librs and just have a look at how it looks. It is essentially the same as most other Anchor programs. There's a bunch of imports. We say our program's ID or program address. And then we have this module that we turn into an Anchor program with the program macro that defines all our instruction handlers. There's one instruction handler called initialize. Let's turn that into our make offer instruction. So I'm going to call it make underscore offer. I'm going to change the spelling of CTX to just be context. That way I don't have to think about it being spelt slightly different. And it's going to be a context of make offer. We'll call our accounts for make offer rather than calling them initialize. Again, I don't particularly like calling structs things that like verbs like make offer, but it's a bit of a Rust convention to if a program or a function has some options, then those options are named after the function just in title case. So inside our make offer instruction handler, I'm going to call two helper functions. The first will be instructions make offer, and we'll call that first function send offered tokens to vault. And we add a little question mark on the end to say, if this fails, throw an error, and that's okay. We expect that maybe it will fail in some cases. And our second function will be called instructions make offer save offer. Examples of failures in sending the offer tokens to the vault was, say, we tried to someone was trying to reinitialize an old vault account. We would throw an error in that function. So that question mark is just a way of saying, hey, if it throws an error, that can happen. We expect that. It's a short way of doing error handling. So we have send offered tokens to vault and save offer. That looks good. We should probably make offer. That sounds good. I think it's it's looking for make offer and it's not finding it, so it's not happy with that. So we need to make the make offer struct, which is all the accounts that will need people to specify that they're going to use when they want to use the make offer instruction handler. And we also need to make the actual make offer file. So in instructions, let's rename our initialize. And let's just call it make underscore offer. There we go. And happy to do any any edits for us. VS Code is just updating mod.rs to specify that file is now called makeOffer rather than being called initialize. Back in makeoffer.rs, what used to be called initialize.rs, we're going to rename that to makeOffer. That struct up the top. And we will also rename handler. We'll turn that into our send offer tokens to vault instruction. And we'll work on that in a moment. Let's just start with makeOffer. What kind of accounts will people need when they're calling this? Firstly, we'll need their own account because they're going to sign the transaction. So we'll call that the maker. So that's pub maker, and that is a signer. Similar to before, we're going to use this info generic, which is the Rust lifetime of an account info object, to tell Rust that the lifetime of these variables in memory will be the same as the underlying account info object. So we have a signer of info, and because this the maker will pay for the transaction, their account needs to be mutable. So let's do account mute for mutable. We will need to have the mint of the token that they're putting into the vault. So we'll call that pub token mint A. We're going to use an interface account again, just to say this could be an old a mint account from token program or a mint account from token extensions. So interface account, and the lifetime is the lifetime of the underlying account info object, and mint is the object we're going to effectively wrap around. We'll also make sure that the token program used to mint that is what we expect. So we'll say mint ding ding token program equals token underscore program. We've done our import, and now we're going to have the other mint, which is token mint B. I'm just going to copy and paste that one, and it's going to have that same check that mint token program equals token program. So that's the type of token that we want, token mint B. We'll also specify where the tokens that we are about to put in the vault come from, which is maker underscore token underscore account A. That will be an interface account again, so wrapping around token account and lasting for the lifetime of an account info object, the underlying Rust account info from the Solana crate, rather than Anchor has nice names like token account, mint account, etc. Whereas the Solana program crate just calls everything an account info object. We're going to add a few Anchor checks to maker token account A. The first is that it's going to be mutable because we're going to move files out. Well, not files. We're going to move tokens out of that token account into the vault. We'll have a few checks as well. Associated token mint must be token mint A, and the associated token authority, fix that typo, equals the maker. In other words, this account actually needs to belong to maker, the person signing the program, and associated token program should be equal to token program. That looks good. I'm going to keep going because I've got a little bit of red there, but I need to finish some more things off before I look at it. Pub offer. So this is the offer account which we will be making. That's just an account. So we call it a system account, so nothing particularly special. But we will add some anchor checks, because this is this PDA where we're going to save details about what we want in exchange for our tokens. So we'll say init, i.e. make it, who will pay to create it, which is the maker, i.e. the person who signed this transaction, how much space we're going to allocate, which is 8 bytes, anchor discriminator, that's what we made in our constants rs before, plus the size of offer init space. So the size for everything to store an offer struct. Seeds will be the bytes of the word offer, the key of maker, the pub key of maker, and as a reference, the ID of the offer, and we need that to be bytes, so let's turn it into little endian bytes, and then also as ref. That looks good. Oh, and finally, because this is a PDA and we want to be efficient, we will save the bump. That looks good. Got a few things we probably need to import. Let's go and check. So we've got our anchor lang prelude star, and we're importing a few things. Oh, wait a sec. We're importing a few things from our anchor SPL token interface, but we probably should be importing a few more. So I would say actually we want from anchor SPL, firstly, yes, we're happy with token interface mint, but we probably also want to import associated token. Thank you very much. And rather than just mint, we'll also want token account and token interface. That should be good. Let's put a semicolon there. And then there we go. A couple of those we're not using yet, but that's okay. So we've added those imports, and you can see there's a lot less red there. And again, always using token interface rather than some of the other imports, just so we can have that compatibility with both the older token program and the newer token extensions program. So we have our offer. We need to also use the vault account, because when we make an offer, we're gonna save details of the offer, and we're gonna put our tokens in a vault account. So let's do pub vault, and that's also going to be an interface account with a lifetime of info, and that will be a token account because it's just going to store some tokens for us. Let's add some anchor goodies as well, some little checks on that account. Firstly, we're going to need to create it, so init. We don't say init if needed because we don't want anyone to be able to reuse old vaults. We'll say who is going to create the account, which is the maker, and we're going to mention a few checks that we're going to do with this, and I'll copy it from maker token account A. We're going to make sure that this token account's mint is token mint A. The authority will not be the maker; it will actually be the offer. So this token account isn't owned by a user; it's being owned by our program. Specifically, actually, its authority, rather than its program owner, is the actual offer account. So the vault account is owned by the offer account. The vault's authority will not be maker. The vault's authority will actually be the offer, because the offer PDA is going to each individual vault will be its authority will be the offer account. The offer account will sign for things to move things in and out of the vault. So you'll see that later on when we start transferring tokens around. And we'll also check the token program is the token program we expect. Finally, we're just going to specify the accounts of the programs we use. So like the system program, system_program. That is a program account. use it for the lifetime of info and system. And likewise, we'll also use the token program. That will be another interface account because we're going to wrap around either the older or the newer, older token program or the newer token extensions program. So that's token program is a interface. Sorry, it's not an interface account, it's just an interface over info and token interface. We can actually make our project a little bit smaller by excluding this stuff, but it is best practice, so that's why we've included it in this tutorial. Finally, we have the associated token program, which is the program that maps associated token accounts to their owners and to token mints. So associated token program is a program for the lifetime of info and associated token. There we go. So that looks pretty good. It's saying it doesn't like ID, so let's go fix that. We need to actually say in this struct that we want access to the ID that the client provided when they were making their instruction. So we will scroll up and we will say we want access to, what was it, instruction. We want the ID parameter, which is a U64. Save that. And you can see the ID green has, the ID red has gone away. Anchor discriminator, it looks like we didn't import that. So import create anchor discriminator. Thank you very much. Sorry, offer is not an account of system, is an account of offer. In other words, offer is the struct, and in our we are specifying that the offer account is an instance of that offer struct. So yeah, our whole make offer is complete. There's no red. We now need to work on send offered tokens to vault. So let's make send offered tokens to vault. This is actually a pretty small function. It's going to take a context, which I will spell properly. And so it's going to take a context of make offer, which we will actually borrow because we don't need to write to it. And what else is it going to take? Probably the amount of tokens. So token A offered amount, which is a U64, right? There we go. And we're going to get rid of the logging there. We're just going to say transfer underscore tokens. Oops, tokens. And we will say our options for transfer tokens. So the first thing is context. I think I might need to import this actually. Is it complaining that I need to import this? No, it's just saying that we, because this is going to return a result of nothing. We can't. There either needs to be a semicolon there, and we go OK, or we can just remove the OK because transfer tokens returns nothing anyway. So there we go, and it's saying that transfer tokens is not imported, so we need to import it. And it looks a little bit happier now. It's just saying that we need to give it the right arguments, which is what we're going to do. So we're going to borrow context dot accounts. This is going to be our from. It's going to come from maker token account A. And it's going to the vault. So context dot accounts dot vault. How many tokens? Well, that is the token A offered amount. What's next? The mint. Mint will be the context dot accounts, and that will be token mint A. Authority will be the maker, so that's context dot accounts dot maker. And the token program will be whatever the person running the instruction has specified. So context.accounts.token_program. Save it, and we've filled in all our details that our transfer tokens functions wants. There is no red in the file. We have now created our send offered tokens to vault instruction, and everything in that file looks good. Let's add the final part of make offer, which is that second function called save offer. So pub function save _offer, and we'll use the context again. So it's going to be a context of make offer because we want access to all those accounts. So we have our context of make offer. We're going to have an ID, which is that U64. We're going to need to specify how many tokens we want in exchange, which is token B wanted amount. And that will also be a U64, and they are all our options. So this will return a result of nothing. And here is our functions body. I'm just going to turn on word wrap so you can see a little bit easy. There we go. There's a little bit of red there. It's just saying that we haven't returned a result yet, which is true. So we're going to call context.accounts.offer, which is the address of the account that we've calculated based on the seeds. And all we're going to do is just use this set inner method to go and save some stuff into the account at that address. So we provide an offer instance that we're going to make from the ID. The maker in our offer will be from accounts, tokens.accounts.maker, and .key, which is their pub key. Token mint A will be context.accounts.token mint A .key. Token mint B will be context.accounts.token mint B .key. How much of token B they want in exchange, which is the token B wanted amount. And also, because this is a PDA, we will be saving the bumps that were used to calculate it, just for performance reasons. Context.bumps.offer. And then, there's a typo there. That context.account should be a context.accounts. And we will also add an OK because we're going to send this back to the top level instruction handler. That looks good. There is no red in our file. Very happy with that. So we've now finished all the functions we need for make offer, as well as the accounts struct that instruction handler is going to need, which specifies all the accounts that we're going to use in this instruction and how we're going to use them. So we're just going to go back into this top-level librs file and make sure that our top-level instruction handler has all the things that we want somebody to provide for this instruction. So obviously, yes, they have a context, which includes all the accounts they're going to use in this instruction, whether they're readable or changeable, or all the other things that we need, whether they need to sign the transaction. But we're also going to need them to specify an ID, which they can come up with themselves. We're going to make it so that people can't reuse IDs anyway. So it's just it's a random number that hasn't been used before. They'll also need to say the amount of token A they want. Token A offered amount, which will be a U64, and also a token B wanted amount, which will be a U64. That looks nice. And then in our make offer body, we need to specify all the things that these two helper functions are using. So instructions, make offer, send offer tokens to vault. You can see from the error that it wants a few things. It wants a context and it wants the token A offered amount. So let's give it the context, which is literally just our context from the parent, and we will borrow that. And we want token A offered amount as well. That looks good. You can see the red has gone away. Save offer also wants to use our context. We can see from the error message, it takes a context, an ID, and a token B wanted amount. So context, ID, and token B wanted amount. Save that. I've got a semicolon on the end of save offer. I don't actually need it because we're going to return whatever save offer returned. So this is just a Rustism. You can omit the semicolon from a line, and that ends up being returned by the function. That looks good. Our program should probably build at this point. We've only done make offer, which is just getting Alice's tokens into the vault and saving details about what she wants. That's a good enough a time as any to go and test our program by building it. So let's do a anchor build and build our program. I'll give it a moment to finish. And we can see now that we've updated our program and it builds now, which is great. So we're now officially halfway there. Let's go create take offer. So back in our top level librs, we're going to do pub function take offer and make a new instruction handler. That is going to take a context, which is a context of take offer, which we will create in a moment. And it's going to return a result of nothing. And there's going to be two parts to take offer, which you can probably imagine. The first is taking the tokens from the vault and putting those in the taker's account. And the second is taking the tokens from the taker's token B account and sending them straight to the maker's token B account. So let's have a function for each of those. Instructions, take offer. This is going to be a file that we make. And the first function will be called send wanted tokens to maker. And we will pass it the context. And we're going to borrow the context because we don't actually need to write to it. And we're going to say if that fails, that's fine, it can fail. There might be many reasons why it fails. Maybe the person doesn't own the accounts they're trying to use. Yeah, that's fine. If it fails, then it fails. That's Anchor just doing its default checks and saying that something was wrong. And if it fails, that's fine because it's Anchor probably complaining that somebody's trying to take an offer that doesn't exist, or that one of our token accounts isn't actually owned by the taker. So that's all good. Instructions, take offer, and we will have withdraw and close vault. And it will take a context and it will return that. Now we can see there's a little bit of red here. It's just saying that take offer, the account struct hasn't been made. That's okay. And the take offer file hasn't been made. So we should probably make our take offer file. So under programs, swap source instructions, new file, take _offer.rs. And let's go create take offer rs. The first thing we're going to need is, well, let's do our import of all the standard anchor bits. We can probably get most of those from make offer. So I'm just going to copy all the imports from make offer into take offer, and we can remove the ones we don't use. Also in mod rs, I'm also going to make take offer a module and expose it for everyone else. So there we go. So let's create our take offer account struct. So it's a pub struct of called take offer, and it takes an account info item to set the lifetimes of various objects inside it. Also, because it's going to be an anchor accounts struct, we need to say hash derive accounts, and I need to spell derive correctly. There we go. That looks a little bit better. And it's a capital A for accounts as well. All right. So we have a taker, which is the person who's going to sign this transaction. That's a signer whose lifetime is info. And we'll also say, because the taker is going to not only sign this transaction, but pay for the accounts to be created. So we'll say account mute, so that this we can mutate, or in other words, change the balance of this account so that they can pay for the transaction. We'll have the maker that they need to specify, pub maker, which is a system account. We'll go for the lifetime of info. And that is also mutable because they will have some of their balances changed. We'll have token mint A. And that's an interface account of info and system. Oops, not system, mint. It's a mint account. So it's interface account wrapping around mint. That just means that, again, we can use this on the older token program or the newer token extensions program. We're going to specify there's token mint A and token mint B as well. So let's specify both of those. Token mint A and token mint B. They look good. What else will we need? Well, we'll need the taker's token account A, because that's where we're going to put the tokens that we get from the vault. So pub taker token account A, and that is a box of interface account that lives for info and wraps around token account. And we'll also have the taker token account B, which is where we're going to take tokens from and send them straight to the maker's token account B. So I'll just do a quick little copy paste. I'll add that missing comma. That looks pretty good. What's it complaining about there? Just got to make sure that those are all lined up. That wraps around. Yep, it's gone away. Excellent. Just needed to add another comma. We're going to add some anchor constraints on token account A and B. We'll say, so account, and for taker or token account A, we will say init if needed. Why init if needed? Because the taker may not have any balance of token account A. So if they've never had token A previously, when we move the tokens from the vault into the taker's token account A, we'll need to make a token account A for them. So let's do that, init if needed. And we'll also say we want to specify the mint of this should be the token mint A. So that is, also say who's going to create this this account, by the way. So payer equals taker. So I'm going to pay to make their own token A account. Init if needed. Payer is taker. Associated token mint of this account should be token mint A. And associated token authority, which is kind of the, if you think of owners in Solana are like program owners, but authority is like the account level owner. So that authority is taker. And the token program should just be the token program that we specified. So that is associated token program should be token program. Cool. So taker token account A is a box of interface account of token account. That looks good. Init if needed. Payer is taker. And the mint should be token mint A. The authority should be the taker, and the token program should be the token program specified in the instruction. A little bit of red there. What's it complaining about? A non-optional init constraint requires a non-optional system program field to exist in the account validation struct. That's okay. I haven't specified the system program yet. So once I add the system program yet, that error will go away. So we've got the taker token account B. And let's add some constraints here. Account. And for this will be mutable because its balance will change. And all we need to do is copy some of our constraints from earlier, but this is taker token account B, so we need to make sure that we're checking that it is the token mint B, not token mint A. That looks good. There's another account that will another token account we'll be mentioning here, which is when we will take tokens from the taker's token account B, and we'll send them to the maker's token account B. So pub maker token account B, and let's add some constraints. So Anchor can check all these good things for us. The maker's token account B will also be init if needed, because the maker, again, may not have ever had any of these tokens before. So init if needed. Payer to create this account will be the taker. And the mint, authority, and token program, I'm going to copy and just double check. So the mint for the maker token account B should be token mint B. That's good. The authority is not the taker, it will be the maker, because this is the maker's token account. This is Alice, this is not Bob. We need to make sure that Alice owns Alice's account that holds token B. And the token program is the token program they specified in the instruction. That is all good. Finally, oh yes, we're going to involve the offer account. So the offer is just an account who will live for the lifetime of info, and it's of the type offer. And what do we need to add to this? Well, let's start our little anchor account constraints. This will be mutable. Why? Because we're going to close this offer account when the offer is taken. We'll also, when we close this account, we will also return the soul in it back to the maker. Why? Because the maker made the offer account in the first place. So it seems fair that when we close this account, we should refund that back to the maker. Close equals maker. And we're going to just do some little, we're going to specify some things we want to exist inside the struct. So has1 equals maker, has1 equals token mint A, has1 equals token mint B, and the seeds for this are exactly the same as what they were before, which is the bytes of the word offer and the maker's key as _ref and the offer ID. Offer.id.to little endian bytes. So we have it as bytes as ref. There we go. That looks good. And finally, the bump equals offer.bump. Always save your bumps. That looks good. Excellent. What else do we need? We need the vault, because obviously this take offer is going to move tokens from the vault. And yes, you can probably already imagine that the vault will be mutable. So let's go set that up. The vault is an interface account. There's the lifetime of info, and it is wrapping around just a regular old token account. Again, if we weren't doing this compatibility between the older token program and token extensions program, Vault would just be token account, but because we want this compatibility layer, the best practice is to use these interface accounts everywhere. So we have our account, and the vault is obviously going to be mutable because we're going to take all the tokens out and we're going to give them to the taker. And the rest is just making sure that the mint of the token account is exactly what we expect. So I'm going to copy these, but I'm also going to check them. So the mint of the vault will be token mint A because we took tokens from the maker's token account A and we put them in the vault, and they will be of the mint A. The authority of the vault account will neither be the maker or the taker. The vault account is actually, its authority is the offer account. This means that the vault is controlled by the offer. It's not controlled by the maker or the taker. It's controlled by the offer, which is the offer account can actually sign for things. And when we send tokens from the vault, they will be signed for by the offer's own account. And our token program will be our token program. That looks good. Save that. And finally, we've got the normal checks about all our programs. I'm just going to copy those from make offer. System program, token program, and associated token program. Thank you very much. I will paste those in. And that looks good. No errors, no warnings. Just a couple of unused imports, that's okay. I'll delete them once I've finished writing this file. So we've made our takeoffer struct, which is going to specify all the accounts that we need to check as part of an incoming takeoffer instruction. And we've created the top level instruction handler in librs, which we called takeoffer. And back in librs, we said we wanted to have two functions. One was called send wanted tokens to maker, and the other was withdraw and close vaults. So in takeoffer.rs, let's create the first of those two functions. So to make that send wanted tokens to maker function, we'll do pub function send wanted tokens to maker. And that's going to take a context, which is a context of make offer. And we're going to borrow that item as well. Also, that's going to return a result of nothing. And let's make that happen. So this is actually just going to be very simple. To send the wanted tokens to the maker, I send the tokens from taker's token B account straight to the maker's token B account. It's just going to be transfer tokens, our little helper function we made earlier. And the from will be, we'll borrow this, context dot accounts taker token account B. The 2 will go to the maker's token account B. Context.accounts.maker token account B. The amount of token B to send will come from the offer. So that's context.accounts.offer token B wanted amount. The mint will be and context.accounts token mint B. The authority, i.e. the person who controls that account, will be the taker. And the token program will be context.accounts.token program, token_program. That looks good. And this is a context of take offer. I did notice that my autocomplete was a little bit funny there, so that explains it. I think I wrote make offer when I should have written take offer. So there you go. So yeah, that actually looks good. So we're transferring tokens from the taker's token account B straight to the maker's token account B. We're transferring the exact amount that the maker wanted. We're making sure the mint of the accounts are token mint B. We're checking that the authority of the from account is the taker, because this transfer is going straight from the taker to the maker. And we're just making sure the token program is the same one that we specified in the instructions. That looks good. So we've just completed our send wanted tokens to maker function. The final part for take offer is to complete the other helper function we made, which is called withdraw and close vault. So let's make that now. Pub function withdraw and close vault. And it's going to return a result of nothing. The options it will take are just simply the context again. Context. And that's the context of take offer. Now, we're going to do a transfer here, but it's not going to be a transfer from a regular account. Instead, we're actually going to transfer from our Vault account, which is owned by our offer account. So this is a PDA transfer. It's a transfer that's being signed for by our offer account itself. So we're not going to reuse our helper function, which is focused on a different type of transfer. We're going to make our own calls to transfer checked with a slightly different set of options this time. So we make the seeds. Which we will borrow. And the first of the seeds will be the bytes for the text offer. You might remember this. This is the seeds we used to get the address of the offer account. So we're going to use that to actually sign this transaction. The second option, the second seed for that account will be context.accounts.maker to account info .key.as_ref. What else will we need? The offer ID, context.accounts.offer.id.to little Indian bytes. I'll do a little bit of magic on it there. And then finally, bump, which we'll borrow, context.accounts.offer.bump. We'll also want to borrow that offer ID. So let's, that looks good. Little semicolon. We can actually have multiple signers when we do a transfer from a PDA like this, but we only have one in this case. So we're going to wrap our seeds into a bigger signer seeds array. Let signer underscore seeds equals bigger array and just our seeds. Do a little magic there. That looks good. We're going to make the accounts that are going to be involved in our transfer checked function. So that is let accounts equals transfer checked. This is really the options for our transfer checked. From context.accounts.vault.toAccountInfo comma, mint. Actually, let's do the 2 first. I think it's a little bit more. Context dot accounts dot 2 is the taker. These will go to the taker's token account A, because we're going to take the accounts from the vault and put them into the taker's token account A, because the tokens in the vault are of the type token A. Taker's token account A, oh yes, to account info, comma, the mint, which is context dot accounts dot taker token mint A, remain obviously to account info, and our authority, which will be our offer account. Context dot accounts dot offer dot to account info. One comment there, and doesn't like transfer checked. It's okay. We just need to import it. Import transfer checked from token 22 or token interface. I'm pretty sure I want the one from token interface. That'll allow us to use both older and new token programs. But let me double check. Yeah, that looks a little bit better. There's actually a transfer checked right below token interface, so make sure you import that one, and not the really long one that I imported. That is happier now. Excellent. So we've got our accounts all set up for this token transfer we're about to do. We're going to make a little CPI context. Let CPI context equals CPI context new with signer. And all we're really doing here is combining the accounts, which are effectively the options for transfer checked, the token program, and the signer seeds, which allow us to sign for this transaction as the offer. So the program will be context.accounts.token program to account info. I might actually, like the next time I get some time free, I might make a little wrapper for this, because I'm getting tired of typing to account info. Maybe you are too. And accounts and signer seeds. That looks good. Oh, we just want to borrow that and it will be happy. Yep, that looks good. No red. The only red there is our result. That's fine. We haven't actually written the code for the result yet. What's next? We've got our CPI context, and let's actually do the transfer now. So that's transfer checked. And takes a context, which is our CPI context. It takes the amount that we're going to transfer. So that's we're going to get that from the vault. So context dot accounts dot accounts dot vault dot amount. There we go. And the decimals. Context dot accounts mint token A dot decimals. Token mint A decimals. That's complaining. It wants me probably to import it. Cannot find function in that scope. That's fine. Import transfer checked. And we probably want to import it straight from token interface. So not token 22 and not token. I think there's I think we can just import it straight from token interface manually. Let's do that. Comma transfer checked. there. That looks good. There's a little bit of red elsewhere. What's this? Check that out in a moment. Oh, I think. Oh yeah, that's just it saying that we need to do our return, which is fine. We've done our transfer checked, which is taken that's the withdrawal part of withdraw and close vault. That has moved the token A tokens from the vault into the taker's token A account. Great. If you're wondering why we need to provide the decimals for transfer checked, it's part of the checked part of transfer checked. It includes some safety checks like making sure that you explicitly provide the decimals. So we've moved our tokens from the vault into the taker's token A account. The other part of this is to close down the vault itself so it can't be reused. So we're going to make a close account struct, which is going to be the options that we provide to another CPI to the close account function. So let's do that now. Let accounts, and it will equals close account. We have three options: the account, which will be the vault itself, context.accounts.vault, and to account info. We'll have our destination, which is where we're going to refund any LAN ports that were in that account. We'll send them to the taker, but we could send them to the maker as well. Context.accounts.taker.to-account-info, and the authority, which is who's allowed to, who's doing this, which is the offer. The offer account owns the vault. That's context.accounts.offer, and you guessed it, to account info. That looks good. I needed to import close account, by the way, as well. I've done that right at the top here, and it comes directly from token interface. So make sure that you import things from token interface, not from the old token program specifically, not from token 22 specifically. Import from token interface. Great, so here's our accounts. Let's make a CPI context so that we can go and invoke our close account function. That's a CPI context and new with signer. The program will be context.accounts.token program and to account info. The accounts we've actually already specified above, and signer seeds. I think we just need to borrow that and it should be okay. Yep, that looks fine. And then, so we have our CPI context, everything we need to go and invoke close account. Let's actually invoke a close account. Close account, and yeah, CPI context. Oops. What's it saying there? Mismatch types. Ooh, I can see what I'm doing there. I am not using the right version of close account. So let's just go back to my imports and double check that. Yeah, I've got token close account. I want token interface close account. It's one thing to be really careful of when you're using an editor that suggests imports. Do make sure you're importing everything from token interface, not from the token program. And you'll see that that's now fixed. Great, and I actually can omit the semicolon because we're going to return whatever closed account returns from this function. That looks good. So we've created our make offer, we've created our take offer, the high-level instruction handlers and all the helper functions and the structs of accounts they need. Let's go and review librs. We've got our take offer, withdraw, and close vault. That all looks good. We should probably check that our program compiles. So back over here in our terminal, let's do a anchor build. A couple of unused imports, that's okay. I might actually get rid of those just for the sake of cleanliness. We weren't using anchor discriminator. we need to handle any errors in transfer checked. So what we can do with that is we can say a little question mark there, and that says, look, if transfer checked throws an error, throw an error. That's, that's okay. We can deal with that. That looks a little bit better. So back in our compiler, let's clear the screen and can build again. And that builds. We now have a working swap program where someone can offer their tokens to be taken, and then someone can take that offer and receive those tokens directly in their own accounts. So we've run our program and it builds. Next step is to test it. We've already got some tests we've prepared for you, but I'll go through them here. This is swap.ts under the test directory, and it's pretty simple. We import a few common bits and pieces, Anchor itself, the chai assertion library, the Solana helpers, make a few variables, and we have one block of tests called swap. That connects to Anchor, which allows Anchor to use the keys and the networks set up in our anchor.toml. And we set up some variables we're going to use in a moment for Alice, Bob, token mint A, and token mint B. Our before handler is really simple. It just creates some users, some mints, and some token accounts, and uses those mints to mint a particular balance of tokens, so that Alice has a lot of token A and that Bob has a lot of token B. There's two tests, and the first is our make token test. Make sure that it puts the tokens Alice offers into the vault when Alice makes an offer. So we're simply going to get our list of accounts together, and then send that transaction off. Program methods.makeOffer with our options, the accounts we want, and our signer is Alice. Afterwards, we're going to check the balance of the vault, and we're going to check the offer account has the data that we expect. The second test is pretty simple. It's program methods.takeOffer, confirms the transaction, and checks Bob's accounts after running the test. Also, we could add a test to make sure that the vault is closed. I don't think we are here, but I can add one in a moment. You'll also note I run .slow, and then I have a variable set to, I think it's 60 seconds. Because Anchor tests connect to our local validator, by default, Anchor shows them as slow because Mocha actually shows them as slow because they take anything that takes more than, I think, half of 30 seconds is shown as slow. So if I set my slow threshold to 60 seconds, anything that takes half of 60 seconds will be shown as slow. Our tests only take 15 seconds, so they won't be shown as slow. You didn't really have to worry about that too much. It's just a me thing. I hate my tests being shown as slow. I like to establish a bit of a baseline for how long a test should take. So yeah, pretty simple. We just have one describe block and a test that goes and checks make offer, and another test that checks take offer. If we run those, and you can import them into your own program, you can get them from the link that we will add to this presentation. You can actually call your take offer and make offer and check that they work as expected. Give it a sec. As I said, these tests take about, I don't know, maybe 15, 16 seconds each. And then we can see the first test is finished, which is puts the tokens Alice offers into the vault when Alice makes an offer. And in a moment, our second test should hopefully finish as well. There we go. Puts the tokens from the vault into Bob's accounts and gives Alice Bob's tokens when Bob takes the offer. So this program is a great example of the benefits of DeFi. Alice had some of one token and wanted another token. She didn't know Bob. Bob, at some point in the future, came along, took that offer that Alice made, exchanged his tokens for Alice's tokens, and each side got 100% of what the other person was offering without anyone in between taking a portion of anything. Also, the other useful thing about this program is that it shows you how to handle tokens in your own program, to how to hold tokens, and how to sign to transfer those tokens out of places where they're stored using CPIs. So I'll see you in the next lesson.
Imagine a company that wants to reward its employees with tokens, ensuring they remain motivated and committed to the project. This process is known as token vesting. Token vesting is a mechanism used by cryptocurrency projects to distribute tokens over time to certain stakeholders, like employees, advisors, or investors. Instead of granting all the tokens immediately, vesting restricts access to the tokens over a set schedule. This aligns incentives and prevents stakeholders from selling all their holdings at once, potentially destabilizing the token's value. In the upcoming tutorial, we'll write our own vesting contract. Our contract will have the following user experience. A company will be able to come to the DApp to initialize their own vesting contract and specify the mint address and total supply of the locked tokens. Next, the company will be able to add employees with their individual vesting details, which includes the total amount of tokens allocated to the employee, the vesting duration, and the cliff. The cliff is the initial period where no tokens at all can be claimed. Say the cliff is 6 months. Then for the first 6 months, the employee will have 0 unlocked tokens. After the cliff expires, unlocking begins according to the monthly schedule. Employees can also use this DApp to view the status of their vested tokens and claim any unlocked tokens. This project enables transparent, automated vesting on Solana. Companies can set customized vesting schedules for any SPL tokens, and employees can clearly track their vesting progress. So in summary, token vesting aligns incentives for projects distributing tokens over time. Our smart contract brings secure on-chain token vesting to Solana. By the end of this tutorial, we'll accomplish writing the smart contract code, running tests, creating a front end, and connecting the smart contract to the front end, creating a fully functioning decentralized application. Let's get started. All right, so let's create the vesting DApp. We're going to be using the npx create Solana DApp scaffold because it connects both a front end and a back end in one workspace and makes it a lot easier when you're making a full decentralized application. So let's get started by setting up the scaffold. We're going to navigate to our terminal and just type in npx create Solana DApp. And now we're going to enter the project name. We'll do token vesting. We'll select the preset for Next.js, Tailwind, and then the Anchor counter program. And this is creating a new workspace with npm. So it's going to take a second to load. We'll wait for everything to generate, and then we're going to open this workspace in VS Code and get started. Okay, so this creates a new folder inside the directory that you ran the command. So we're just going to cd into that folder. And then we're going to open in VS Code. Okay. And just to get everyone familiar with this scaffold, how it sets up the workspace for you, you have your web folder that has everything for the front end of the application. And you can see the app, the components, and all of the needed configurations. We're going to work with this later. So we're going to start out with our Anchor smart contract. So in the Anchor folder, you can see it has everything set up for the back end of the application. We have our programs, and then you go into source, and this is where the main smart contract lives in your librs. Now, we also have a few other folders generated that we're going to use later on in this application. But let's just first start with our librs. So you can see this is just a basic counter that was generated. If you actually run this with npm run dev, it's going to actually show the front end and a working counter. But we're going to change all of this for our vesting contract. So what we can do is just delete everything within the program. As you now know, by working through the bootcamp, this program macro defines all of the instructions for your smart contracts, and then you have the corresponding data structures for all of your context. So we're just going to delete everything related to the counter and just have the basic setup for an Anchor smart contract. So that's using the Anchor lang import. It has your declare ID with your program ID of the smart contract. And then this is where all of your instructions are going to live. Now, what we need to do is rename everything from counter over to vesting. So let's start by updating the name of this program to vesting. And then we're going to navigate into our cargo file. So the package name is counter still, so we'll update this to vesting. Okay. And then let's see, we're just going to Command Shift F and see everywhere else that counter is written. And we just want to update that. So it's going to be in quite a few places. This will take just a second. Anything related to the TypeScript files for our web app, we're just going to deal with later when we start working on the front end. So all of this we can just ignore for now. So now we have to set up our cargo TOML for this program. And in our vesting contract, we're going to be moving SPL tokens around, as well as using a Solana program. So we're going to update our dependencies in our cargo TOML to use both of those crates. So we can just open up our terminal and run cargo add. And we're going to add first our Anchor SPL. Sorry, we actually need to navigate into our Anchor directory. So one thing to note whenever you're using the Create Solana DApp scaffold is everything related to the Anchor smart contract lives in the Anchor folder. So whenever you're running Anchor commands or any of your cargo commands, it has to be done in the Anchor folder. So we'll cd into Anchor, and now we can run cargo add Anchor SPL. Okay, so you can see our dependency updated with Anchor SPL. And now if you're following along, depending on the time that you're following along, this might have a different version. So if you want to make sure that everything stays consistent with the rest of this tutorial and make sure all the dependencies are compatible, I would recommend using the dependency versions that we have here in our cargo TOML. So now we'll also add in the Solana program. So we'll do cargo add Solana program. And if you want to specify a specific version, we'll just do that at for the version that we want. So we're going to use 1.18.17. Okay, and now our Solana program is updated. And now another thing that we're going to need in our dependencies is the init if needed feature for Anchor link. So I'll explain what this does later on when we're actually using it, but for now, let's just get our cargo set up. We're going to do cargo add Anchor link and add the feature flag. And this will just be init if needed. Okay, and you can see that the dependency was updated with the feature init if needed. And one last thing to update in our cargo TOML is our IDL build feature. So because we're using the Anchor SPL crate, we also need to update our IDL build to work with Anchor SPL. So in our IDL build, we'll just add Anchor SPL -IDL build. Now our cargo is up to date and we can navigate back to our librs. So let's think about what we're building here. We're doing a vesting contract, and as we explained in the introduction, is we have two perspectives. We have our employee perspective and our employer perspective. So first, we're going to think about the employer. We're going to be creating a vesting contract, so we have to initialize that, and then we also have to add in the ability for the employer to add employees. And then lastly, we need to allow for the employees to be able to claim their tokens once they have vested. So let's start with initializing a vesting contract. So we can first define the instruction within our program macro, and we'll just do pubfn, and we'll name it create vesting account. Whenever you're defining an instruction, you always have the first parameter is going to be your context. So we're going to just define the context, and then we're also going to want to create a custom data structure for this context. So we'll name that data structure create vesting account. And it will return a result. And then we'll write the logic for our instruction, but first we need to define what this data structure is. So outside of our program macro, we can go down here and we'll use derive accounts. and we're going to just define the struct. So pub struct, and this will be create vesting account. And we need to make sure we use the lifetime specifier. So what this context is doing is it is passing through all of the accounts that are needed to process the instruction that you're writing. So let's explain all the accounts that we need. First, we need the signer. So we'll write an account, and we need that to be mutable because the signer is going to be paying rent. So their account state is going to be changing when their balance of SOL changes. So we'll name them signer, and then the type is going to be a signer with the lifetime specifier. Okay. So one thing to note when we're writing all of our accounts is that with Anchor, each account used in a transaction, it's declared in a context structure with specific traits, and these traits dictate how the account can be accessed, like mutability, which is why we needed to specify the mutability for the signer because their account state is going to be changing, and in Rust, as you know, all variables are immutable by default. So here, when we define our account macro, we're going to have to specify all the constraints for the next account that we're writing. And we're going to be defining our vesting account, which is what we're creating with the instruction. So because we're creating the vesting account, we want to use the init constraint to specify that we're initializing an account when we're writing the instruction. So let's use our account macro. And then inside, we're going to first specify a init. Now, whenever you're initializing an account, it's going to be taking up space on chain, and that space you need to pay for in rent. So we need to be able to calculate the space. So we can just define the space constraint, and we'll do the anchor discriminator, which is 8. And then we have to be able to calculate how much space that it's going to take up. And that's going to be defined by what you're actually putting into this account struct. So one thing that we do need to specify is what is this vesting account going to be? This is a custom-made account, so we're going to pause from writing this data structure, and we'll just go down to define what our vesting account is actually going to be. So on Solana, all smart contracts are stateless. Every state is stored within accounts. So here we're creating a vesting account that is going to store all of the information for a specific vesting smart contract. So what do we want to store? We're going to first define that it's an account. We're going to use the account macro from Anchor. We're going to name this vesting account. Okay. So this is a vesting account for an employer for all of their employees at a company. So what do we want to save here? First, we want to know who the owner is. So that's going to be whoever has special permissions to update the vesting account. So we'll save the owner, and that'll just be the public key of the owner. And now we're going to be distributing SBL tokens. So we want to save what the mint is for the SBL token. So that will also be a public key. And now this is just an account that's storing state. We're also going to need an account that's storing the SPL tokens. It'll be a token account. So we want to be able to store what the public key of that token account is within our vesting account state. So let's just do public key, we'll just do pub treasury token account. This is just going to be the treasury account of an employer's tokens that are all going to be allocated to employees that are working and receiving vested tokens. So this will be the treasury token account. The type will be public key. Okay. Another thing that we'll want to store, just for referencing, maybe creating a PDA in the future, is the company name. So we'll write company name. And that'll just be a string that can be a user input value when they're creating their new vesting account. And then we also want to save the bump, and we'll save the bump for both the treasury token account as well as the vesting account. So we'll do bump for treasury. And that's always a U8 type. And then just the bump for the vesting account, which is also a U8 type. So now we have the account, but how are we going to actually calculate the space? Anchor actually has a way to do that. So this account macro It is an attribute applied to the data structure to designate that it's a Solana account. And then we can also add the derive macro, and it's an implementation onto this account data structure. And we can specify that we want to use a init space. So we'll just do derive and then a init space. And what this does is Anchor automatically calculates the space for you. Now you can see that when I wrote that, we have an error that was generated. And that's because the company name is a string value, and a string can be extremely long. So we're going to want to designate a max length for what this string can be. So I can just go in here and actually write max length. And I'm just going to say 50. Seems good for a name. Now that error went away, and now we have our account fully defined. So now that we have that, when we're calculating the space in our create vesting account struct, we can just use the init space. So that's going to look like just the name of the struct and then a init space. Okay, so now that we have the space calculated, we need someone that's going to pay the rent. So we just have to define who the payer is. And that's going to be the signer of the instruction. And now we're creating a new account. So since we want to be able to derive the PDA in the future, we need some type of attribute that differentiates the different PDAs for a specific signer. So here we're just going to use the company name. So we can do seeds, and we'll use the company name as ref. Okay. And then lastly, because we have the seeds, we need the bump. And then we're going to just need to define what this account is. So we'll name it vesting account. And it will be an account with the lifetime specifier, and it's going to be using the vesting account struct that we defined right here. Now, there is an error, and the reason for that is because we're passing through a company name, and this struct doesn't know what it is. So yes, we need to update the input parameters from the instruction first, and just say we're allowing on the front end someone to type in what the company name is. That'll be of type string. But this still isn't passed through down here. So to be able to pass this information through our context data structure, we're just going to add this macro that is basically saying we're pulling this variable from the instruction. So we'll do the instruction and then name the variable. So we're using the company name of type string. Okay. The next thing we're going to pass through is just the mint account, and that's going to be what the SPL token mint is for the vested token for this specific vesting account. And we're going to be using interface accounts here. And it will be a mint type. So we need to import this mint, and this is coming from our SPL token crate. So you can see here, Anchor SPL token, mint. But actually, we're going to be using the token interface rather than the token. So we'll go down to Anchor SPL token interface mint and import that. So you can see the import updated. And you can see the vesting account still has an error, and we'll get to that in a second. But basically, whenever you initialize a new account on chain, you do need to pass through the system program. But we'll pass that through towards the end. So far in our context data structure, we're passing through the signer who is signing the instruction. We're passing through the vesting account that we're creating to hold all of the state for the new vesting account. We're passing through the mint of the SPL token that we're vesting. Now, we also need the treasury token account that's going to store all of the tokens that are going to be handed out to employees. So we can initialize that at the time of running this instruction. So we're once again going to use the init constraint on the account. And now here, It's going to be a little bit different because it's a token account. So we're going to need all of the information for the token. We can do that by running the token constraint, and we'll define what the mint is for the token. And that mint is going to be the mint that we just passed through above on the previous account. Okay? And now we also need the authority for the token. And that authority is going to be the token account itself. So in the future, when we're actually transferring the tokens, the token account has the ability to transfer to the employees. So we'll set the authority to the treasury token account, which is what we're going to name this account. Okay. And now we just need the payer, which will be the signer once again. And then here we're going to define the seeds. This is going to be a token account, not an associated token account. This is because it's going to be a token account specified just for this vesting contract. So we want to create seeds for the PDA that will make it easy to derive. So we'll make the seeds state that it's the vesting treasury. And we can do that by just typing out vesting treasury. And then we'll also want to add in the company name as ref. Okay, a little typo, let's fix that. There we go. And now because you specified the seeds, we also have to add the bump. And now all the constraints are defined, so we just want to state what this account is, and that will be our treasury token account. And now we're going to update this to an interface account. And then the type will be a token account. So now we have our treasury token account, our vesting account, we have the signer, we have the mint. So all that's left is two things, our system program, and then the token program because we're creating a token account. And this token program is actually going to be an interface, and we're going to use token interface. And now you can see we have one more error left, and that is we need to import token account. So we'll just import that, and that's going to come once again from the token interface. Okay. And because we're using a string here with vesting treasury, we're going to update this. Instead of as ref, it's going to be as bytes. And that's everything for all of the accounts that we need for the first instruction to create a new vesting account. So now we can write the logic out for creating a vesting account. And you can see here, there's a warning generated for a company name, and that's just because we haven't used it yet in the logic, and Rust always wants to warn you if you're passing through a parameter and it's not being used. So the first thing we're going to do is just load in the vesting account, and we want to be able to update the state. So because the context holds all of the accounts for this instruction, all we can do is just load in the context dot accounts, and we can point to the vesting account. Now what we need to do is we need to dereference this. So we can add this asterisk, and that is a dereference operator in Rust. And what that does is it dereferences the account that it's pointing to, which is the vesting account in our case. And it allows you to modify the account. You need to do this because it's an account reference. You need to dereference it to be able to modify it. And this tells Rust that you want to work with the actual data and not just the reference. So now you can update values of the actual data of the vesting account. Now we'll just pull in the vesting account type. Okay, and then we can just update all of the fields within vesting account to save the information for the new account that we're creating. So first we'll do owner. And that will just be the key of the signer. So we can pull in the signing account and then just grab the key. Now we need the mint. And we'll just pull in the mint account and grab the key. Now we need the treasury token account. Once again, we'll pull in the treasury token account, grab the key. And then the company name is just going to be the company name that's passed through. And then we'll just grab the bump of both the treasury and the vesting account. Okay, sometimes Copilot tries to autofill things and it's not always correct. So we're going to fix what Copilot just wrote. And we're actually going to pull this in by doing ctx.bumps. And we're going to pull the bump of the treasury token account. Okay, and then we need the bump for the vesting account. So ctx.bumps.vesting account. Okay, and I spelled account wrong, so we'll just fix that typo. There you go. And then we're just returning an OK for our result. And that's everything we need for our first instruction. So you can see that most of the logic here happened within our create vesting account data structure because that's where all the accounts are handled. So if we go back down to our create vesting account, you can see we've set up both our vesting accounts and a token account for the treasury. And then the logic within the instruction is just saving all the information that we need to the account state of the vesting account. So first instruction is done. Now we can move on to the next. So not only do employers need to have a vesting account, but employees need to have a vesting account as well. And that's going to hold different information. It's going to hold all the information for their vested tokens, like the cliff time, how many tokens they have allocated to their public key, and anything associated with their token vesting. So that's going to be input by the employer of what their specific allocation is, and then the employee needs to be able to access that to be able to claim their tokens. So let's create the employee vesting account. Now, because we're creating a new account, let's define what is being saved to the state. We're going to do the same thing that we did with our vesting account by defining what the account is. So we'll use the account attribute that just tells that this is a Solana account. Okay. And then we're once again going to use derive init space because we need to calculate how much space it's going to take up on chain. Okay, and then we'll just define what this struct is. So this will be the employee account. So what do we want to save here? We want to know who's going to be able to claim this. So let's define what the beneficiary is. And that'll just be the public key of the employee for this specific account. So typically when you create a vesting account, you want to keep track of when the allocation started, when it's going to end, and what the cliff time is. So let's define all of that first. So the start time. Now this is all going to be stored in Unix time, which is an I64 type. The end time, also an I64, and then the cliff time. And what the cliff time is just how much an employee has to wait before any of their tokens unlock. And then once the cliff passes, it typically unlocks linearly after. Now, we'll also want to keep track of the vesting account. And this is just the corresponding vesting account that was just created by their employer. So that will be a public key because it will be the account address. And now we just need to know how many tokens are being allocated to the employee. So we'll do total amount. And that will be a U64 type. And then we want to keep track of how many the employee has withdrawn from their account. So we're able to calculate at a specific time how much they're able to either claim or how much they still have left to claim in the future. So total withdrawn. And that'll be a U64 type as well. Okay, so that's everything we're going to be storing to the state for the employee account. Now we can write the instruction to create this. So pub fn, and now we're going to create employee account. Okay, so we'll pass through the context as our first parameter, as always, when writing an anchor instruction. Define as a context type, and then we're going to create a data structure for create employee account. So let's pause from this instruction and go down here to write our derive accounts data structure. So pub struct create employee account. Add in our lifetime specifier. So now we want to know who the owner of this employee account is going to be. So the owner is actually going to be not the employee, but the employer, because the employer is going to be the person who has access to update the allocation information for a specific employee. So that's why we're going to update. The signer is going to be the owner. And once again, it needs to be mutable because we're creating an account, so the signer has to pay rent for that account. So we're going to set the signer as the owner. Okay. Now we also need to know who the beneficiary is, which is the employee that's going to be able to claim tokens later on. So let's pass through the beneficiary account. And that'll be a system account. And we'll add in the lifetime specifier. Okay. Now we need to pass through the vesting account. And that is because we're going to need all of the information from the vesting account state. But one thing we want to do is we want to use the has one constraint to just make sure that the owner of the vesting account is the signer of this instruction. And that's just validating that the person with the correct access is going to be able to run this instruction. So we'll do the account attribute and add in the has one constraint. And set that to owner. So now we have to actually create the employee account. So we're going to use, once again, the init constraint on the account. So account init. And this is just an account that is holding state, so we don't need to use the token constraint. And we're going to specify what the space is. We'll use the 8 discriminator from Anchor. And then we can just use a init space to calculate the rest. So employee account, init space. And then because we're taking up space, we need to pay rent. So we need to define who the payer is. And then we're going to define the seeds for our PDA. So here, let's use employee vesting. And then we're going to add in the beneficiary key as ref. And then the vesting account key as ref. And now that we have seeds, we also need a bump. And then all that's left is just to name what this account is. So it'll be our employee account. Okay, and now we have an error here. And that is because we need to define the system program whenever we're initializing a new account on chain. So we'll pass that through, and now our error went away. And that's everything we need for an employee account. So we can go back to the instruction and finish the logic there. Okay. So we'll load in the account the same way. We need to dereference, call the context accounts, and employee account this time. We'll use the employee account struct. Okay, and now we need the beneficiary is the first field. And that will just be the context accounts beneficiary key. And we have a typo. It's accounts with an S. There you go. And now we need the start time and the end time, but we don't know what that is. So we want to update our parameters to include start time and end time. And this will be passed on the front end. Okay, so we have our start time, we have our end time. Now we also need to pass through the total amount. So let's add that. That's a U64 type. Okay, and then the total withdrawn, since we're initializing a new account here, it's impossible to have withdrawn anything, so we'll just set that to 0. And then we need the cliff time, we'll pass through as a parameter. And now we need the vesting account, and we'll just pull in the account's vesting account key. And lastly, let's save the bump. Now this will be the bump of the employee account, so we can just do ctx.bumps employee account. Okay. And now we just need to return OK. So now we have an error, and it's saying there's no such field as bump, which means we forgot to define the bump in our employee account state. So we'll just go here and add that field because we always want to save the bump. There we go. So everything's good for creating an employee vesting account. Now, the last instruction that we need here is allowing the employee to come and claim tokens. So this will have a little bit more logic to make sure that an employee can claim tokens at the correct time. So let's start by defining this instruction. We'll do pub fn claim tokens. Okay, so we'll pass through the context as the first parameter, and then we'll go down and define what that is. So claim tokens. And now we can do derive accounts for claim tokens. So this will pass through all of the accounts that are needed for an employee to be able to come to this program and claim tokens. So first we need the signer of the instruction. And in this case, instead of it being the owner of the vesting account, we want it to be the beneficiary of the employee account. So we'll update this to account. It needs to be mutable. And it will be the beneficiary, and that will be the signer of the instruction. And next we need the employee account. So we can define the account. And here we're going to need to update information in the account state because we'll be updating total withdrawn if an employee withdraws tokens. So we want to make the account mutable. And now we need the seeds. So this will be the same seeds from the employee account. So just to make things easier and make sure we have all of the correct information, we'll go back to when we initialize the employee account and just copy those seeds over. Okay, so this is employee vesting, the beneficiary, and the vesting account. And now we need the bump, and because we saved the bump when we were initializing, we're able to just pull that information. So we can do employee account dot bump. Now we're going to need to do 2 checks on this account. We want to make sure that it has the correct beneficiary, so only the employee that is the beneficiary of this employee account is able to come in and run the instruction claim tokens. And then we also want to make sure that this is connected to the correct vesting account that's being passed through. So we'll do has1 beneficiary, and we'll also do has1 for vesting account. Okay, so we'll just define this as the employee account. Now there's a few things here that we haven't defined yet. So the beneficiary was already passed through as the signer, but we need to define the vesting account. And the vesting account is used twice, so we want to just make sure that that account is passed through so it's able to pull the correct information. So let's pass through vesting account next. And we need the seeds for the vesting account. And we'll just do the same thing. We'll go back to when we initialize the vesting account and copy over the seeds. And then because we saved the bump to the vesting account state, we can just grab that information. And then we're going to do 2 checks here as well. So we want to make sure that this vesting account has the correct token account that's being passed through, and that is the treasury token account. So when this claim happens, it's going to be transferring SPL tokens from the treasury account into the employee token account. So we need to pass through the correct treasury account to be able to pull those tokens from. So we'll do has1 and the treasury token account. And then we also want to make sure it has the correct mint address of the SPL tokens. So we'll do has1 mint. So then we'll just define this account, and that's the vesting account. Now, there's a few things that we haven't defined yet. So one is the company name. Now we're going to have to pass through the company name as a parameter from the instruction. So let's go back up to the instruction, and let's add in company name here. And then for this data structure to be able to recognize that information, we have to pass through our instruction with the company name. Okay, so now you can see that error went away. Now we need both the treasury token account and the mint account to be passed through. So let's do the mint next. And that will be an interface account, mint. Now we need the treasury token account. So this also has to be mutable because we're going to be changing the token account balance. And all we have to do is just define what this is. So treasury token account, it's an interface account, token account. Okay. And now you can see both of those errors went away and all the accounts are passed through. Now, what else do we need? So we have the beneficiary, we have the employee account, we have the vesting accounts, we have the mint, and we have the treasury token account. So it seems like there's one important thing that's missing, and that is the employee token account. So we have the account state for the employee, but we don't have where the tokens are going to be sent to. So what we can do is create an associated token account. And this is where the init if needed constraint is going to come into play. So let's first define the account. And instead of init, we're going to use init if needed. And that's because some users may already have their token account for the specified SPL token created. And if they do, it's going to just bypass the init constraint and continue with the rest of the logic for the instruction. But if they don't already have this initialized, this account will then become initialized after running the instruction. Now we'll need the payer because it has init if needed. So if the user doesn't already have this account initialized, then we need a payer to be able to pay rent for the account. Okay, so in this case, the payer is going to be the beneficiary because it's their associated token account. Now we're going to just define what the associated token account is. So we'll use the associated token constraints. And first we want the mint, and that'll just be the mint address of the mint account that we're passing through. And then we also want the authority. And that'll be the beneficiary because it's their own token account. And then we also need to define the token program. So associated token, token program, and that will just be the token program. And now all that's left is to define what this account is, and this will be our employee token account. And because we're using the token interface, this will be an interface account, token account. Okay. Now, one thing is missing is what is the token program? So let's define that. And the token program is an interface, token interface. And now because we're using the associated token constraint, we also want to pass through the associated token program. And this is associated token. And then lastly, because we're potentially initializing a new account, we want to pass through the system program. Okay. And now that error went away. And this should be all of the accounts that are needed for claiming a token. But let's just double check. So we have our beneficiary, which is the signer. And we want to make sure that the beneficiary is the signer because we only want the beneficiary of the specified employee vesting to be able to claim tokens. And then we have the employee account, and that is just all of the state of this employee's vested token information. We're doing a check to make sure the correct beneficiary is signing, and also it's connected to the correct vesting account to grab the information for the mint and the company. Now we have the vesting account being passed through. We're checking the treasury token account is passed through correctly, and that's needed to be able to pull tokens from to send to the employee. And then we have the mint, which is to know what SPL token we're sending. Now we're passing through the mint account. We're passing through the treasury token account. And then we're creating, if needed, an employee token account, and that's the token account that's going to claim the SPL token for the vested token. And then just the token program, associated token program, and system program need to be passed through. Okay, so that looks like everything. Now we can go back to the logic needed to claim tokens. We can return the result. And I like to always, before writing all of the logic, just have our OK return value at the end so Rust doesn't get angry with us and have a bunch of errors as we're writing. First, we need to load in the employee account to get all of the information for the vested token. So let's load in the employee account. And here we're going to do a mutable reference. That is because we need to specify that the referenced account is going to change information. And let's do ctx accounts.employee account. Okay, so that loads in our employee account. It's being stated that it's a mutable reference. Now, earlier when we loaded accounts in, we used the dereference operator, but here we're using a mutable reference. So let's talk about the difference between the two as we're writing this out. So dereferencing is used when you need to manipulate the actual data stored in the reference location, and it's kind of less common at a high level operations, and it's mainly used when you're initializing or resetting account data. Earlier, we were initializing two accounts, so we were using the dereference operator. But here we're borrowing a mutable reference, and this allows you to pass employee accounts around in your function or to other functions while still having the ability to modify the original data. And this is useful when you're using multiple operations on the data, which we're going to be doing as we're calculating to be able to claim tokens. When you're claiming tokens, the first thing you want to know is the current point in time, so we can know if an employee is able to claim tokens or not. So let's first use the clock to figure out what the time is. So we'll do now is equal to clock.get, and we'll unwrap, and we need the Unix timestamp. Okay. Now we want to check if the current time is before the cliff time, because if it is before the cliff time, then no tokens can be claimed. So if now is less than the employee account dot cliff time, we want to return an error. And now we're going to create a custom error for this program. And we'll name it claim not available yet. And it's always important to define custom errors when you can, because it allows a user to understand more of why they're getting an error when they're interacting with the smart contract. So we can define custom errors by using the error code macro. from Anchor. So we'll just do error code. So this error code attribute, it's applied to the enum that it's attached to generate a result type T or an error type. So that's used to return errors for the program. Okay, and we're using an enum here because you're only going to be calling one error at a time. Okay, so we'll do claim, We'll copy in the error that we specified just to make sure everything matches. Okay, and we can add a message that's going to be displayed for the user. So we'll do message, claim not available yet. There we go. And now you have a custom error in your program. Okay, so next we're going to have to start doing some calculations, but when you're running calculations in Rust, we have to add some additional checks. So we need to take into consideration both underflow and overflow errors. Underflow occurs when calculations result in a number that's smaller than the minimum value that can be stored in the data type. And overflow occurs in the reverse, when a calculation results in a number that's larger than the maximum value that can be stored in the data type. So we're going to use specific methods when we're writing out these calculations. So let's first calculate the amount of tokens that are able to be claimed. First, we're going to define the time since the start of the tokens being vested. So we'll do time since start. And we'll do now. And instead of just subtracting, we're going to do a saturated sub. And what that does, it just ensures that the subtraction doesn't go below 0, which can help prevent underflow errors. So we'll do .saturating sub, and we'll be subtracting the employee account start time. And this is an I64 type because it's in Unix time. And now we need to find the total vesting time. So we'll do let total vesting time. And this will be the end time minus the start time, which gives you the total time period that the tokens are vested for the employee. So employee accounts dot end time, and we're going to subtract using saturating sub, and that will be subtracting the employee account start time. Okay. Now we're just going to do a little bit of error handling first. So we want to check to see that there is a total vesting time. So we're going to do, if the total vesting time returns 0, then the vesting period was invalid for the employee. So let's just do that check first. So if total vesting time is 0, and this is also going to help with calculations in the future because we don't want to divide by 0 anywhere. So if total vesting time is 0, it will return an error. And we'll once again write a custom error code. So we'll do error code. Invalid vesting period, we'll call it. And now we'll just add that to our custom error enum. So we'll go down to the error codes enum and add invalid vesting period. And we'll add the message. Okay. And we'll go back to our instruction logic. Okay, so now we want to know the total vested amount of tokens, which is the total amount of tokens that the employee can claim. So we'll do let vested amount equal. Now, if the current time is after the end time, then all of the tokens have unlocked. So let's do a check for that. So if now is greater than or equal to the end time then we're going to just return the total amount. And then else, we're going to do a match statement. And that's because we want to make sure that all of the calculations are safe and we're handling possible errors. So we're going to type it out like this. We'll do match, and then we'll take the total amount and multiply it by the time since start. So employee dot total amount. Employee account dot total amount and we're going to use checked multiply. So checked multiply is a multiplication, and the checked prefix allows you to handle possible overflow errors. So checked multiply and we're multiplying by the time since start. Because the time since start is an I64 type because it's in Unix time, and the total amount is a U64 type, we're going to cast the I64 as a U64. And you can do that by just typing as U64. Because whenever you perform any calculation against variables in Rust, they have to be of the same type. Now, we'll do sum if the product of this multiplication we're just going to divide the product by the total vesting time. So what we're doing is we're taking the total amount, multiplying it by the time since start, and then dividing that by the total vesting time. Okay. And then if there's a none value. So the reason we're able to do this is because checked multiply, if there is an overflow error, instead of panicking, it returns a none value. So here we're just doing a check in our match statement. If it returns a value, we're going to be able to divide. If it returns a none, we're going to have to handle that error. We'll just return an error. And we'll make another custom error. And we'll name this one calculation overflow. And then we'll go back down to our error enum and add in the calculation overflow error and add a message. Okay. Okay, 1 second. My VS Code is being a little slow to update, so we'll just let that update. Okay, so just to recap this calculation, if we didn't perform a match statement here to check the product of your multiplication, then this checked mul is just going to return a none value, and then we wouldn't be able to do the division by the total vesting time. So by implementing the match statement, you're able to check to see if there's a product returned, and if there is, then you do the division. If there isn't, then you're handling the error of a none value being returned. Okay, so that looks good to me. Now we want to find what the claimable amount is for the user. So we found the vested amount. So this is how many tokens at the current point in time are unlocked. But if a user came in earlier and already claimed some, we want to be able to handle that. So what we're going to do is find the claimable amount by taking the vested amount and subtracting the total withdrawn value that's stored in the employee account state. So we can do let claimable amount So we'll do the vested amount, and then once again use saturating sub. And we'll do the employee account total withdrawn. Okay. And now a little more error handling. If the claimable amount is 0, we want to be able to let the user know that they have nothing to claim at the current point in time. So we'll do we'll do if claimable amount equals 0, then we're going to return an error of, and we'll do the error code, and we'll make a custom error called nothing to claim. And then we'll update our error code enum down here with our new custom error. So VS Code is being a little slow to update. All right, there we go. Now the error went away. Now we did all the calculations needed. So we now know what the claimable amount is for the user. And now that we know what that is, we can actually process the claim. So by doing that, all we're going to be doing is a transfer of SBL tokens from the treasury account into the employee's token account. So we can do that by making a CPI call. A CPI call, it's a cross-program invocation, and it allows you to make calls from another program. In our case, the transfer is from the system program. So we can do let transfer CPI accounts, and we're going to define all the accounts needed for this transfer to take place. Here we're going to use transfer checked. And we want to make sure this has the correct import, which VS Code is once again still being slow. So instead of using the quick import, we're going to manually import. Looks like there was a weird import generated. Okay. So all we're going to do is update our token interface from the Anchor SPL crate to include transfer checked. Okay. Now we can go down here. And you can see from the structure, we need from, mint, to, and authority. So we'll define all of those fields. From, so the tokens are going to be coming from the treasury token account. So we'll load in the context accounts treasury token account to account info. Now the mints is the next parameter. And we'll just do the mint account. And then we have to, and we have the authority. And in this case, the authority is going to be the treasury token account. And that is because when we earlier initialized the treasury token account, when we used the token constraint on the account attribute, we specified that the authority was itself. So here we can just set the authority to itself. Okay. So those are all the accounts that are needed for the transfer. Now we can define the CPI program. So let CPI program equal, and that is going to be the token program. So the transfer instruction that we're calling from the cross-program invocation is coming from the token program. The next thing we're going to have to do is define the CPI context. But first, to be able to sign the CPI context, we need to define what the signer is. In our case, we had a PDA for the treasury token account. So we need to now derive that PDA to create our signer seeds. So let's do signer seeds. And the signer seeds have an interesting type. So we're going to explicitly define that type here. And all it is a few references. So 1, 2, 3, and a U8 type. Okay. So now we can go back to what our seeds were, which is for the treasury token account. When we created it, let's go to that context. Right here. So I'm just going to screenshot this so we can reference it and make sure we have the correct seeds. So we've first had our vesting treasury. Vesting treasury. And then the next field was the company name. So we can load that in from our context. So we can do context.accounts dot, and the company name was saved in our vesting account state. So we're going to use the vesting account. And then within the vesting account was the company name. And then lastly, we just need the bump defined. So we're going to reference the context.accounts. This is for the treasury accounts, and we saved the treasury bump into the vesting account state. So we're going to call in the vesting account. And then from that, we're going to pull in the treasury bump that we saved to the state. Okay, so one thing we were missing was adding a reference to the seeds. So we'll add that in. And now we'll just double check. We have our initial reference. We have the second reference for the seed. And then we have the last reference for the bump. Okay, and actually the bump lives inside of this. Okay, there we go. So now we have 3 nested references. And that is our signer seeds for the treasury token account. Now that we have that, we can define our CPI context. And this will be a CPI context new. And the first parameter is going to be the CPI program. And then we need the accounts. And now we need to specify that it's with signer because it is a PDA, so we need the signer of the PDA. So with signer, and this will be the signer seeds that we just derived. Now, lastly, we need the decimals of the SPL token that we're transferring. And that we can just take from the mint account that's passed through. So we can do context.accounts.mint. And then decimals. Okay. Now we can actually process this CPI. So we're going to use the token interface. And we'll do transfer checked. And we'll pass through the CPI context, the claimable amounts, and the decimals. And now let's make sure the claimable amounts is of a U64 type. So we'll just we'll cast as a U64. Okay, it looks like the signer seeds type may be off. So we're just gonna update the spacing here so it's easier to read. So we have our signing seeds and we have our reference. Oh, okay, we're just missing a comma here. There we go. Okay. Now we need to import the token interface. So the token interface is coming from the SPL token interface. We'll update the interface here. So this should just have self. Okay. Now we performed our CPI of transferring tokens from the treasury token account into the employee token account. And all we have left is just to update the account state for the employee to reflect that we've withdrawn tokens. So we'll add employee account dot total withdrawn and increment that by the claimable amount. And there we go. So that is everything for our instructions. Now, one thing to notice is in our parameters, we have company name and it's returning a warning. And that warning is because the company name is not being used within the instruction logic. But we need to tell Rust that we know it's not being used, but we're using it somewhere else. So to do that, we're just gonna add an underscore here. So just to recap, we've created vesting accounts for the employer. We've created employee accounts for the employee to be able to claim their allocated tokens. And we've created an instruction for employees to be able to come to the UI and grab the tokens that are claimable. So now let's do an anchor build to make sure that the program builds. So we need to remember to be in our anchor folder to do any instructions that are related to anchor. Okay, so we can run anchor build. Okay, so we can see that the code compiled. Everything's good to go. There was a warning generated. So this is just trying to help with formatting. So we can go and make that update with the warning. If we go to our match statement, there were some parentheses here that just aren't needed. So we can get rid of those. Clean that up a bit. There we go. Okay, so we can just one more time run anchor build. It'll be a lot faster now that it's already compiled once. So now that we've built our new program and everything compiled correctly, we can start testing. But first, let's go over everything that happens within this anchor folder. So when you run anchor build, it updates the target folder. So you can see here, the target folder is now green, meaning there are new files generated. And we can go into our IDL, and now there's an IDL created for the vesting contract that we just wrote. We have this counter IDL from the previous counter program that was generated with the scaffold, and we can just delete that because we don't need it anymore. And we'll just keep the vesting IDL. Now, there was also a types file generated. We can once again delete the counter file. And what this vesting types, it's a TypeScript file that's compatible with your TypeScript that uses the program IDL. These two are going to be using for both our testing and our front-end application because both of those are going to be written in TypeScript. Now, all of that's done. So let's start with our tests. There is a counter test that's already generated. We're just going to delete that because we no longer have the counter program and we're not writing normal TypeScript tests. We're going to be using Bankrun here. So let's get everything set up for our Bankrun tests. So what this does is it creates a Banks client and a Banks server and runs our tests against it. Now, we're going to have to specify the path of our program to be able to deploy the program to the Banks client and run the test correctly. So let's make a fixtures folder inside our test folder. And what that'll do is we'll just import our vesting.so file. So if we go back to target and we go to deploy, you can see our .so is generated. So we're just going to copy that and paste it into the fixtures folder. And this just allows the bank run test to be able to easily access our .so file of the smart contract that we just wrote. And just to clean up a little, you can see the counter key pair, anything counter related. If you see it, just delete it. Okay. Now inside our test folder, we can create a new file, and that's going to be our bank run test. So we'll do bankrun.spec.ts. Okay. Now there's a few packages that we're going to want to install to be able to use bankrun. So in our Anchor folder, we're going to npm install. And we want, let's see, what do we already have? We'll go to our package.json. And we have Anchor, we have web3.js. So now we also want to add in the SPL token. So we'll do @solana.spl token. Okay, so you can see there's some dependency issues. So what we're going to want to do is define a specific version. So we're going to do @Solana SPL token, and we'll do .4.8, and we're going to update our web3.js to 1.94.0. Okay, great. Now we're going to install Anchor bankrun. Okay, and that'll be version 4.0. And now we're going to install Solana bankrun as well. Okay, and that'll be version 2.0. We're going to update the version here. So this is just making sure we have compatible versions for all our dependencies. And then because we're going to be using the SPL token when we're testing, we want to also use the SPL token from bankrun. So we'll npm I SPL token bankrun. Okay, and this one, we're also going to update the version to 2.5 instead of 2.6. So let's see, we have our Coral Anchor, we have Solana SPL token, version 4.8, we have web3.js version 1.94, we have Anchor bankrun, Solana bankrun, and SPL token bankrun. Okay, so those are all the dependencies we need for our bankrun tests. And let's just make sure everything's properly installed. Okay, great. Now we can go back to our bankrun file and start writing our tests. So first thing, we're going to just set up our test. So we'll do describe, and then we'll name the test vesting smart contract test. Okay. Before we start actually running the test, we first want to start with our environment setup. So in our environment, we want to make sure we have an SPL token mint that we're going to be using with the proper authorities. We also want to make sure we have the right programs deployed to be able to test our vesting contract properly. So let's set up our environment first. So we're going to do that by using before all. And what this is going to do is run these specific functions before every single test is being ran. So this is going to be an async function. Okay. Now, within the bank run test setup, you have a wallet with a payer that is already funded and ready to be able to work. But in our smart contract, we have two different scenarios that are being tested. We have the employer perspective as well as the employee perspective. So we'll keep the default native wallet within the test to be for the employer. But now we have to set something up for the employee. So let's name this beneficiary. And we're just going to generate a new key pair. So we'll do new anchor dot web3 dot key pair. Okay. So we need to first define the type. So outside of our before all, we're just going to let beneficiary be of a type pub key. Okay. And this is TypeScript, so the type is actually public key, not pub key. We're not in Rust anymore. Public key. Okay. Now let's fix our imports. So we're going to make sure we import public key from Web3.js. We also want to import anchor. So we'll define our first import here as anchor, and we're going to fix Copilot suggestion, and this should be from Coral XYZ anchor. Okay, and now we have a typo in key pair, so let's fix that. There we go. And this is actually a key pair, not a public key. So there you go. Now, one thing to note, the difference between a key pair and a public key, the key pair has both a private and public key attached, so you're able to sign with it. And because we need the beneficiary to be able to assign instructions, it needs to be of a type key pair to be able to sign those instructions. Okay, and we're just updating our imports. We'll just keep the public key import there because we will be using that in the future. So we've defined the beneficiary. So next we're going to define our context for Bankrum. So we can do that by await start anchor. Now we'll define what the context is. And the context is your program test context. So program test context. And we'll import that. So the quick import isn't showing up, so we'll manually write that. This is going to be an import from Bankrum. So we'll do import program test context from, and this is going to come from Solana Bankrum. Okay. So we'll be defining our context. We're going to do that with start anchor. And what start anchor does is it starts a bank run in an anchor workspace with all of the workspace programs deployed. And it spins up a bank server and a bank client, deploys the programs and all the accounts that are added. So let's import start anchor. And that's going to come from Solana Bank Run. And let's update our program test context to import correctly. Okay, there we go. Now we're going to update all of the parameters that need to be passed through for start anchor. So start anchor first has the path, which is the path to the root of the anchor project. And because we created this fixtures file with the vesting.so pasted into it, we're able to just make the path an empty string. And now the next parameter is going to be the extra programs. So the program that we need to deploy to bank run is going to be vesting. So we're going to set the name as vesting. And one thing to note when you're naming these programs, it needs to be whatever the name is of your .so file. So you have to make sure that those two values match or it's not going to pull the right program. Okay, so we have the name and we also need the program ID. So program ID, and this is going to be of a public key type. Now, when we created our librs, you have this declare ID with a public key. This is your program ID. When you run Anchor build, it creates an IDL, and within the IDL, you have an address. These two values should be the same. You can see that they are. And this is the program ID of the smart contract that we just wrote. So we can go back here and just pull that from the IDL. So we want to properly import the IDL. So we'll import IDL from, and it's going to be our target IDL vesting.json. That's the file path to get back to this file here. Now, in our program ID, we can just call that address. So we can do IDL dot address. Okay, and now we have a little typo. This should be on the other side. Okay, we passed through our parameters for the added programs. Now we need to pass through what our added accounts are. Now, we talked about earlier how we need to add a beneficiary account. With Bankrun, you already have a signing key pair that has both the public and private key with funded LAMP ports, and we're going to be using that for our employee. But now we have another perspective that needs to be able to sign instructions, and that's our beneficiary. So we generated the key pair for the beneficiary, but now we need to load that key pair in and make sure that it's funded with LAMP ports, so there are LAMP ports to be able to pay the gas fees when executing an instruction. So we can define that here. We'll first specify the address, and that will just be the public key of the beneficiary. And now we'll add in the info for this account. So this is just your typical info data structure. It's going to have the LAMP ports, and we'll just fund it with a bunch of LAMP ports. And then it's going to have the data, and then it'll have the owner, and in our case, it's just going to be the system program. So we can actually import the system program ID from Anchor. And lastly, the executable, which we're going to set to false. And now we're getting an error here, and that's because we have a typo in ID, so it's just camel case program ID. Okay, so that's everything we need for our context. And just to recap, we have our start anchor that has the path to the root of the Anchor program. We also have the programs, which is an array of the objects indicating which extra programs need to be deployed to the test environment. And we have accounts, which is just an array of accounts indicating the data that needs to be written to a certain address in this testing environment. So now we set up the context. Now we need the provider. So after context, we're going to define the provider. And this will be a new Bankrun provider. And the parameter is just the context that we defined in the previous step. Okay, now we need to make sure that first provider's type is defined. So provider is a Bankrun provider type. And then we just need to import Bankrun provider. And this is coming from Anchor Bankrun. So we'll do import Bankrun provider. From Anchor Bankrun. Okay, now that we have the provider, we need to set the provider. So we're going to do anchor dot set provider, and that will be the provider that we just defined. We have the provider, we set it. Now we need to define the program. So we have the program, and that's just a new program. And we want to make sure that it is matching the vesting IDL. So we'll add IDL as vesting, and we can import that vesting type from our TypeScript file that was generated. And the other parameter is the provider. Okay, so first let's define the program type. So program is program vesting. We want to import program from anchor. Now we want to make sure we already did an import of the IDL, but we also want the TypeScript compatible version. So we're going to import vesting from the target types vesting. And this is our TypeScript file. There's two things that we're going to be using a lot throughout our tests. So we're just going to simplify that by creating a variable for that. So one is the banks client. So the banks client. So one is the banks client, and the banks client comes from the context. So we can name banks client is the context.banks client. And now we'll define the type above. And that is a banks client type. Okay. And the next thing we need is the employer. So we talked about how the provider comes with a wallet that is already funded and has the full key pair of both the public and private key. So we can just name that employer, so we don't mix up our two signing keys that we have. So we have provider.wallet and then .payer. Okay. And then we'll define what the employer is up here. And that will be a key pair because it is a signing key, just like the beneficiary is. Okay, so far we've set up our environment with the needed accounts and programs. But we also need to have an SPL token mint that we're going to use as the token that we're going to be passing back and forth between our treasury accounts and employee accounts. So let's actually create a mint. And we need to create that so we have the mint authority to be able to mint tokens to the correct accounts. So we'll set mint, and we're going to await, and we'll create mint. Okay, and this is an import from SPL token bankground. So we'll add that import, create mint. From, this will be SPL token background. There you go. Okay. So now the arguments that are passed through for create mint, we have the banks client, we have the payer, we have the mint authority, the freeze authority, decimals, key pair, and program ID. So let's define all of those. And first, before we do that, let's actually define the mint type. So we'll go back up here and do let mint, and the mint is going to be a public key. So now we have the banks client. Okay. And then up next is the payer. And in our case, that will be the employer that we defined earlier. And then we want the mint authority. So that is going to be the public key of the employer. For our testing purposes, we don't need to freeze any tokens. So we're just going to leave that as null for the freeze authority. And then for decimals, we'll just put 2. And I have a typo in banks client, so let's fix that. There we go. I have a typo everywhere in banks client, so we'll fix all of them. Okay. Now, there's an error, there's a type error with the banks client. And you can see here that it is between the Solana bank run and the SPL token bank run. So this is actually within the dependencies themselves. So what we're going to do is just do a TS ignore because it does work between the two. So we'll add in at TS ignore. Okay, now there's just a few more things to do to finish setting up our test environment, and then we can go to writing the actual instructions to test the smart contract. So first is setting up the provider for the beneficiary key pair, and we're going to be using a different program when we're actually executing the instruction for the instruction that the beneficiary needs to sign. So we'll just get that set up now. So we'll do beneficiary provider. So that is a new bank run provider. And we want to use the same context that we defined earlier, so we can just do context. Okay. And then we're going to do the wallet. So beneficiary provider dot wallet equals, and this will be a new node wallet of the beneficiary. Okay. Now we need to define what the beneficiary provider type is. So we'll go back up to the top. Let's beneficiary provider, and that will be a bank run provider. And now we need to import node wallet. And this is coming from Anchor. Okay, and then we can just define this second program with the new beneficiary provider. So program 2 is equal to new program of type vesting. And then we'll need the IDL as vesting. And it's setting the provider as the beneficiary provider. Okay. And then we'll once again define the type for the new program. So let program 2 equal the program vesting type. And lastly, we just need to derive the PDAs. So we have 3 PDAs throughout our smart contract, and we'll just derive all of those now. So we'll do the vesting account key. And now you're able to find the address from the PDA by just using the find program address sync. And what this does is it generates the public key for a specific PDA. So public key dot, and we'll use find program address sync. And then we need to define our PDA. So for the vesting address, we used just the company name to create the PDA. So we can do buffer.from company name. And then we just need the program ID. So we'll do program.program ID. Now, 2 things. One is defining the type of the vesting account key. So we'll go back up to the top. Let vesting account key is a public key. And then the next thing is the company name. So since the company name is a user input value from the UI, we're just going to explicitly define the company name for testing purposes to make things easy. So we'll make a constant at the top. Company name is just, we'll make a company name for now. Okay, cool. So that's our vesting account key. now we need a treasury token account key. So treasury token account. And we're going to do the same exact thing. So public key dot find program address sync. And this is where we define the seeds for a PDA. So we'll do buffer dot from. And for our treasury token account, we did vesting treasury as the first part of the seeds. So vesting treasury. And then the second part was the company name. So buffer from company name. And then lastly, we just need our program ID. Okay, we forgot an equal sign, so we'll add that. And we need to define the treasury token account type. So let treasury token account be a public key type. Okay, and the last PDA we need to derive is the employee account. So let's define that. So same exact method. We have our employee account. And that is a public key dot find program address sync. And then the seeds for our employee account was a little bit longer than the rest. So we have buffer from, and it was employee vesting. Okay, and then we had the public key of the beneficiary. And then we had the vesting account key. So we had a typo in public key. So just for a reference, the public key class has a capital K in TypeScript. Okay. And then lastly, we just need to define the program ID. Okay. I'll just fix some formatting a bit. So this is a bit easier to read. There we go. And now we'll once again define the type. So this will be let employee account be a public key type. Okay. So that's everything for the PDAs that we need to derive. And it looks like we have everything set up for our testing environment and we can start actually testing. But let's just recap everything that we wrote. So before all, sets up the environment, and this is going to be ran before every single test that's ran. And here we're setting the beneficiary key pair. We're running start anchor, which is setting your bank run in the anchor workspace. And it's creating the bank's client and the bank server. It is specifying the path to your .so of the smart contract that we're testing. It's specifying the programs that we need to deploy, which in our case, it's just the vesting contracts. And then it's also specifying the accounts that need to be funded and have specific data written to it. And for our case, it's just funding the beneficiary account. We're setting our provider, running anchor set provider, naming our program, setting the bank's client. We're creating a mint address with the employer being the authority. We're updating the provider for the beneficiary. And then we're getting all of our program addresses for each PDA that we need to derive with the seeds that we're specifying. Okay, great. So now we can start writing our tests. So we'll go outside of the before all and write our first test. So we're going to create a vesting account. Okay, and this is going to be an async function as well. And now we can write our first transaction. So we'll do const tx and await. And now we can just call the namespace from the program. So we'll do program.methods. And now we can call the create vesting account instruction. So create vesting account. And all we're passing through as a parameter here is the company name. So we'll write company name, which is a constant that we defined earlier. And now we need to define all of the accounts that need to be passed through to run this instruction. So when we're creating a vesting account, we need the signer, we need the mint, and we need the token program. So we're going to set accounts. And signer is going to be the employer, but it's going to be the public key. And then the mint is just the mint that we already defined. And then the token program is, and this is just the token program ID. There we go. So with the new version of Anchor, any account that is a PDA that needs to be derived, it automatically does that for you. So you're just passing through the additional accounts here. Okay, so now we need to send the transaction. So we'll do .rpc. And then the commitment is confirmed. Now we're just going to console log our transaction. So we'll do console.log and then creates vesting accounts, and it will be our transaction. So another thing we can log actually is the vesting account data, just to make sure that the vesting account was created correctly. So let's do const, we'll do vesting account data. Await program dot account dot vesting account. And we can fetch our vesting account key. Okay. And then we'll just console log that. Okay. Now we can run our first test, make sure it works. So in our Anchor folder, all you need to do is run Anchor tests, and it will run all of the bank run tests. So you can see it's recompiling the Anchor program. And now it's running the test suite, and you can see our test passed. So let's go back to our logs. Within Anchor Bankrun, so here's our test. It's running the Bankrun spec TypeScript file. It's running Solana program test. Here are your runtime messages. And then here's our console log. So the vesting account data, we have the owner is the public key. We have the mint address. We have the treasury token account, the company name. We have the bump for the treasury and the bump for the vesting account. And then we also have the transaction of our create vesting account. And you can see in our test suite, we have one test passed, and the test was named should create a vesting account. Okay, so now we can go on to the next test. So in our first test, we created the vesting account. Now the next instruction that we want to test is creating an employee account. So let's write that test out. We'll do it should create a... Actually, before we create the vesting account, we need to fund the token account. So let's think back at what we just did. So we created a vesting account. And when the vesting account was created, not only was the account that's holding the state for the vesting account created, but a treasury token account was created as well. Because when we wrote our context data structure for creating the vesting account, we had two initializations. We had the initialization for the vesting accounts and the initialization for the token account for the treasury. So this token account needs to be funded to be able to pass tokens from the token account over to the employee's token account later on in our tests. So since the SPL token, mint, was created with the employer as the mint authority, we're going to be able to mint tokens to the token account that was just created to fund it. So let's add that as the next step as our test. Should fund the treasury token account. So let's define the amount that we want to fund. So this is going to be in Lamport. So we'll do 10,000 times 10, times 10 to the 9th. Okay. Now we can just execute the mint transaction. So we'll do mint tx, await, and we're going to run mint 2. Okay. So we want to make sure that we import this, and we're going to update the import from the SBL token bank run. Okay. Now this has a few arguments. It's very similar to create mint. So first we want to pass through the banks client. This is going to generate the same type error from create mint, so we can just copy over our little comment here. Okay. And now we have employer as the next argument, mint, and then the destination is going to be the treasury token account. And we can just pull in the key that we derived earlier. And then the employer is going to be the signer. And then the amount is going to be the amount that we just specified above. Great, so now we can just console log that transaction. And let's run anchor test to make sure that went through. Okay, so you can see our whole test suite passed, which included 2 tests, and those both passed. So now our treasury token account is funded. So we can move on to the next step. And this is going to be creating an employee vesting account. So now we can just define our transaction, and this is going to be the second instruction of our program. So we'll just name it tx2, and we're going to await. We'll call program.methods dot, and we'll do create employee account. Now this has several parameters to be passed through. So let's see. It has the start time, the end time, the total amount, and the cliff time. And because these are both I64 and U64, those convert to big numbers in TypeScript. So we're going to create a new big number, and we'll do, just for simplicity, we'll set the start time to 0 and the end time to 100. We'll set the cliff time also to 0 and the total amount to 100. So total amount is next, and then the cliff time to 0. This just helps us with testing because it sets the, so we don't have to wait for the cliff to pass. Okay, so now we'll just import bn from anchor. Okay. So next is passing through the accounts. So accounts, and we'll need the beneficiary and the vesting account. Okay. And lastly, we'll send the transaction. So RPC, commitment confirmed, And we're also going to skip preflight to true. So there we go. So we'll console log this transaction, make sure it went through. Okay, and then we'll just confirm the employee account. So we'll just console log the employee account address. And this is going to have to be 2 base 58. Okay. Now we'll run anchor test one more time. Okay, so you can see the test suite passed, all 3 tests have passed, and it names each test. We can just go back to our console log to just check everything. So we have our first instruction, and it created the vesting account, and there's our transaction signature. We have creating an employee account, and here's the transaction signature. And then this console logs the employee account public key. And we also have the minting tokens to the treasury token account. Now, the last thing we need to check is claiming tokens. So we'll make one more test. So should claim tokens. So now, because we need time to pass here to be able to claim the tokens, we're going to use a clock. So we're going to const current clock is equal to await, and from the Banks client, we can just get the clock. So Banks client dot get clock. Okay. And now we can set the clock in our context. So const dot set clock. And this will be a new clock with, and we're going to use the current clock slot. And then current clock epoch start time. And I spelled current clock wrong. Let's fix that. Okay. And then let's make sure we import clock. So this is an import from Solana Bankrum. Okay. And now we can see all of the arguments needed. So clock, start time, we need epoch next. So we'll do current clock.epoch. And then next is the leader schedule. So current clock dot leader schedule epoch. And then last is the Unix timestamp. So we'll just set this to 1000 in. Okay, now our clock's set. Now this is going to take a little bit longer in our bank run test. So we're just going to set a timeout. So we'll do await new promise. Resolve, set timeout. Okay. Now lastly, we're going to run our third instruction of the smart contract. And here, we're actually going to use the second program because the signer for this instruction is going to be the beneficiary and not the employer. So methods, and we'll call claim tokens. Okay, so what we're passing through here is just the company name. Now we need to add the accounts, and for this it'll just be the token program. And then we need the RPC commitment confirmed. Okay, and now we'll just console log our transaction. And this is our last test to run, so we'll run anchor test and see if the employee was able to claim their tokens. Okay, so you can see all 4 tests have passed. The full test suite has passed, and we can just look back at our console logs from the beginning of our bank run test. So we have the vesting account. When we're creating the vesting account, your transaction was logged. We have the minting to the treasury token account. We're creating an employee account. Here's the employee account public key. And then here is our claim tokens transaction. Okay, so now that our tests have worked and we have our program built, we're going to be able to deploy our program. So in this whole bootcamp, we're going to be using our local testing environment. So let's get a local test validator running, and then we can deploy to it. So we're going to go back to our terminal, and let's just do Solana test validator. So running the Solana test validator just initializes a new test ledger and then is running a local validator on your computer. Now that this is loading, you can see that it is loading to my local host, and we're able to now use it. So once you build a program, you're able to deploy. So we can just run anchor deploy, and we're going to specify the cluster that you want to deploy to. So we'll do provider.cluster. And this will be our localhost. Sorry, with Anchor, it's localnet. With Solana, it's localhost. Okay, there we go. So you can see it's deploying vesting. And you can see this is our program ID. Now, one thing to check is you want to make sure all of the program IDs are synced. So we're going to run Anchor keys sync and make sure you're using the correct program ID throughout the entire workspace. Okay, so you can see all program ID declarations are synced. There was an incorrect public key in our Anchor TOML, so this was updated by running Anchor key sync. So just because there was an incorrect program ID, we're just going to go back and rerun Anchor deploy, make sure everything's correct throughout the workspace. Okay, great. We're going to start working on our front end. So we can take this program ID and connect it to our front end. So in the Create Solana DApp scaffold, there is one part that doesn't automatically update the program ID, and you have to manually update it. So we're going to go there and make sure that it's using the correct program ID. So that's here in our exports, and we actually need to fully update our exports because it's still working for our counter. So we're going to update our counter exports for our vesting program. So let's rename this to vesting exports. And what this is doing is it's exporting information needed to be able to pull into our web folder when we're creating our web app. Okay. Now everything that's counter we want to update. So this is actually our vesting IDL. And this is coming from idl.vesting.json. Okay. And we're going to import the vesting type from our target types vesting file. Okay. So now we can export our vesting and vesting IDL. Now we'll update the program ID for vesting. So vesting program ID. And this will be the vesting IDL. And now this public key should be the same as the program ID here. So we're just going to paste this in. Okay. And this will be the vesting program ID. Now we're going to go back into our files and just check for counter. Okay, great. So you can see everything left with counter is in our React app. So we can worry about that as we're building out the front end. Now we can close out our Anchor file and open our web. Okay, so if you look on our web folder, we have the app folder, we have components, and we have public. We're going to start out in components. So you can see the components are separated between account, cluster, counter, dashboard, Solana, UI. What we're updating is the counter, because the counter is the area that's connected to the Anchor program. So let's rename this to vesting. Let's also rename this to vesting. Okay, just for consistency. Now you can see the vesting component is split into 3 sections. We have data access, we have feature, and we have UI. Let's first work with data access, because that's where we're going to be accessing all of the information needed to display on the UI. So we're going to import our get vesting program this time, and get vesting program ID. Okay. We'll just update everything from counter to vesting. Okay, so when you're using the vesting program, it's going to be making a query. And what we're going to want to set up is a query for the vesting accounts. So we're updating that. Now it's getting the program accounts based on the program ID. Now here's the initialization. We want to update this to initialize our new vesting accounts. So let's remove the initialization function. And this is just coming from the counter program. You had to initialize the counter program. So let's make this create vesting. Actually, let's keep this just to follow the same format, and we're just going to rename it. So we'll do create vesting account. Now this is program.methods, and it's going to be your create vesting account. This is going to pass through a company name and a mint address. So we have our company name, now this is a user input, and we're pulling this from the front end. And because we're doing that, we're going to have to tell this mutation that we're doing that. So we're going to update the mutation to have, we have a string, we have an error, and we also need to specify our arguments. So create vesting args, and let's write an interface to define what that is. So we'll do interface create vesting args, and we'll need the company name. And we need this because this is a user input parameter, and we're using this as an argument for the create vesting instruction. And this is its string type. Now another thing that we're going to have to pass through is the public key of the mint. And that's because we don't derive the mint account anywhere, so we need to pass through what the mint account is. And that is an account that's being used within the context data structure when you are actually creating the vesting account. But since it's being an input on the front end, we're going to make the type a string, and later when you're using the value, we're going to have to generate a public key from it. So we're passing through the arguments that we need. Our mutation key is going to be our vesting account creates we're using the cluster. Okay, so here is where we want to pass through the company name and the mint. This is because these are the two arguments that we're grabbing from the front end and then passing through. So we just need to specify that. Okay. Now we can run program methods, and we're using create vesting account, and the only parameter that's being passed through there is the company name. Okay. And then the accounts that we need is going to be our mint account and the token program. So we'll go back to accounts, and we'll do the mint. And that is a new public key of the mint. And we're creating a new public key type because the mint is being passed through as a string type. And now we also need the token program. Okay. And then we'll just import the token program ID. And then we don't need a signer because we're going to actually be using the wallet that is connected to the front end of the application. So we'll just use the RPC, and then on success, it'll sign. And on error, it will give failed to create vesting account. Okay, great. So now we'll just update the return, and that is going to be create vesting account. Okay, so that's all the data we need for using the vesting program. Now we want to be able to use a vesting program account. So what this is going to be is once an employer has come to the front end and they have created a vesting program, now they can go in and update that vesting program by adding in employee accounts. So we'll go to use vesting program account. And this is passing through the accounts. Okay. Now we'll do use vesting program. And then the query is going to be for the vesting accounts. Okay, so now you can see we have close, decrement, increment, set. This is everything related to the counter. So we can just delete that. Okay, and we'll delete the corresponding returns. Okay, so now we're going to want to add in creating an employee vesting account. So this is going to be very similar to our instruction above. So what I'm going to do is just copy this over to make things easier. Okay. Now, instead of create vesting args, we're going to create an interface for create employee args because these are going to be different. When you're creating an employee account, you're specifying things like the start time and cliff time of your vested tokens. Okay. So interface, create employee args. Okay. Now we'll define what that is. We need the start time. Which is a number. We need the end time, which is also a number. The total amount, which is a number as well. And then the cliff time, which is also a number. So those are our 4 arguments needed when you're creating an employee account. Okay, so we can go back to our create employee vesting. We'll update this to employee account. And then we're passing through the arguments we just defined. So start time, end time, cliff time, and total amount. Okay, and then we'll update this to create employee accounts. And that is going to take in the start time, end time, total amount, and cliff time. Okay, and now the accounts. Let's go back to our bank run tests and just check to see what accounts we need. So accounts, test background. So one good thing about testing in TypeScript when you're creating the front end, it's very similar. So it makes things a lot easier because you can always reference your tests and you know that these work. For creating an employee account, you need the beneficiary and the vesting account. So we'll go back to the data access and we're going to update our employee args to include the beneficiary, which is going to be a string because it's going to be a user input. Okay. And then we'll go back and do the same thing to convert it to a public key. So this will be beneficiary, new public key of the beneficiary. And we'll update that here. Okay. And now we don't need the token program, but we need the vesting account. And that is just the account. So now we can return the create employee vesting. Okay. Great. So for now, this is what we need for our data access. Let's update our UI and then the feature. So let's rename this to vesting UI. We need to update all of our imports. So let's just go through everything here. And we also need to update the data access file name. So we'll change this to vesting. And while we're here, we can update some of the unused imports. We no longer using a key pair because we're connecting to the wallet rather than generating a key pair. And we're no longer using program. Okay. Okay, so we'll update the create to vesting create. And then we're using the create vesting accounts from use vesting program. Now, this is what the UI is going to look like. As of right now, it was just a button that you clicked for the counter. However, we need to accept some user input parameters. So we're going to have to change that a little bit. So first, we're going to need the company and the mint. So let's actually update this to have the company and then set company. And we're going to use state. Okay. And we're just going to import this from React. And then we also need to do the same for mint. Okay. And now, because we're using the wallet that's connected, we want to be able to get the public key from the wallet. So const public key, and this is going to be use wallet. And this should be an import from the Solana wallet adapter. And you can see that updated the import. Okay. So now we have that set up. Now we need to be able to get these two values from the UI. So let's create a text field for both of those. So in the return, we're actually going to create a div. And we'll put this button inside the div. Okay. So now we'll have a text field. So we'll do input. And let's just take what Copilot has, and we can update it as we need. So we have the type is a text. Good. The placeholder is company name. Good. The value is company. And then on change, we want to set company. Okay, great. Now let's also add in the class. So we'll do class name. And we're just going to define this as an input. And we want to have a border. We want the width to be full. And let's do max width for extra small. Okay. There we go. So that's our first input. Now we need another one for the mint. Okay, we're just going to accept what Copilot's suggesting and then review it. So we have the input type text, we have the placeholders, the mint address, the value is the mint, it's updating the mint on change, and then it's taking the same exact class name from above. Now let's update the button. Well, we can change the name of the button, and that'll be create new vesting account. Okay, now we're going to need to do a little bit different than how the counter is. And that's because we have some values that are being input. So we want to make sure that those are added from the user. So we're going to actually check the form. So let's do a few steps before we actually update the button. So first is we want to make sure that the form is valid. So let's do const, we'll do an is form valid check. And we just want to make sure the company dot length is greater than 0 and the mint length is greater than 0. Okay. And now we're just going to do a handle submit. So let's do a const handle submit. And we're going to do if. So we want to make sure 1, the wallet's connected, and 2, the forms are valid. So if the public key exists and if the form is valid, then it's going to run create vesting account dot mutate async with the company name, which is the company, and the mint. Okay. And now we just want to do one more error handling, and that's just if the public key doesn't exist, we want to return an error to tell the user to connect their wallet. So we'll return connect your wallet. Okay. So now that those checks are in place, we can just update what happens on click for the button. So on click, all we're going to do is just handle submit. And then it should be disabled if the create vesting account is pending, and it should also be disabled if the form is not valid. So a user cannot click the button unless they've fully filled out both of the forms needed. Okay. And then we'll just update the button to have create vesting account is pending. And there we go. So now we've updated the vesting create page. Now we need to update the list. So what this does is it returns a list of all of the vesting accounts that are connected to the connected wallet's public key. So if I created multiple vesting accounts because I'm separating my company into separate mini companies and I want a vesting account program for each of those, it'll show all of them. We're going to update this to have use vesting program. And now what this is doing is it's checking the data of the program account. If the account is not found, it's going to return an error and say you need to make sure that the program account is deployed to the correct cluster, meaning if you're connected to LocalNet, the program should be deployed to LocalNet. If you're connected to DevNet, the program should be deployed to DevNet. So now you have the return and it has your cards. So this is going to be all of the cards associated with the vesting account. So we're just going to rename this to vesting card. And then we'll find where the counter card was originally written. Okay, and we're going to update this for vesting. So this should use vesting program. Sorry, this should be use vesting program accounts. And it takes in the accounts. And now we'll update this to have create employee vesting. Okay, so this we're going to make updates very similar to the previous section because we're going to be taking values from the front end and using that in processing our instructions. So let's set up all of the information that we need. We'll need the start time. And now instead of using state as a string, this is going to be a number. So we'll update that to a 0. And we'll do the same for end time, the same for total amount, and the same for cliff time. Okay. Now we're also passing through the company name, but because we're connected to the account, instead of needing to pass that through on the front end, we can just query the account because the company name is saved to the account state. So we're going to do const company name is equal to, and we'll do use memo. So we'll do an account query of the data in the account. We'll unwrap that and find the company name. Okay, and then we'll just need, there we go. Okay, so we can remove this because that's coming from the counter. And that was just querying the count from the counter state. So we're doing basically the same thing, but querying the company name instead. So now we'll return, we'll update the UI here. So we have, this is separating everything into cards. And we have the header. This is just querying the account. So from the account, instead of the count, we want the company name to be the header. Okay. Now, before the buttons, we're going to need a text input. So we're going to do basically the same thing we did above. So for simplicity, let's just copy that over instead of having to write it all out. Okay. So we'll make that update under the header and then under this div. So this div is separating all of our buttons. So we have an input. And this will be text. We're going to set this as start time. The value will be start time. And now we want the start time placeholder to show. So because of that, we're just going to do this. Okay. And now we have the value on change. It's going to set the start time. And this is going to be, because this is a number, we're going to have to parse the integer. So we'll do parse int. There we go. And we'll keep the class name the same. So now we're going to do the same thing for the rest of the inputs. So we'll just copy this and update this to end time. And this will be set end time. Okay. And then we'll do the same for cliff and total amount. So total amount comes first, actually. And we'll set total amount. And then we'll do cliff time. Okay, so let's just make sure we did all of that. So start time, set start time, end time, total amounts, and cliff time. Okay, and let's just write allocation here so it's easier on the front end so you know what that value is. It's the total allocation an employee gets. Okay, so now we can update our button. So the button, it'll have the same class. On click, we want to create employee vesting, and that is going to update these arguments to start time, end time, total amount, and cliff time. Okay, and then we'll update this to create employee vesting. Okay, and now we're getting an error, so let's figure out why. So you can see beneficiary is missing in the type. So we actually are forgetting one field. So let's update this to also have the beneficiary. So here we're going to need const beneficiary, set beneficiary, and beneficiary is a type string, so we're going to use the string. And then we're going to need to have an input field for that. And this will be a beneficiary. And this will be the wallet address. Okay. And we'll update this to just beneficiary. And this is not an integer, so we can get rid of the parse int. Okay. And then this should be set beneficiary. Okay. And now we can pass that through as well. Okay. And we'll update the name of the button to create employee vesting account. And this we can get rid of because this is coming from the counter program. And we'll just clean everything up. Okay, and we'll clean up our imports. Anything unused we'll get rid of. All right, so lastly we need to update our feature. So the counter feature is going to use the vesting program. It's going to use the vesting create. Let's update our counter list to be named vesting list. Okay. Then we'll update everything for vesting. So this should be a vesting feature. Okay, this should be vesting create and vesting list. Okay. We'll update the title to vesting smart contracts. Actually, we'll just name it token vesting. Okay. And then create a new vesting account. Below. And we'll just remove the rest of these comments. Okay. So let's see. This is our feature. We're setting up the vesting feature. We're connecting the public key from the wallet that is connected to the front end. We have the program ID from our vesting program. If there's a public key connected, it'll return to create a token vesting account. Okay, so this looks like everything we need. We're just going to rename this vesting. And now we should have gotten rid of almost everything related to the counter by now. There's just one more thing we're going to need to update. So vesting, let's just Command Shift F for counter. Okay, these are all just comments. So here we go. In the layout, we'll update this to vesting program. And this should be using the vesting path. On the page where we want to use the vesting feature, and we're going to import the vesting feature. Okay. These are all comments. Okay. And now let's just update our queries to vesting. Okay, so now we're good to go. So now to recap everything that we've done so far, we've created our smart contract using Anchor in our Anchor workspace. We've built the project and deployed it also using Anchor. We deployed onto our local host, so we're running a Solana test validator locally on our computer. And then we've updated the front end to be able to connect to our wallet and execute smart contract instructions. Now that all of that's done, we're going to run on our local host, the UI, and be able to test it out. One thing to know before we start running, you're going to want to make sure that your package.json, the lock file, is updated because it's probably still going to have dependencies linking to all of your counter files. So I would just delete the package.lock and rerun npm install to make sure that everything is set and good to go. And then we can just go into our web folder. So we'll cd into web, and we can run npm run dev and get this running on our local host. Okay, so we're gonna open up our browser, navigate to our local host. Okay, so this is what our UI looks like using the Create Solana D app. You have the cluster that you're connected to. You can see here we're connected to local. You have your wallet connection here. And this is connected to my Phantom wallet that I have linked on this webpage. Now, you can see that it automatically prompts you that I'm on local, but I don't have an account found. So I'm going to request an airdrop. So this account that my wallet is connected to is now funded with Sol, and the account exists. So this is our placeholder. You have this basic front end that has just GM. This is your new Solana D app and some links. Now, what we updated was the vesting program tab. And just to make sure you're familiar with the Create Solana DApp scaffold, we'll just go through all the other tabs first. So you have this account tab. And this shows the account that I have connected. Here's my wallet address. It is the same as the wallet that's connected. You can see that I have one Sol that I just airdropped to myself. You can see the transaction history, which was the Sol that I just airdropped to myself. You can see that I have no token accounts currently. And you can see that we have the option to airdrop, send, and receive funds from my wallet. Now we can move on to the clusters tab. And these are all the clusters that you can connect to from your front end. So you have DevNet, you have LocalNet, and you have TestNet. Currently, we're connected to local, and we're running our local on our Solana test validator in our terminal. You can see our status of our current validator. Here's the process slot, confirm slot, finalized slot, and full snapshot slot. So you can see everything's running correctly on our local host. All right, so now we can go to our vesting program. You have the name, token vesting. It says create a new vesting account. This is the program ID of the account that we just deployed. Now let's test this out, but we're going to need an correct mint address for this to work. So we're going to go back to our terminal, open a new tab, and we're going to create a mint on our localhost. So let's do SPO token, creates token. I'm going to specify the URL to be your local host. Okay, so you can see we're creating a token under the token cake program, so it's an SPL token. Here's the address of the token we just created, and there's the signature, so you know it was a successful transaction. So we're going to copy that address, go back to our UI, and paste the mint address in the mint address field. Okay. Now we'll do the company name, so we'll just name this bootcamp. Okay, so we'll create a vesting account, unlock, confirm the transaction. Nope. Great, so now you can see the new vesting account that was created for the bootcamp. And this allows the employer to now come in because this bootcamp card from the new vesting account that was created is connected to the public key that I'm connected to on the UI. So all of the vested accounts that I create are going to show up here, and then me as the employer is able to come in and create employee vesting accounts for employees for each account that I create. So if I wanted to make another one, just like a subset of vested tokens, and I set this as my 2024 bootcamp employees. We're going to just create new vesting account, confirm. And now you can see this is my other set of vested allocated tokens. Sorry. You can see this is my other set of vested tokens. So now I'm managing two different accounts that have separate tokens. I could create a separate mint address if I wanted to, so we can actually just test that out. I'll go back to the UI. I'm going to run SPL token create token. Now I have a whole new token. So let's say I wanted to have some employees vested with one token and some with another. I can do that. We can do just a test here, create a new account, confirm. And now you can see here's my next account. So this is related to one token, and this has a mint address of another. So now I can keep track of all of the vesting accounts that I create, and within those, I'm now able to create employee vesting accounts that have a start time, total allocation, end time, cliff time, and the wallet that I want the beneficiary of this account to be able to claim tokens. So there's my UI, and you can see everything works with the program that we created. And overall, we created a smart contract. We tested it using Bankrun. We updated the front end with our Create Solana DApp scaffold, and we tested it on the front end. We also deployed our smart contract to our local host while we're running our Solana test validator locally. So there's our token vesting DApp.
Now that we've been building with tokens, we're going to add something new in our next project. The next project will be a token lottery system, where the user will be able to enter into a lottery with a smart contract acting as the ticket issuer. The hard thing about lottery systems and blockchain is that they require some amount of randomness to be fair. A distributed system coming to a decision on a fair random number is impossible, so we're bringing in a new concept to help us out. In blockchain, oracles can be used to retrieve random numbers for use cases on-chain. Oracles connect the distributed system to the data of the outside world, financial data, football game outcomes for betting markets, or even random numbers can be retrieved from these oracles. The way these oracles work is that they have a distributed set of data providers from the outside world pushing data on-chain. The on-chain data is then normalized within your smart contract, throwing out data oddities and taking a fair number based on the data provided. Random numbers are still difficult even with oracles, but they can be retrieved using a commit-reveal scheme. First, someone will commit a random number that is hashed with a random seed value. This commit value can be stored on-chain for use later. Once ready to reveal, the original committer will then push both the random number and the seed value, which can be verified against the original hash. We're going to do exactly this commit-reveal scheme in our project. Let's get started.
All right, so for this project, which we have called the token lottery, what we're going to do is we're going to have a lottery system that people can buy tickets from. They can use those tickets to then claim prizes, and then we're going to use something called off-chain randomness. So it's not actually on-chain, it's using something called oracles to decide the winner of the specific lottery. So let's get started. Before we do any code, what I'd like to do is I'm going to draw up all the different things that we need to build. So we're going to design our program. So this is the token lottery, right? The token lottery is going to have a few functionalities. So we have issue ticket. We are going to be able to, let's see, we're going to have to be able to do a commit reveal for randomness, and finally claim prize. And so thinking about this, what kind of instructions do we need? So let's start building out and designing our program. So the first instruction we obviously need, we're gonna have to create the configuration for the lottery. So this is gonna be like initialize config. So that will build everything that we need to for that lottery. The next thing that we might need is we might need a initialize lottery so that we can create all the different pieces for creating our collection, being able to issue tickets later, etc. Because we want to make sure that we initialize the lottery collection first before we can allow people to buy tickets. The next one, this one's going to be something that's going to be done by the user of this, but we're going to do a buy ticket function so that people can buy those tickets and then they can later use those to claim. So we're going to get into this a little bit later, but we're going to have two separate instructions. One's going to be a commit function, so commit randomness function, and the second one will be a reveal randomness, or choose, we'll call this choose winner. The reason being is whenever you do like a commit reveal type of scenario or scheme, you have to make sure that you do those in two different instructions, specifically also two different transactions. You cannot do the commit reveal both in the same transaction because there's some gaming that you can do there. And the final instruction that we'll need is claim prize. So claim prize. So you can see there we have six different instructions. You can already kind of think this is going to be a pretty thorough and in-depth smart contract that we're going to be building. Let's figure out what that config is. So we're going to call this the token lottery. This is going to be everything about the token lottery. We're going to need things like we're going to figure out who the winner is. This will be a ticket number, basically. We're going to have to figure out if the winner is already claimed, because what we don't want to happen is someone to be able to claim the prize immediately on token lottery without anybody doing anything. We want to make sure that it's bound by the time that the token lottery is taking. And time meaning we have a start time and an end time for the token lottery. Next thing we have is we're going to have an actual winning amount. So we have to have we'll call it a lottery pot amount. This is the amount of money that is up for grabs so that people can win it. Another one that we're going to have to need is we have to keep track of the total tickets. If we don't have the total tickets, let's actually call this total tickets. So total tickets. If we don't have the total tickets, we won't be able to figure out what number to choose from for our randomness data. So we have to keep track of that. We want to make sure that we have a price for all these tickets. So if there's a price to pay to get in the lottery, that's something we're going to have to keep track of. We're going to need two things that are not really obvious, but we'll need the authority. So there's going to have to be an authority that can do the commit randomness and choose winner. Otherwise, you can't really do much with it. And then finally, you'll need that randomness account. This randomness account is just to tie the account that is required to do the randomness information. We want to tie it directly to the token lottery config. All right, so we have a basic understanding of what our instructions are going to look like. We're going to have 6 different instructions. We have our config. Let's go ahead and start building. So we're going to open up VS Code, and I'm going to do new terminal. And as usual, we're going to do mpx create Solana dapp, and I'm going to type it all out. So this is going to be a lottery. We're going to call it token lottery. Token lottery. We'll call it an XJS. For this project, we're not actually going to build a front end. It'll kind of be like a challenge for you to figure out how to build that front end. We're going to do a focus on the smart contract side. Tailwind, we're going to come with the basic stuff and it'll create. So I'll see you in a moment. All right, so we have a project. Let's go ahead and open it. So we go over here. I'm going to open Token Lottery. There we go. We have our project. It has an anchor folder. Looks like it has everything we need to get started. Let's close all these warnings. And I'm going to open a new terminal. And we're going to do first two things. npm install, just so that we make sure we have everything that's needed here. All right, now that's done. Now we're going to go into the anchor folder. Let me make this bigger for y'all. We're going to go into the anchor folder and we're going to do an anchor build, just so that we make sure that it sets up everything. So right there, we saw something that we want to keep track of. It says warning anchor version 0.30.0 is not equal to the CLI version. So as a note, throughout this entire bootcamp, we're going to be doing it with the 0.30.1 anchor version. So we want to make sure that we set up everything to be using that. All right, so what we're going to do is we're going to go update that. So if we go over here into programs.basic, cargo toml, you'll see down here it says anchorlang 0.30.0, update that to .1. We're also going to change a couple places. We're going to change this to say, we're going to say token lottery. We just want to make sure that that's everything. This one's going to be an underscore. There we go. Actually, let's just make everything underscore just so that it's easy for us to understand and remember. So I'm going to update this. I'm going to update this. We're going to update this folder path name also just to be token lottery, the lottery. Okay, token lottery. So let's update all the names. Let's make sure that it's set here. So there's going to be a programs here. There we go. Update that to token lottery. And then finally, we got to go into our librs and update this to say token lottery. Okay, so now we can do an anchor build. So everything completed, everything ran perfectly, so we can actually continue. So we have our greet. It has a message of GM, so good morning. We're going to go and remove that, and we're going to go back over to our specific design diagram that we created. So here we have initialize config. So we're going to build that one first. So we'll call this instruction initialize config. We already have the context of initialize, and it's going to do a bunch of different things. Right here, we know that we're going to create an account because we have to create that specific config account. We're going to call it the token lottery account with all that data that we had over here. All right, so because we know that we're going to have a pair. It's going to be a signer. I'm going to use lifetimes here. If you don't know what lifetimes are already, I would recommend looking them up in the Rust book. They're not that hard. All right, so this is going to be account mutable because we are going to use a pair and there's going to be LAN ports deducted from the account. And then we're going to have another account. So this is going to be account, and I'm going to enter here. We're going to initialize it. The pair for this will be pair. I'm just going to put 8 here. We're going to update that in just a minute once we create the account. Then we're going to have two different things because it's going to be PDA. I'm not going to do it as config. I'm going to do it as the token lottery. And because it is a PDA, we're going to need a bump. And so this is going to be a pub token lottery, and it's going to be a specific account. We're going to call this info token lottery. And because we're creating it, you can see Copilot already knows, because we're creating an account, it's going to say like, hey, we need a system program. Let's go add that system program. All right, so we have this token lottery. We have to actually define it now. So let's go define it real quick. We need an account. It's a pub struct token lottery. You can see here, it's asking us to do a bump, and we're actually going to keep that. It wasn't in our original design, but best practice, if you're using a PDA, you want to save the bump in the actual PDA. This allows you to use less compute later on. Just make sure that you always save the bump in the PDA and then use that to derive it later. All right, so let's set all this stuff in the token lottery. Before I do anything, I'm going to do the, what is it called? Derive, the macro for derive init space. And then because I did that, I can now go the 8 bytes for the anchor discriminator plus the token lottery init space. This will make sure that it auto-generates the amount of bytes that it takes to store this token lottery on chain, and I don't have to do some math. I always am for that. All right, so let's go ahead and set everything. So first off, we need a winner. We're going to have U64 as the ticket numbers. Next thing, let's say we need the winner claim. So this is going to be winner claimed. This is going to be a bool. Next one's going to be start time. We're going to do this in slots, which is a U64. We need the end time. We need a lottery pot amount. So pub lottery pot amount. This is going to be U64. The next one we have is the total tickets. So pub total tickets. It's going to be a U64 as well. We have the ticket price, and then we have an authority. So this is going to be pub authority. This is going to be it's going to be a pub key. Let's remove that extra space right here. And then finally we have the randomness account, which is going to be another pub key. So randomness account, not randomness account. There we go. All right, so we have this big struct. We should have everything we need to get started. Let us start filling this in. I'm going to do a quick anchor build just to make sure that we wrote the right code and we don't have any typos anywhere. All right, everything compiled. It's great to hear. All right, so what we're going to do is we're going to start filling out this configuration. So in order to do that, we just start writing all of them. So I'm going to remove this underscore here because we're actually using the variable. So accounts dot, we're going to do the token lottery equals, we want to make the bump because we always need to remember to set the bump. We're going to do context.bumps.token lottery. This is basically just going to set it in the account for the bump that was used to derive this token lottery. Next up, we have the start, end date, and price. So start, end time, and price, right? Those are actual parameters that we need to pass in. So let's go ahead and pass those in. So we have start of a U64, end U64, and price also as a U64. So we have this. We're going to have context.accounts.start time is start, end time is end, set the ticket price. We want to set the authority. So the authority will be the payer. Then we need the lottery pot account amount to be 0. It actually sets it as 0 by default, but we're going to set it just to be verbose. We want the randomness account to not be set yet. We're going to do that whenever we commit the randomness. So dot randomness account equals pub key default. So it's going to be a default pub key. Can't derive that. That's fine. And then finally, we're going to do context.accounts.token lottery winner equals, well, not the winner. We want the winner claimed equal to false. Let's do the winner. Let's change this to winner chosen just to be a little bit more understanding what we're doing because it's false. We haven't chosen it yet. We're waiting to choose it before we continue. All right, so we set everything. Let's go ahead and test it. All right, compiled. Let's go over to the anchor tests. We're going to update this to say token lottery instead of basic. So token lottery.spec.ts, and I'm going to call this the token lottery, and should init config. So there's a couple of things here. What we see is this is trying to import basic. We need to import, instead of basic, we're going to have to import the token lottery. So this is going to open token lottery instead, and that's going to be token lottery. This is so that we can use the program, and then I'm just going to copy and paste this right here. This is so that we're using the program from Token Lottery. Now note, this might be different than other tests that we've done throughout this bootcamp. We're going to use the standard anchor test instead of bank run for this one because we're going to do a lot of funky things with accounts and programs. A fun challenge would be to figure out how to do this with a bank run on your own. But ultimately, like, it's only a few lines of code difference to get set up. All right. So I'm going to remove these. One other thing that I'm going to do is I'm going to create a provider equals anchor.anchorprovider.env. And then I'm going to set the provider here. This is so that I can grab the wallet, which I'm now going to set as the wallet down here. So we'll set also a wallet, const wallet equals, this is going to be provider .wallet as anchor wallet. All right, so we have the wallet, we have the provider, we have the program. Now we can actually do things with the program. So let's go ahead and do it right here. So I'm going to do const. We're always going to do the instructions first because it's simpler to understand what's going on. So this is the init configuration instruction equals await program dot methods dot initialize config. Now you can see here has an error. Let's go figure out why it's missing. So it's because we don't have that start time, we don't have that end time, and we don't have the what's the last one that we needed? So start, end, and price. So let's go ahead and set those. So it's going to be U64, or sorry, new anchor BN, because that's how you set the price, or a U64. We're going to do a few things. I'm going to make the start of 0. We're going to go grab a Unix time from online. That's going to be really high, just so we can test this. So let's grab that real quick. Boom. That's really high. Let's make it even higher, so it's way in the future. And the price, let's make the price 10,000. This is 10,000 LAN ports. All right. So we have the instruction. Now we have to actually create the transaction. So const tx equals new anchor.web3 transaction .add initialize config instruction. Let's see what happened with it. Let's see, argument type of pair writable. Okay, so we're just missing something. That's fine. We can do that. So this is just because it's missing some of the information needed to complete. So let's go add all of that. All right, so the things that we need for this transaction is we're going to need some things from the block hash. So we'll do a block hash with context equals await provider.connection. We're going to use get latest block hash. There we go. And now we just need to set everything right here. So the fee pair, we're going to set the fee pair as my wallet. We're going to set, let's see, we're going to set the block hash as the block hash with context. And then finally, we're going to need the last valid block height, which is going to be block hash with context dot last valid block height. There we go. And let's see, all the errors didn't disappear. All right, so we're just still missing something. This is because, let's see, this is missing an add. Let's see. I think it's because we don't have the right information to run this. So let's go back up here. So it's program, methods, initialize config, perfect. oh, it's not an instruction. This is a builder. So we have to actually set as dot instruction. There we go. Everything's happy. Yep. We got the transaction. This is our transaction signature. And now we just have to send it. So what we're going to do is we're going to do const signature equals await provider dot web connection. We'll do it with anchor. So anchor dot web 3 dot send and confirm transaction. This will need a connection. So we're going to do the provider dot connection. We need the actual transaction, and we have to need the actual payer as well. So wallet dot payer. There we go. I'm going to add a semicolon just for making it look nice. And then we just do a console dot log your transaction signature. I'm going to go ahead and pull this one out because we don't need that until afterwards. Let's run it. So anchor test. One thing I'm going to do is I'm going to run a separate local test validator. So we have, let's actually remove that. Kill terminal. I want a specific type of terminal. I want my ZSH, not just a plain bash terminal. So separately, we're going to set up a local test validator. So if I run local Solana test validator, it'll run my test validator. And then here, I'm going to do anchor test -- skip local -validator. This is just so I don't have to wait for the startup every single time. Also, we're going to do some special things with the local validator. This will make it nicer. So let's run it. All right, so it failed. Let's go see why it failed. Should not in config. Program error 1004. So that's a custom program error. This is usually, I'm probably just missing something. We're going to do a trick here. We're going to add a skip preflight checks so we can actually read the full error. So we're going to skip it. Going to run that thing again, and then we're going to go check that errors. All right, so let's grab that transaction signature. There we go. We're going to go over here. We're going to go to our Explorer. Make sure that you set it to local. Go look at that transaction signature. You can see here, declared program ID mismatch. Perfect. So that's a better error. Let's go figure out what that means. This is because if you go over into librs, you can see that it says HVX. However, when we deployed, it now is ESFW. So let's go update that. And I believe you have to do it in one other place. Let's go find it. I believe it's in the cargo, or it's in the anchor toml right here. So that also needs to be ESFW. All right, let's run it. Let's do an anchor build with it real quick. And then we'll do an anchor test. And that way it will start up with all of the right program IDs. Anchor test, and deploy again. We'll deploy to that same program ID. And then pass. So we can see here, if we can go grab that signature real quick, and I'm going to go paste it in here. There you go, success. And when we go all the way down, we can see initialize config, return success, and then it took some compute units. Fantastic. It would initialize our config, it created our account. Now we can move on to the next step. All right, so we've initialized the config. The second thing that we had here, if we remember from our design, is we have the initialized lottery. So there's a number of things, different things that this initialized lottery is going to do. I'm going to move this initialized config over here, and just so we can draw up all the different things that this lottery is going to do, because it's going to do a lot. And it's going to be quite a lot of work as well. All right. So this initialize lottery, right? So we're going to do initialize lottery. It's going to do quite a few things. The first thing it's going to do is it's going to create a collection that is owned by the program. This is because we want the program to have full control of minting more tickets. We don't want to have anybody else have that control other than the program itself. It's a separation of concerns, security thing. That's fine. So create a collection that's owned by the program. This is a lot of work, and this will create mint. So create collection, create something called a master edition, so that you can mint more tokens. Or sorry, this is not a master edition, it's a metadata account. So metadata account. And then we're going to also create verify the collection. All right. And if you go over here, so if we go over to the token metadata docs, we can see here that it's very important to check that this verified thing. Let's see if I can make this a little bit bigger. All right. So this is kind of what we're creating here. We're going to create a verified NFT, which includes the mint account and the metadata account. We're going to have that collection NFT, which is also is a separate NFT that will have a collection, some details, and have a mint account. And then we're going to verify it, which sets this collection metadata in the metadata account to the key equal to the metadata, as well as verified equal true. So this is what we're basically going to build, is these 4 accounts right here. Let's go ahead and start building them. All right, so first thing we're going to do is we're going to create a new instruction. So pub function initialize lottery. This is going to have a new context. We're going to do context initialize lottery. This is going to return a result. I'm going to remove all this extra code. And now we have to actually build out the initialized lottery context. All right, so let's go ahead and throw it all the way right after initialize. We're going to set it right here. I'm going to make my term a little bit smaller. So this is going to be a derive accounts. So, and then pub struct initialize lottery. And it's going to have a bunch of different things. So one thing it's going to need is it's going to need it's going to need a signer. So let's do account mutable pub pair signer. And then we know that we're going to be creating accounts. So let's already create that as well. So system, program system. All right. So we have this initialized lottery. I'm going to go ahead and do this real quick. We've started writing the code for the lottery thing. So let us compile it and make sure that we didn't make any mistakes in the meantime. Okay, so everything worked just fine. Because we're going to be using token accounts, we want to make sure that we add the specific cargo crate for the specific crate for Anchor SPL. So Anchor SPL. This is actually, it's a cargo add. What is it called? Anchor. Let's go grab the docs real quick. It's always good to have the Anchor Lang docs available. So this would be SPL. Was it Anchor SPL? All right, so let's go grab this Anchor SPL thing. So there we go, Anchor SPL. So we need to add this right here. There we go, it's adding. Okay. Looks like Rust analyzers are still catching up. Now, another thing is we're going to have to make sure that we add something right here of anchor-lang/ or anchor SPL/IDL build. It's just so that we make sure that we have the right IDL stuff for it. Right here we have anchor SPL. We want to make sure that we have the features of metadata. So I'm going to add it right here. So this is version equals 0.30.1 / features equals metadata, I believe is what it's called. There we go. And I'm going to do an anchor build one more time just to make sure everything is set up correctly. All right. So it's because, let's see, I missed something here. Oh, I missed quotes. That's fine. I'm okay with that. All right, so it compiled. That means we added everything correctly. I always like to do that just to make sure that everything is right. Let's continue with creating this initialized lottery. So we have the token, we have the system program, the pair. I just spoke about what I wanted to add as well. We want to make sure that we add the token program that we're going to use. So pub token program. This is going to be an interface program, because we want to make sure that we allow any type of token program to exist. So interface of info, I believe it's what? Token interface? Yeah, token interface. There we go. All right, so we have the right token program. We're also going to need the associated token program. So pub associated token program. This is going to be of type program info, not token interface, but associated token. There we go. We're also going to need what's called the token metadata program, because we're going to be creating those metadata. So token metadata program info token metadata. It's going to say that we need to add it. So let's go add it real quick. We need to make sure that we add it here and save. Running into an error. We'll fix it in just a moment, and that's okay. Is not satisfied with ID is not satisfied. All right, we'll fix that in just a moment. I'm just going to make this a little bit prettier, because otherwise it's going to be a mess in the long run. I think this is the wrong token metadata is the issue. All right, so let's add all that. This metadata that we need is actually from a different crate. Let's see if it knows it. Otherwise, I'm going to have to add it individually. Oh, so it's not actually token metadata, it's metadata. And this is under Anchor SPL metadata. Perfect. All right, so everything is happy there. Next up, we need to actually start creating all of our different accounts. So these are our collection mint, our metadata account, our actual collection token account, so that we can have it on chain, and then finally our master edition account. So let's start off with some of them. So first off, we're going to do the collection. We're going to have to do the collection mint. So this is going to be an account. This is going to be init, because we're going to initialize something, pair equals pair, so that we have something paying for this thing. Since this is a mint, we're going to have mint decimals of 0, because it is going to be a collection mint. This is going to be mint authority. I'm going to set it to pair, but we're going to change it in just a moment. We're going to also change this one to be something else in a moment as well. We also need the seeds. We're going to make it a PDA, just so that we can easily derive it later. We're going to call this collection underscore mint as ref. And because you have seeds, you must have a bump. Now, unfortunately, because this PDA is a mint account, we can't actually store the bump inside the mint, because it doesn't have a space for it. That's okay. We'll be fine with that. This is going to be of type interface account, because it is could be a different type of token account. Info mint. There we go. And this mint, let's see, this mint should be the interface mint. All right, save. So that is our collection mint. The next two are, let's do the collection token account first. So the collection token account is an account. It's going to be, we're going to initialize it. We're going to have a pair. That's perfect. Oh, it did a whole bunch of things. I don't want all of this here, so I'm going to remove all of it, and we'll keep going through it in just a moment. All right, so we have the token mint equals the collection mint, and then token authority. We're going to have the authority to be itself. So we'll leave it for pair, we'll update it. So pub collection token account is of type interface account, because it can be either type of account, /info token account. and it's going to be token interface. Perfect. So we're going to update a few things here. I don't want the pair to be the authority of the collection. We want the PDA to be authority. Same with the collection token account. We don't want the pair to be authority, so we're going to make the collection token account the authority of itself. All right, so we have those. That looks fine. Just to make sure that we're doing all right, I'm going to do an anchor build. Everything compiled fine, we can keep going. All right, so the next two things, we're going to do something that's not normally best practice, but it's okay in our case. You'll learn in the security module if you've if you went through it already, why it's not best practice, but it's okay. So we're going to use two different accounts. The first one is going to be the metadata account. So metadata, and this is we're going to call it metadata, an unchecked account. And the reason being is it's going to be checked and created by the actual metadata program. The other one is we're going to need the master edition. Also same thing. It's going to be checked by the metadata program. Because you do these two things, what's going to happen is when I run this, it's going to say error, warning, you have an unchecked account. It's always good of an error to get because you need to know what you're doing when you're using these. You can go check the code for the token metadata program right here. You can read it. You can see that it's actually going to be checking these accounts. And since we're CPIing, we should be okay. So let's do an anchor build and see that error. All right, as expected, safety checks failed. Didn't work. We didn't want it to work. Great. So we're gonna have to add some checks to say like, these are checked by the token meta program. So this account is checked by the metadata smart contract. And I'm going to copy this and put it in two places. All right, so we have these. Now, there's one more thing I want to do is that these accounts can actually be derived. They don't have to be just mutable. We're going to actually set all the seeds and stuff here so that we don't have to derive them ourselves. If we derive them ourselves, it's more work on us. Let's just make it auto-derived every single time. All right, so for this one, we have to add those seeds. We're going to add empty seeds real quick. Needs a bump. And then finally, it will need to specify the program that it is getting or deriving these from. So this would be seeds program equals the token metadata program. All right. And the seeds for this one are as follows. First, it's metadata. Then it's going to be the metadata program, so token metadata program. Next up is the mint. So we're going to have to do the collection mint as ref. And let's see, it's got an error. Let's figure out what it is. It's just missing a comma somewhere. Oh, it's missing a comma right above it. That's fine. All right. All right, so this needs to be the key. Yep, key. That's fine. Save it, and there we go. So we have these as the seeds here, and we're going to copy and paste this real quick. So I'm going to copy and paste this account real quick because it's very similar. And instead of, let me just do some enters here so that it's easier to read. So token metadata program collection mint. And the final one for this one is we have the token metadata program collection, and the last one is not actually empty, but it's going to be addition. And I need a comma up ahead. And let's see what, oh, I had a dot. That's fine. So if you're ever interested in how to derive this, you can actually derive it just based off of the smart contract itself. So we can go to the code. We can see here's the seeds for metadata. It's that prefix that we have, the program ID and mint info. Everything's there. You can also do the code diving for this one as well. This is for the master edition. You can just go to the MPL token metadata program. It's on GitHub. You can go look through it all. But we have everything here. We have our checks. So check. Let's make sure we have those. Otherwise, we're going to get another error. Let's go ahead and anchor build it. All right, so it's saying that token metadata is not there. Let's see, it's right here. So token metadata program. I probably just set it incorrectly, and that is fine. Token metadata program, token metadata program, token metadata program. Let's see. What is not in scope? Let's find it. So one thing I noticed is it should be .key. Because otherwise it won't know to use the key. It'll just use some, I guess, some bytes or something. Let's go ahead and build it and see if that fixed it. Yeah, that fixed it. Just needed to be .key. Yeah, so it's just because it could not find it because it needed to be a key instead. All right, so we have everything. It builds. Now we can actually start writing the code for initialized lottery. So there's going to be a whole ton of code in this specific function. We're going to go through it line by line. All right, so the first thing is we're going to do a bunch of things with CPI, and they're going to be signer seeds. They're going to need signer seeds. So we're going to do let signer seeds. We're going to do equals. It's going to be a type of reference U8. This is how all signer seeds look like. We're going to go backwards there. There we go. Equals reference. We're going to have to add our collection mint. This is because we're going to use the collection mint to do a bunch of things as ref. And then finally, reference. Let's change this from underscore context to regular context. Context.bumps.collection mint. So now we will be able to sign with the PDA that is the collection mint account to do a bunch of things, which we'll need in just a moment. So first thing, we need to be able, I'm going to create a message that's going to be creating mint account, because that's the first step that we're going to do as referenced when we were doing the Excel draw. We have to create the mint, create the collection, create the metadata account, and verify the collection. All right, so let's go ahead and create that mint. This is going to be something that you've probably done before. Mint2, this needs a CPI context. We're going to do it new with signer. New with signer. There we go. I'm going to go ahead and put a question mark there because we need it. We'll need it in just a moment. A new assigner, we have to provide the program. So it's going to be the token program, context.accounts.token program.to account info. The next thing we'll need is we're going to use mint2. This is just kind of to help us out with creating the accounts. There we go. You can see here it already kind of tells us all the different things we need. Some of these things don't actually exist, but we need to make sure the mint is the collection mint. It's going to mint to that collection token account, and the authority is not there, but it's going to be the collection mint as well. As we remember, it's the collection mint. All right. We're going to make sure that we set it with the signer seeds. And we need to mint 1. So we're minting 1 to our token. Let's see, this is saying that I can't find it. Let's go ahead and add it real quick. Import mint 2. Yeah, sure. Let's do it. Import from token. Yes. All right, it's saved. Let's do an anchor build and make sure we did everything right. So one thing I realized is that this mint 2, it's coming from, let's see, it's coming from Anchor SPL. We actually need to make sure that we're using a different mint 2. So we need to import the let's go backwards a little bit. We actually need to import a different mint2, and this one's going to be a token metadata one. So it's going to be anchor SPL. It's going to be, let's see, not token metadata, but token interface. Interface, and this is going to be mint_2. Might have to write it myself, and that's okay. All right, so we need to add it here, token interface, it's right here. We need to add the mint_2 and mint2. There we go. We need to make sure that this is using the right thing. Remove that. All right, so everything should work. Let's just do an anchor build, just make sure that we did it correct. All right, so we have the mint2. It's minting a single token to our token account. Next thing we're going to do is we're going to create the metadata account for that token. So let's create those metadata accounts. So message, just to make sure that we have all the messages stuff for creating a metadata account. We'll remove these later. That's fine. So this is going to be create metadata accounts v3. You can see it's already kind of knows what I want to do. I'll leave this here. We're going to fill this out. It's a lot of things we need to fill out here. All right. So first is that context. This is going to use a new context. So we need a CPI context. First one, this one's going to be new with signer because we have to sign with that, keep that collection mint account again. You can see it already says your program, what accounts are you doing, and your signer seeds. Thankfully, those signer seeds are the same ones as earlier, so we don't have to worry about that one. The program is going to be that context.accounts.token metadata program. .to account info. Perfect. We're going to use a fancy helper for us. We're going to do create metadata accounts v3. This is just to help us out. And you can see there's a lot of different things here. All right, so let's start filling this in. It's got a bunch of red lines. Let's make sure that we fill it in. All right, so the metadata is going to be that metadata account. That works. The mint is that collection mint. The mint authority is itself, perfect. Payer, the one who's going to actually pay for this is the payer, great. There's the update authority. We want to make sure that's not the payer. We want to make that the collection mint. So let's go ahead and paste that over here. System program is system program. You can see it requires rent. We didn't actually include rent. So let's go ahead and go add that real quick. So going back down to our context right here, we're going to have to go add a rent account. So pub rent sysvar info rent, and we'll just update this up here to be, instead of the system program that was auto-generated, rent. All right, and then this should be everything. Let's see what it's missing. Expected accounts v3 lifetime. What is this? Expected found mismatched expected pub key got account info. So it's missing something. Let's figure that out. So I figured it out. This up here, just the auto import did not work as expected. It's grabbing it from the wrong import here. So you can see it's doing import of anchor MPL token metadata. That's completely different than what I actually wanted. It's actually, there is a create metadata account v3 right here. It should be anyways. So I figured out here, this import is using the wrong create metadata accounts, is using it from MPL token metadata. So it's an easy fix. We should be able to just update this here. It's also because I did it, it's under account. It needs to be accounts v3. So we'll just remove this right here, save it. It's not being used, you can see, and I can go back down here, update this to say accounts, and then it should be happy. All right, cool. All right, so this is a reference to the signer seeds. We need to make sure we always reference it. And then we have to create the data as mutable, update authority as signer, and the collection details. So we're almost there. All right, so next one, what we're going to do is we're going to create that data. So this is going to use a struct called data v2. We're just going to have a bunch of things in it. See, it already tries to set them all. I'm going to set them individually. I'm going to go ahead and skip to the bottom and start doing all these. So true, we want to make sure that it is mutable so that we can change it later. The update authority will be yes, the update authority is the current signer. And then we're going to do some collection details. V1 of size 0. There we go. All right, so we should just have to fill out this data v2 instruction now. So it needs a name. We're going to create these names in just a moment. We're going to just, for now, we're just have an empty one. We'll need a symbol. We're going to need a URI. And then we'll need a setter fee basics points. We're going to set as 0 because we don't care about this in this collection. We're going to have a creators array, or a creators struct, I should say. Well, it's an array of some vec. We have to create a creator. We don't really care about this, but sometimes you might care. This is for like profit share or sharing of fees amongst the creators. We don't actually care in our case, so that's all right. Context.accounts.collection mint.key. We're going to have it verified as false because it's not verified yet. And then share of 100. We don't really care about all this. We're not going to use it. Unfortunately, you have to include it, but we don't care about it at all. The next thing is you have a collection is none at the current time. We're going to change this later. And then uses none. This is also true. Okay, so the thing that we're missing here is it says it doesn't know what creators. Let's go import it real quick. It's trying to import it from there. We don't want it to create from there, so let's make sure that we're importing it from one place. I believe it is just under metadata, so let's make this nice and set up here. So let's see if it exists under there. No. All right, I'm going to be right back. We're going to check where it exists. All right, so where it exists is it's under MPL token metadata types creator. Boom, we have the creator. It's being used. Unnecessary braces, yeah, it's not necessary because we're only using one type as of right now. All right, cool, and that should have everything there. The next thing that we're going to have to do is we have this name, symbol, and URI. Let's go add them as constants up here so we can use this up throughout the program as needed. So we're going to do a constant. This is going to be pub const. We're going to do the name first. This is going to be of type and string. It's going to be, we're going to call it token lottery ticket number. And you'll notice that I did it with no ticket number. This is because we're going to add the number for the ticket later. The symbol, we're going to call this TLT, sure, why not? The constant, this is going to be the ticket constant, so pub, URI, and string. It's going to try to do some arweave address. We're just going to go grab something from the internet. So let's go grab it real quick. So let's just go ticket. And we'll grab a ticket here. So emit, well, this is a nice ticket. I'm going to go ahead and copy the URL, image address, and put it right here. Oh, that's a big address. We'll figure out that breaks it later. That's fine. All right, so we have all those things. Let's just go set them right over here. So this is going to be name. Guess it has to be toString. This is going to be the symbol, toString, and then finally the URI, toString. All right, let's go ahead and build it, see if it works. All right, so compiled, we must have done everything right. The next thing we have to do, if following our things, is we have to create the actual master edition. So let's go create that master edition. So I'm going to do message. We'll do creating master. Look, it knew exactly what we needed to do next. We're going to have to use create master edition v3. It's going to need a context and a max supply. This max supply will be a sum 0 because we're not going to be doing more than just this account. But let's create that context real quick. So context, whoops, there we go. I'm just going to pull it out so it looks nicer. All right, so another context. So we need a CPI context. This one, once again, new with signer. This is because we have to sign for everything. We're going to do a signer with that collection mint. And so we're going to pull this out. We know that we already have the signer seeds, so we're good there. This is going to be that context accounts.token metadata program to account info. And then this accounts is going to be a create master edition v3 right here. And we're going to need quite a bit of accounts. So first one we'll need is that pair. Is going to be that pair info. Then we're going to need the mint. This mint is going to be that collection mint. So thankfully we already have that. Next one is going to be the edition. This is going to be that master edition account that we've passed in. The mint authority is going to be the collection mint once again. The update authority, collection mint. That collection mint has a lot of power, and that's okay. Metadata is going to be that metadata account. The token program is going to be the one that you pass in. The system program for creating the account. And then finally, rent. I'm hoping in the future that this rent's not required anymore because you actually don't need it. All right, cool. So we've created the master edition. Let's anchor build, make sure we did it right. All right, so we did that. And the final thing, if you remember, is we have to verify that collection. So let's go ahead and verify that collection. So we're going to do a message. Copilot did not get it right this time. Verifying collection. We'll remove all these messages later. It's just going to be helpful for us to understand what's going on. So this is going to be a sign metadata function. It's going to have a context. So let's add that real quick. I'm going to go ahead, go down here, finish it out. All right, so CPI context, once again, as expected, new with signer, because we have to sign with the collection mint PDA. That collection mint PDA is going to be used a lot throughout this whole thing to sign. All right, so program is that token metadata program. So context that accounts dot token metadata program to account info. The accounts, we're going to use a nice little struct for this, sign metadata. It doesn't have all these things that it thinks it has. That's okay. The things it does have is it has a creator, which is that collection mint account as we set up here. So we set up here to the creator was the collection mint account. And then we're going to have the metadata account. All right, it was happy. Looks like, just making sure my braces all line up. Yep, I'm going to remove this new line because we don't need it. All right, let's build it and see if we did everything correct. All right, so we have everything set up. Let's go build it out. I'm going to add this into this initialize. We're just going to make this a general initialize test. It's not really a test because we're not asserting anything. That's okay. We just want to make sure our thing's working. We can assert it ourselves. If you want to write good code, I would recommend just asserting it if you want to on your own. So I'm going to do it here as well. So we're going to do const. This is going to be a init lottery ix. It's going to have some accounts. So this is not everything. So we'll do .accounts. It should only have one account, if I remember correctly, because of what we can do is we can actually check what the accounts are required. We can see the pair is myself. We already know who that is. The collection mint, we already know who that is. Collection token, we already know who that is. The metadata account should be derived from these seeds. Same with the master edition. What is not given is this token program because it's an interface. We have to tell what token program to give. So this should just be token program. And we're going to use the It's going to be token program ID. We can see it's get grabbed from, we don't want to grab it from there. We want to just import it. There we go. Let's make sure it imported from the right place. From Anchor from SPL token. If you don't, I don't remember importing this, but if it's imported, great. If it's not, we'll do it in just a moment. So this is the IX for that. That's all we need, I believe, for that. So once again, we'll just create this instruction or this transaction. So const, this is going to be init lottery tx equals new anchor.web3 add lottery tx. We should be able to use the same information from earlier. I don't expect time to have passed dramatically, so our block hash should still be valid. There we go. And then finally, let's just do the same thing. We're going to go grab this real quick. This should be a init lottery signature, init lottery signature. I'm going to enter so that it looks a little bit nicer. I'm going to take out the skip pre-flight because we don't need it unless something doesn't make sense. I'm going to make this pretty as well. All right, so we have provider connection. We need to make sure that's using the lottery transaction. We have the pair as the wallet.pair. Let us also console log it. So console.log your init lottery signature, and let's run it. So one thing you're going to note is that if I run this right now without doing anything, it's going to try to initialize all of those accounts again. The lottery, token lottery config, a whole bunch of accounts. So I'm going to go ahead and restart the validator with -R. This resets the state so that we can make sure that we understand the state that we're going to start out with. All right, so let us anchor test it. Anchor test skip local validator. All right, so it failed. Let's figure out what we were missing to make it work. So we got a specific error code. This is on the init lottery transaction. So let us do that same trick as earlier. We'll do the skip pre-flight so we can see what is the issue. So I'm going to reset my test validator again and run that test. All right, so we have a transaction with a custom signature or custom error. We can see it failed on that init lottery. Let's go see what that error is. Go to the Explorer, and see it failed with invalid program execute. Program account is not executable. All right, so I know what this issue is. This is because we don't have the token metadata program on local. So if we go to this program, we can see this account right here. Count does not exist. We actually have to go grab that from our mainnet. So if you go to Solana Cookbook, you can see here that there's going to be some information on how to dump programs. It's Solana program dump-um, your program ID, and the SO file. So we're going to do that once on our own, and then I'm going to show you a script that will get you all the information that we need. So Solana program dump-um, this is for that specific token metadata program, which is, let's go grab it from the transaction right here. And this is going to be put into metadata.so. Boom, we have the metadata SO. And now if we want to load it, we have to do BPF program. We have to set up, let's just make sure, verify with the code. BPF program, and the SO file. So metadata.so, reset. Now, if we go over to look at this account, it should exist. Boom, it exists, perfect. And it is an executable. All right, so let's run that same test again and see if it works this time. All right, so it passed. Let's go grab that init lottery signature and look at it. Okay, so here's the instruction. We can see a whole bunch of accounts that we've initialized right here. We can see the token balance of 1 because we have 1 token in that new token account. And then there's an instruction, a create account, initialize the mint, and create another account and initialize the account. We have mint to it. And then here's our big instruction for, let's see, looks like this is one of the metadata program accounts. And then here's another one. So one of these is going to be the master edition. One of them is going to be the metadata account. And then we set all the authorities. And then this final one is the verify. So this is verify right here. So you can see all of our code right here, setting up, creating. It went through and built the whole thing, signed the verify, and our collection is verified. So fantastic. Another thing that we can do, and let's see if we can pull it, is that let's see if we can pull the account. So one of these accounts is going to be our token account. Let's see. So this is our writable one. We can cheat this. Where's the token account? Here we go. Address token. Let's go look at that token, see if it has the little logo. So my fear is realized that random image that we pulled is not showing up here because it had something weird with the URL. That's okay, but we can see the token lottery ticket right here. That's the master edition, has that same TLT. So the URI is actually something else. You can go look at that in the token metadata account. So let's go look at what the URI is supposed to be. There you go. So it's a specific format. So metadata format. So if you go look at these JSONs, it's actually supposed to be a JSON URI, which includes the image. We're not going to do that real quick. You can go based off of the previous collection module and just learn it from there. I'm going to go ahead and pull one that I have. So we'll go grab that from Phantom real quick. All right, so the image wasn't generating because it's actually the URI is supposed to be a JSON file. I just grabbed an example one. We're not going to create one real quick, but this is an example one of name, test token, symbol, test, description, your test, your image, and here's your actual image. So that's why it's not showing up. I'm going to go ahead and generate this on GitHub real quick. So we're just going to create this on GitHub under the developer bootcamp, and I will be right back. All right, so I've created this under the Project 8 token lottery. It's a metadata JSON. It has that image that I grabbed from the internet. You can use the same URL. So what you do is you go click on raw, copy and paste that, go into here, update your URI to that specific URL. And then if you go look at now this transaction or this token, you can see the token has a ticket. Token lottery ticket hash TLT. All right, so now we can continue. So we've now initialized the lottery. The next thing that we want to do is we want to actually buy tickets. So let's go ahead and buy those tickets. I'm going to just make this should test token lottery, just so that we can do the whole thing in one. This is not necessarily a good test, but it's just so that we don't have to worry about it every time we restart. All right, so we'll get back to this. Let's go to librs and start building out that new instruction. So we've initialized the config, we initialized the lottery. I'm going to go ahead and minimize all these so that it doesn't get in our way. The next one that we have, if we go back to our design, is buy ticket. So let us do that buy ticket instruction. We have to go afterwards. Let's go at the end of this. All right, so pub fun buy ticket. You can see it already kind of generated some code for us. I'm going to minimize this again. There we go, buy ticket. So it's going to have a buy ticket context, and we're going to get started. I'm going to we're going to have an amount. I'm just going to have it buy ticket one ticket at a time, just so that we don't have to worry about this. We can do the amounts on the front end, and that's fine. All right, so we have the buy ticket. Now we need to create the accounts for it. So let's go down here and create those accounts. So it's derive accounts, pub struct, context or buy ticket. That's our context. It already tried to generate a bunch of things for us. I'm going to remove all of them. The only thing that we know we're going to need so far is we need the signer because we need someone to pay for it. And then we're going to need the pub system program because we're going to create a new ticket. All right, so the next thing that we need is we're going to need a new mint for this new ticket. So let's initialize a new mint. So we're going to do account. We're going to have it init again, pair equals pair as usual. We're going to create this as a new seed. It's going to be the specific token lottery number that we're going to use it, which actually in order to do that, we need to do the lottery as well. So let's grab that token lottery real quick. This is going to be a mutable. It's going to be mutable, not immutable, because we're going to be updating the ticket count within it. It's going to have those seeds. Those seeds are going to be B token lottery. And then the bump is going to equal token lottery dot bump. This is so that I can easily derive it. So pub token lottery info. All right, so now we have seeds. The seeds for this one is going to be token underscore lottery dot ticket. It's going to be the number of tickets. So what total tickets. So it's going to be the current ticket number, 2 LE bytes, little Endian bytes. That's going to be bump. And then we're going to be initializing. This is going to be ticket mint. It's going to be once again another interface account of info mint. So we're missing some code here because it's a mint. We have to provide all the information for it. So mint decimals equals 0. Mint authority equals we're going to have this as the collection mint. That collection mint is going to be very powerful yet again. Looks like I'm missing a colon. That is fine. There we go. Mint freeze authority is going to be that collection mint again. Mint token program is going to be that token program. All right, so you can see here, we're already missing some things. We are missing the token program, and we're going to, so it's probably going to say right here, yeah, missing token program, and we're also missing that collection mint. So let's go ahead and create those real quick. So pub is going to be the token program, token interface. All right, so we need that collection mint account. This collection mint is going to be account is going to be mutable because we're going to increase the number of tokens on it. Well, we're going to use it basically. The seeds are going to be the collection mint account again. So collection mint dot asref, and then bump. Unfortunately, we couldn't save it because it's not our account. Collection mint interface no mint. All right, so we have that. Next, we're going to need a few things. We're going to need a metadata account for our ticket mint. We're going to need that same master edition account that we had earlier, and then we're going to need also the collection metadata account as well. So let's go ahead and build those out. All right, so first off, we have a new account. We're going to do the first one as the metadata account. So seeds are the same as earlier. So let's go grab those seeds. Where do they go? It's an initialized lottery. It is going to be right here, not here, right here. All right, so seeds are these. And go ahead and grab all of this code right here. How much should I grab? I forget. There we go. Okay, seeds, collection mint. It's not going to be the collection mint. It's going to be that ticket mint. All right, let's go ahead and grab this. This is going to be the metadata account. So pub, we're going to say is a ticket metadata. Once again, it's going to be created by the metadata smart contract. And the other one that we need is that master edition again. So let's go grab that. You need this so that you can add a NFT to a collection. So instead of the collection mint, it's going to be that ticket mint again. This is going to be the ticket master edition. All right, so that should be right. Okay, so it's already telling us need the metadata program because we're doing stuff metadata program. So pub token metadata program, token metadata, perfect. Okay, and the next thing that we need to do is since we're buying a ticket, we need a destination. We need a token account to give for this. So let's go ahead and put that in here. This is one thing we're going to need is the associated token account, which we'll do in just a moment. So account init pair equals pair. We're going to do the associated token mint equals token mint, associated authority. This one's going to be the pair because we're going to give it to that person. And then associated token program equals the token program. And then we have to create that specific account. So it's going to be a pub destination equals interface account of type info, lifetime info token account. Perfect. All right, and because we're using the the associated token program, we once again need the associated token program set. So let's set it down here. Pub associated token program, associated token. And if you remember when we did the master edition earlier, we also needed rent. So let's add that real quick. Boom. All right. So that should be everything for buying tickets. Now let's actually write the code to buy the tickets. Go back up here and let's get started. Before we get started, let's actually do an anchor build just to make sure we're doing all right. All right, it passed. Just had a warning because we have a context. That's okay. So first thing, I'm going to get that clock so that we can tell if whether or not someone can actually buy a ticket. So now we have the clock. Then we're going to get the ticket name, just so that we make sure that we set the ticket name. This is going to be name. We're going to do a little bit of string concatenation in Rust. This is going to be plus context.accounts.token lottery.total tickets .toString as string, boom. And now let's check. So if clock.slot is less than context.accounts.token lottery this is going to be lottery start time. So the lottery is not ended, or clock.slot is greater than the end time because we don't want anybody buying after it ends. We want to throw an error. We'll go at lottery not open. You can see here we already have an error code, so that we need to actually create those error codes. So let's go down to the bottom and create those error codes. So the way that you create error codes in Solana programs or Solana smart contracts is you use the macro error code pub enum. You can see it actually already knew. Lottery is not open. It's a message. That's the message. There's our enum. All right. So let's scroll back to our code. We have the ticket name. We've done the clock slot. Check that someone is eligible to buy the tickets. Now we actually have to do the buying of tickets. So if you remember, there was a price to pay whenever you do the ticket. So we're going to take that money from the buyer and deposit it into our lottery pot. So CPI context, this is going to be new because we don't need any PDA signatures here. We're going to do context.accounts. This is the system program to account info. We're going to have to do system program : transfer. Whoops. There we go. All right. So it's going to be from the pair to the token lottery. It's not the authority because that would be myself. It's going to be the token lottery. It's the token lottery account itself. And the LAN ports is specifically the token lottery price. But that is not in this section. It is actually outside of the transfer. It's down here. And it's actually just the LAN port amount. There we go. All right, so we've done the transfer. Next thing we need to do is we need to create the ticket. So as earlier, we're going to do a lot of the same thing. We're going to do let signer seeds. It's not going to be token lottery. It's going to be the collection mint because we have to use the collection mint authority to create a bunch of these, a new ticket off of this collection. And we have to mint the new token. So mint2, once again, CPI context, new with signer. We're going to just enter a bunch of things real quick. There we go. The program signer seeds are a reference. The program is going to be a context.accounts.token program .to account info. Then we're going to use the mint2, the same one as last time. And we're going to mint to, the mint is going to be, let's just set all that. It's a ticket mint. We're going to mint it to the destination. And the authority to do that minting is going to be the collection mint. Perfect. All right, so let's see all the errors that we have. So first off, I realize that this needs to be bumps because that is the current way that you grab the bump. And see that mint2 instruction. So I'm missing something in the instruction. We're missing the amount. That's okay. Very easy fix. It's going to be comma 1. There we go. So we minted a single token to the ticket of the ticket mint. Next up, we're going to go create the metadata accounts and create the master edition. I'm going to go ahead and grab that from the token lottery and we'll just update it as needed. So these two right here. I'm going to copy and paste those just so to save us a lot of time. All right, right here. And the first one we need to go through is this one, the create metadata accounts. We need to make sure that it's all set up correctly. So the correct one should be ticket metadata. The mint is the ticket mint. The mint authority is the collection mint. That's correct. The pair will be the pair. The update authority is the collection mint. System program, rent, perfect, signer seeds. Our name, our string. This is actually going to be our ticket name because we want to have our ticket name be the one with the number. Let's see. Okay, so seller's fine. Address is going to be let's see, this is the created address. We don't actually have any creators for this one, so I'm going to go ahead and remove this and put none. True, and then this is going to be none because it has no collection details. This is just like if you remember from the token metadata information, the specific mint account has none. All right, so we have that one. Next up, we have the master edition. So let's go ahead and start creating it. So this one, the first thing I know is this is going to be the ticket mint. The master edition is going to be the ticket master edition. Once again, also the metadata is ticket metadata. And let's go down pair. Yep, the mint is the ticket mint, ticket master edition. The mint authority is the collection mint. Update authority is collection mint. Metadata, token metadata. Yep, rent, everything good. Sum is 0, perfect. Now we need to actually verify this as part of the collection. So set and verify side collection item because we're adding a new collection item. We're going to go ahead. This is the authority record. We remember earlier we set it as none. So we're going to set it as none now. And I'm going to make this a little bit prettier. Enter, enter, enter. All right. So we need a new CPI context. Once again, it's new with signer. So new with signer. Let's see if it did everything. That would be fun. So it needed to be a token metadata program. Perfect. Set and verify size collection item. That is correct. Now we're missing a bunch of the different items. So let's just fill that in. So the first one is the metadata. This is just going to be the context.accounts.ticket metadata.to account info. Next one is going to be the collection authority, which is that collection mint. The pair is going to be the pair that we're used to. We're going to have an update authority, which is going to be the collection mint again. We're going to have the collection metadata. context.accounts. Do we actually include this? Maybe did we forget something? I think we forgot something. That's okay. Let's go at it. Two of the things that we missed two things. I just double checked. We missed the collection metadata and the collection master edition and collection metadata. So we're going to copy and paste this. We're going to change a couple things. So this is going to be collection metadata, and this one down here is going to be collection master edition. And then we just need to change these to use the collection mint account. There we go. All right, go back up to our code. So collection metadata should be now collection metadata to account info. The next one, I believe it is the collection master edition. So collection master edition, which is our collection master edition. And let's make sure I have everything. So looks like you don't. Let's see what I'm missing. I'm missing so I'm not importing it. Let's import it. Let's do this one. Let's make sure it imported in the right place. One thing I don't really appreciate is it's putting it all here. I actually want it to all go up here. So let's go pull it out and put it up here. So create master edition. Just going to clean this up a little bit. It's adding it in a place I'm not exactly fond of. This is why you don't do autocomplete sometimes. So let's go and copy and paste this whole thing into here, and then just update it as needed. Pull it out. All right, let's see if it added everything. Whoops, I put an extra character. That's okay. All right, so where is it? Set and verify collection. Looks like I'm missing something. Missing collection mint and collection metadata. I added an extra thing, and then we need the collection mint. So collection mint. As expected, collection mint, and it's all happy. All right, so we've done all this. Now that we've created the ticket, we need to increase the ticket number by 1. There we go. All right, so we have everything. Let's test this. Let's see if it works. Looks like there's some errors. Let's just remove these and get them working before we start, because otherwise we will run into errors later. System program / transfer. This is just us needing to include the system program. So use anchor _lang system program. Now let's see if we're missing anything else. Looks like we have everything now. Looks like everything is happy. Yep, everything seems to be happy. Let us now anchor build it. So built correctly. Now let's go buy our tickets. I'm going to go ahead and create another function for this, just so that I can make sure that I buy the tickets. I can buy multiple tickets very easily. So buy ticket. This is going to be a new function. We're going to buy all those tickets. So const buy ticket ix equals await program.methods.buy ticket. And then it's going to be .accounts token program ID instruction. Now we have to get that block hash with context again. We are going to have to get some information. We're going to have to create a new transaction. So this is going to be new anchor transaction. We're going to do the same thing we did earlier. There we go. All that code right there. Add by ticket instruction. And then we need to just const signature, send a confirm our transaction, and console log it. This is going to be the buy ticket signature. And then we have to actually call it. So let's go call buy ticket over here. Await buy ticket. All right, so we have our test. Let us kill our validator, restart it, and buy our ticket. All right, so it failed. And we meant it to fail actually this time. So let us see program failed to complete. This is on the send and confirm the buy ticket instruction. Let's add our pre-flight instruction so that we can still get the pre-flight parameter, so we can still get the signature and try this again. So I'm going to kill this. Actually, it should be fine. No, okay, I have to kill it first, and then we should be able to run it. And what we should see is that there should be an issue if we did everything right with the program, which I might have done a typo here and there. We should have the signature tell us that we'll hit a limitation. So let's go find out. So if you go over here to our localhost explorer, you can see it failed. We go all the way down to the logs. We exceeded the CU meters. So we did, seems like we did everything right in the program. We'll figure that in a moment, but we actually exceeded the amount of CU required for a base level transaction. We hit 200,000 compute units. So this is a great little teaching opportunity right here. Because we hit the compute unit limitation on a single transaction, we actually have to increase the compute limitation. So let's create two instructions to do that. So this is something that you will normally do within your Solana development. You will normally create different compute instructions and priority fee instructions all the time. So if we do this compute instruction equals anchor.web3.compute budget program, program, not instruction, dot set compute unit limit. There we go. We can set a compute unit limit of, let's make sure I do that right, of, well, let's set it as, so we hit it at 200,000. Let's just set it at 300,000. We can update this later as needed. I'd actually recommend, and this is very important, I would recommend updating this units to be as close as the amount of compute that you need max for your transaction ever. This is so that you don't have to worry about this and you don't make your users pay more. All right, so we also need the new priority because we're using a compute budget program compute instruction. We also have to create the priority. So compute budget program set. This is going to be set compute unit price. And our price is in microlamp ports. We're going to just set it to 1. Normally, you're going to have to set it to something else or be dynamic with it. Because we're in a test and only one environment, we're fine with this. All right, so now let's add everything, all of our new instructions that we've just added. Perfect. All right, let's run it. Let's restart our validator and run it. All right, so it passed. Looks like our buy ticket signature passed too. So let's go look at that real quick. I'm going to go click on this, and you can see here, got a new ticket. Let's go look at that token account. It's ticket number 0 because we count from 0 because we're comp science people. And it did all the work. So it set it and verified a collection, did a clean write to the collection metadata, and added our new ticket to the collection. So that's all the work that we've done to create the collection, add a new ticket to the collection, have someone buy it. Now, the next two things that we're going to do is we're going to do something with a smart contract called switchboard. We're going to do a commit reveal function to create randomness and use it within our smart contract. Be great. I'm looking forward to doing this. Let us get started. So I'm going to minimize these buy ticket things because we're going to go into a whole new function. Let's actually go down here. Oh no, I can make this faster. Let's minimize it. I'm going to enter here a few times, and we're going to create two new instructions. You can see here we are 3 in. These 3 are going to be a lot faster, thankfully. These are all the setup ones. All right, so pub function. We're going to call this one, this is going to be commit randomness. All right, let's try to do some things for me. I don't care for all this. Let's just remove it all, have a base context one, underscore context, because we're not going to use it immediately, and let us create that struct. So this is going to be a new context, so I'm going to create it right here. So derive accounts, pub struct commit randomness, and then I'm going to have nothing in there. And we're going to, let's see, it's not going to like it because I had nothing. We're going to add a few things. So we know that we're going to need the token lottery. And so we need to be able to update that account. And this is going to be mutable because we're going to be updating it. So mutable, I'm going to go grab the seeds from it real quick. So our seeds were right here, seeds and bump. Bump equals token lottery.bump. And then I'm going to build this just to make sure that we are doing everything correctly. All right, so built, perfect. So there's 2 things that we're going to do. One thing that we're going to do right here, and then we're going to do the second thing later. We're going to have a randomness account. We're going to create that. This is going to be an unchecked account because it's actually going to be managed by Switchboard. It's not by us. So this is managed by the randomness smart contract. This is specifically Switchboard. And then we're also going to need because we're creating an account, we'll need the system program. And finally, we'll need a pair for this. So this is going to be account mutable of pubs pair signer info. Perfect. So those are actually all the accounts that we need. So let's go back to our function, commit randomness, and get started with it. So before we do any commit randomness, we want to make sure that the clock is done. We want to make sure that the lottery is done, is what I should say. The clock is past the lottery time. Okay, so the first thing that we're going to do in this commit randomness thing is we're going to get the clock, because we're going to need the clock to make sure that we're setting the randomness information correctly. The next thing we're going to do is we're going to grab the token lottery account because we're going to have to do some checks to make sure that we're doing everything correctly. And then the first check that we're going to have to do, I believe it's the first check that we're going to have to do on ourselves is we're going to have to check that the accounts pair, so accounts.pair.key, if it's not equal to the authority, we want to throw an error that this is not authorized. Now let's go create that error real quick. So we'll go down here and we will enter not authorized. So we have that error code now. This is because we only want the people that are authorized to commit the randomness. Otherwise, someone might do something funky. We don't know. All right, so context because I have the underscore. There we go. Fix that. And the token lottery, the token authority, this is because it doesn't need to be, there you go. All right, doesn't need to be referenced. Okay, so we have the pair checked. The next thing is we need to grab the randomness data, and we need to use something called from Switchboard to do this. So let's go add Switchboard to this real quick. So Switchboard's crate is just cargo add Switchboard on demand. So we're grabbing the crate. We'll be right back in a moment. Okay, we're here. We have the crate. Now we can actually use it. So what we're going to have to do is we're going to have to check this randomness data is what we expect. So let randomness data equals randomness account data, and we have to parse it because we need to make sure what's going on. So accounts dot randomness account data as ref. We're going to have to do this. Actually, we're going to borrow it and unwrap it here. There we go. Okay, so we have the randomness data. Let's see what's the problem. It's because I don't have the type for it. So we have to go up here. We're going to just import it real quick. So use switchboard on demand accounts randomness account data. Okay. Let's see. It's not being used. It's probably because I misspelled something then. Randomness account data context.accounts.randomness. There we go. Looks like everything is happy now. So we have randomness data, and we have to check that the slot is valid. So if randomness data dot seed slot is not equals to clock dot slot -1, we need to return an error. Error code randomness already revealed into. This is because if the randomness data is already, like, we're past the slot, basically, it's already revealed. So we make sure that we're not revealed, because that would be bad. Otherwise, someone can know exactly who the winner is. That would be really bad. So let's go add that. Randomness already revealed. Randomness already revealed. Okay. So C is error. It is just ERR. All right. So now that we've set all that, let's go set that in the token lottery. So token lottery dot randomness account equals context dot accounts dot randomness account key. Okay. So we have the commit randomness. We have everything here that is required for it. Now, there's a few things that we're going to need, and it's quite a lot of things, actually. Now that we're using Switchboard, we have a new Switchboard program that we're building, or that we're using. We're going to have to make sure that we add all of those, just like we add the specific metadata program right here. And there's a lot of different accounts that you need. I've made it easy for us to develop with it by if you go under to Project 8 Token Lottery Setup, there's going to be two separate SH files. All you have to do is go into it, copy and paste it, and create your own SH file. So I'm going to do this right now. We're going to create a bunch of things here. So I'm going to go make a new directory. This one's going to be called Setup. And go into Setup directory. This is just going to be just like how this is set up. There's a Setup directory. And we're going to create in that directory. I'll stop doing the stuff all in the CLI for just a moment. We're going to go into that setup directory and create two files. So this is going to be setup local.sh, and then I'm going to copy and paste that from the setup local file. And the other one is going to be the setup start validator. This is just going to have that really long command that we need to set up all the accounts. All right, so in the next one, so start validator. All right, so we have both of these shell scripts now. You can look at them if you want. I would recommend always looking at and checking it. I'm going to make them executable of chmod setup local and chmod +x start validator, and then we're going to run them. So set up my local. This is just going to download all those accounts that we need from mainnet. Now note, you should only have to do this once. If you run into some errors that were unexpected throughout this, you might need to do this again. It's all because like the randomness accounts might expire. And that should be fine. All right, so we have all the different randomness accounts. Now we can just run start validator. We'll just run this again over and over. This just will grab all the accounts that we need and start it in our local validator. All right, so next thing we're going to do is we're going to actually run our script. So I'm going to buy a couple tickets just because I want to make sure that I have a lot of tickets later so I can test some things. All right, so we're going to buy a bunch of tickets, and now we can do all the different things for running this commit randomness function. So the first thing that we're going to need is we're going to need the queue. So the way that switchboard works is there's kind of like a queue of randomness accounts, and it goes through this queue and it gives you this randomness data. So I'm going to set up this queue, new anchor.web3.public key. This is going to be a specific value. It's going to start with, if you go to, I'll show you how you actually figure all this out. So go to Switchboard on demand, their code. So this is their randomness code right here. This link will be in the GitHub repository. If you go to their specific, I believe go to their index, they're going to have a whole bunch of code here. You'll see it. It's very similar to what we're about to do. And if you go to their utils, they'll give the specific, let me make this bigger for y'all. They'll give the specific queue thing. We're going to work with the queue from mainnet because we copied it from mainnet. So let's go ahead and copy and paste that account. All right. So this is going to be the queue. The other thing that we're going to need before we start doing anything else is we need to actually pull the specific code or the program to run with a switchboard program, because we're going to do a bunch of things to set this up in the JavaScript side. So let's go ahead and do that. So we have this switchboard program. I'm going to do a let switchboard program for now, and we're going to update that in a moment. We're going to need this later, so I'm going to go ahead and create it. This is going to be a randomness key pair. So anchor.keyPair.generate. And then we're going to create the specific, we're going to grab switchboard. So if we go, we're going to do a before, and this before is going to load the switchboard program. Load switchboard program. That's going to be an async, perfect. All right, so we have the before. This what it's going to do is we're going to do const. We got to grab that switchboard IDL equals await anchor.program, capitalized program, fetch IDL, and we have to fetch it from the switchboard specific program. So we have to include switchboard from here. So let's do a npm. Is this the right place? It should be in the thing. So npm add or install at switchboard switchboard dash xyz slash on dash demand. This is switchboard's nice package for this. At switchboard on demand. Perfect. So the ID is going to be switchboard on demand. So the switchboard on demand PID, that's the program ID. And then we need to set the connection. So this is actually going to be from mainnet. So connection new anchor.web3.connection. And then the provider or the URL we're going to use is going to be mainnet. So if we set this real quick, I'm going to make sure I remember. We're going to set this to the mainnet URL. So I'm going to go grab the mainnet URL real quick from the Solana docs.com/docs. And this is going to be the RPC URL. So let's go grab that. So mainnet RPC is going to be under that public endpoints. So let's go grab it. Here it is right here. Put that right there. And now we have the IDL. So then we can do switchboard equals new program using this switchboard IDL. And let's see, make sure I did everything correctly. Program, new switchboard should be the provider, not the PID. Provider, because we're grabbing it from our provider. All right, so this error right here is just because it's saying like, hey, this might not exist. We want to make sure it always exists, and that's okay. So I'm going to go ahead and put that as anchor IDL, and we should be fine. So as anchor.idl. All right, everything's fine. This should load that program so that we can use it later. Now, what's interesting is we can actually save this to a JSON file, and we're going to do that in just a bit so that we don't have to constantly load this over and over. So I'm actually going to go grab this this ID, and we're going to pull it out and set it as a JSON. So be right back. All right, so I did some quick coding. All I did was I used FS to save that switchboard JSON to my file system. That way I don't have to do this over and over again. Now what I can do is I can just grab that IDL and just be fine. So the switchboard program, we're going to just make that a const instead. I'm going to go ahead and comment out this code. What I'd recommend, I'm not going to put this JSON file in here because it might change, but always try to get it again later. So we're going to do new anchor.program. This actually says that the switchboard on demand IDL exists. It doesn't look like it does, so that's okay. We're going to have to import this real quick. So just like we did the target types token lottery, we're going to have to do import switchboard IDL. So switchboard IDL. This is going to be from that file that we just did. So I saved it to switchboard.json. And let's make sure that it updated it correctly. Switchboard IDL, switchboard JSON not found. This is because we are in tests, so it needs to go backwards. So backwards, and there you go, it found it. All right, so we have switchboard JSON. This one's going to be as anchor.idl, and then it's going to be the provider. Let us make sure we did everything correct now. I believe I did everything correct. We should be able to just anchor test it. Since I've run this test before and I haven't restarted the validator, we expect the test to fail, but I don't want them to fail on this switchboard program. Let's see what happens. So it did fail, perfect. And it failed on commit confirmed transaction. So now we have the switchboard program. Perfect. All right, so I'm going to remove all this extra code. Whoops, didn't remove all of it. There we go, from top to bottom. And now we can start testing our commit reveal function. So we've reloaded the switchboard program. We have to go all the way down here with our queue. We have to start doing things with this specific queue. All right, so we need to go grab our queue account now. So queue account equals, this is going to be new switchboard.queue. And this is going to use that switchboard program that we used earlier and the queue that we just pulled. All right, so the next thing we need to do is we need to get the queue account. So we're going to do const queue account equals new sp.queue. This is going to be with the switchboard program and that specific queue that we have right above. There we go. And we're going to do a quick try catch. There we go. Let's just console and we'll do a process exit so that we can see what the error was. We don't want to continue just in case something went wrong. And then here what we'll do is we will do await queue account dot it's load data. That way basically we're loading the data into the queue. All right. The next one we're going to do our create randomness and do our commit reveal. So const randomness create randomness ix equals await sp dot random randomness dot create. This is with the switchboard program, the RNG KP, and our queue. All right, looks like, oh, I forgot a equals. That is fine. There we go. And then we got to create our instructions. So create randomness. Well, first in transaction. So await SB as V0 transaction. Connection. We got to do the provider dot connection because it's our current provider. This is going to be our IXs, which are just going to be our create randomness IX. These are instructions. Pair is our current wallet, right? So wallet, not pair, but public key. There we go. And finally, the signers are going to be that wallet.pair plus the RNG key pair that we created. All right. So the next thing that we'll have to do is we have to send the transaction. So const create randomness signature equals await provider dot connection dot send transaction with our specific create randomness transaction. There we go. And let's just console.log create randomness signature so that we can see what the signature is. All right, so let us restart our validator and do our anchor test. Oops. So anchor test skip local validator. There we go. And see what happens. All right, so it passed. Let's go grab that signature. So here's the create randomness signature. We'll go back to here. We're going to open Explorer as usual. Go make sure it's on local. Go to that signature, and we can see here we had our transaction. It was using, so we did the compute limit. That's our program, create. We got the account size for the immutable owner, or sorry, for the token program. We did a create account, initialize. So here's a address lookup table thing. This is for our something that we did in the switchboard program. So it's allocating, it's assigning. So this will allocate, assign, and transfer. Looks like this is about what we did for our queue account. So there we go. All right, so we have our that one worked. All right, so the next thing that we need to do is we need to actually do that commit so that we can commit this randomness to be later revealed. So let's go ahead and do that. All right, so we do const commit. We're going to create that commit instruction. It's going to be await program.methods dot commit randomness. This is that commit randomness instruction that we created earlier. We're going to have only that account that we just created, so that randomness account, randomness.public key. There we go. And we're going to make sure that we pull this instruction out. All right. And then like before, we're going to do const compute ix. We're going to call it a commit compute ix equals anchor.web3.compute program. There we go. And we're going to have to set the units. Let's set it to 100K. I don't think it's going to need 300K. Then we're going to need that priority fee. So this is going to be the commit priority ix set compute. This is not compute enterprise. Oh no, it is compute enterprise of microlamperts. We'll set it as 1. We're working on local. That's okay. And then we're going to get that block hash. So commit block hash with context. So wait, get latest block hash. And then we have to create that instruction. So const commit, or the transaction. So new anchor dot web3 transaction. It just filled in everything. Let's see if it filled in. Fee pair, provider, wallet, public key with the commit, the block hash, and the last valid block height is that. And it just added our IX. We actually need a little bit more. So we need to add this IX. whoops. We need to add our new the compute priority, compute IX, and then finally the commit priority IX. And there we go. So we have commit, the compute budget, priority, commit IX. We also need the SB commit IX. So add SB. Oh, so we didn't actually create the switchboard commit, so we have to also create that. So commit IX. This is because we created our randomness account with that create randomness signature, we need to also make sure the switchboard program is using that randomness account to commit for it. We need to provide this in the same instruction that we do the commit on our actual program. So this is going to be switchboard commit IX equals await our specific randomness account commit IX with our queue. Perfect. So this needs to go before our new commit IX. So I'm going to put it right here, right beforehand. Whoops, not that one. It's SB commit IX. There we go. And don't have a semicolon. There we go. So we have our 4 instructions that we need. And now we just need to send and have a signature. So commit signature. What we're going to do is send a confirmed transaction. It's going to be provider. Our commit transaction. We're going to have our, so commit transaction wallet payer. I'm going to have skip pre-flight on, or sorry, skip pre-flight not on because I just want to get the signature. And then we just need to console log it. Commit signature. There we go. I just realized I have to restart the local validator. So always remember to do that. So restart it and then run it. All right, failed. So let's figure out why it failed. Should test cannot read properties of undefined of key. This is for Q. Looks like I missed something on the Q. Let's go look that up real quick. All right, so I figured out what the issue was. So what happened is some of my accounts, they expired. If you actually dig into the code for Switchboard, they expire after, it was like 6 hours. So mine have expired. So what you kind of do is just do setup local. You run this, and then you restart your validator. So let's just do that real quick. There we go. Start validator. And then that should run it. And then let us anchor test skip local validator. And now, as long as it doesn't like exceed the test timeline, this should pass. All right, let's see what the failure was. Account does not exist or has no data. So try to pull some account. Let's just make sure that, yep. So I'm not actually setting it. Let's run this again just to make sure. All right, so the issue that we ran into where it's failing is actually because this send transaction didn't wait for it to confirm until we moved on. And since this is using a special type of transaction, it's called a version transaction, we have to do a little bit of extra work in order to check it. So we're going to do this real quick. We're going to do a let's call this confirmed equals false because it's not confirmed yet. And while, it's going to be simple code that we probably write in our college days. I don't want it to throw, let us take that out. We basically just need to check if it's confirmed. So const confirmed randomness equals await provider dot connection dot get signature statuses with our create randomness signature. And then, so randomness status, we need to pull that specific status out. This is not quite right. Let's just remove that extra code right there. So it's dot value, because it will be 0, because it's the only one that we send back. If randomness confirmations is not equal to null, so not undefined, and the randomness confirmation, let's do randomness confirmation status is equals to confirmed. Then we set confirmed equal to true. So let's clean up some of this code. There we go. And clean that up a little bit as well. All right, so if confirm equals true, then move forward. If not, continue looping. There we go. All right, so let's kill this validator, restart it, start it here. Whoops. There we go. And so this should always work now, because what it's doing is it's now waiting for that transaction to be confirmed before it does the overall commit transaction that we just coded up. There we go. And sure enough, it got confirmed. So one thing that you also note is that our time has increased dramatically. What you do is you just add a timeout. I've made it a very large timeout. The real thing that you would want to do is like separate these tests, but because we're just doing one large integration test, it's all right. So now we've done that. We've done the commit. Now we actually have to code up the reveal. So let's go back over to our smart contract code. Let's start writing up the reveal instruction. All right, so we're going to create first the derive accounts. So the accounts that you would need for this specific reveal instruction. So this is going to be, we're going to call this reveal winner info. There we go. So what are the things that we need for revealing? There's a number of different accounts that we're going to have to consider. Things like the commit account. We're obviously going to need the pair to do things, but overall, what we need is, so let's start writing that actually up. So first we need that pair, because there's going to be some money being used. The next account that we're going to need is, it figured it out already. We're going to need the token memo, or sorry, the token lottery. So there we go. There's our token lottery. And then finally, we need the randomness account that we're using. So this is going to be an unchecked account because it's going to be created via the switchboard smart contract. That's okay. It's every time you use an unchecked account, you should always have some red alerts going on and make sure that you know what you're doing when you're using this. I know that this account is being created and checked by the switchboard smart contract, so I'm okay. All right, so we have the reveal winner accounts. Now let's actually create the instruction. So we'll do pub function reveal winner. We have to create that context with the context that we just wrote. So this is going to be with that reveal winner context. And then we don't need anything else. So we're going to do outputs, the same thing as usual. We do outputs of result. There we go. And we know that it's going to give an OK at the very end. Oh. All right. I'm going to just go ahead and do an anchor build while I code the rest of it, just so that if I run into any issues, this will tell me very quickly. Let's see. All right, looks like we didn't run any issues, so let's start writing it. So first thing, we're going to have to check the clock. So get the clock. Then we're going to have to do let token lottery and get our specific token lottery account. We need to make sure that the token lottery account, so accounts.pair.key, that the person who is doing this or revealing it is the specific authority of the token lottery, because otherwise we want to return an error code of not authorized. We don't want someone revealing that they're not allowed to. And the next thing that we need to do is we need to make sure that the specific account, is that right? What am I doing right there? Context.accounts. Let's see, something is missing there. Similar name for context. Let's see, context.accounts.pair should be right. Dot accounts. All right, sure. Context.accounts. We need to make sure that the randomness account is the same randomness account that we set earlier in that token lottery config. Otherwise, we need to exit because that is a problem. is avoiding someone setting a new randomness account and hijacking it based off of a randomness account that creates a good random value that makes them win. We want to make sure that it's set before everybody buys tickets. The next thing that we need to do is we need to check that the end time is set. Otherwise, the lottery is not completed. And then the last thing that we need to do is we need to also require, this is another way that you can do these checks. It actually, I think it's kind of cleaner. We need to require that the winner is not chosen, because if the winner is already chosen, then what are we doing? Why are we trying to overwrite with a new winner? Otherwise, we can accidentally create more winners overall. All right, so random is data. We need to grab that randomness data from the randomness account data. So we're going to have to parse it. This is grabbing from the context accounts randomness account data bar. This is so that we can actually get the information out of that account and that we know what to do. So we're going to get that revealed random value. Oops, there we go. And it's coming from that randomness data dot get underscore value, and not the clock. Well, it is the clock, but it's a reference to the clock. Otherwise, you can't make good Rust code. Then what we're going to have to do is we're going to have to make sure that we handle an error of, if there is an error, you need to make sure that our randomness is not resolved. So say that someone's trying to reveal this winner in the same instruction that, or same transaction that they're committing, we should fail because it must be that clock plus 1. It must not equal, basically. So next thing we need to do is we have the revealed random value. We need to create the winner. So the winner equals revealed random value of the first random value in that array. And we're going to make it as U64. And we're going to do some basic math that we are used to in computer science. We're going to do it over the total tickets. So we don't want the revealed value to be larger than the total ticket amount, because then we just run into issues. So now we have the winner, and we need to make sure that we set the winner of our token lottery, and we need to say the winner was chosen equal true. And that is it. That's everything that we need for the specific token lottery, revealing the winner. All right, so let's do an anchor build and see if it runs. All right, so we've done that. Now let's go over to our test and start writing that test again. So after the commit, we want to now use our new reveal winner instruction. So reveal winner ix equals await. Now this is not going to be all the code. Thanks Copilot for trying, but not quite. It's not the program ID, but we're going to need one account set here, and that is that randomness account. Otherwise, it won't know what randomness account to use. The next thing that we're going to have to do is we're going to do what we did before. We're going to have to create a reveal block hash with context, and then const reveal tx equals new anchor transaction. Then we have to set the actual variables just as before. There we go. This is that fee pair of the provider using the specific things in our reveal block hash with context. There we go. And we have to add two things. We have to add the reveal winner ix, and then there's one other thing that we haven't done yet, is we actually have to call switchboard and make it reveal as well. So right before we do all this, we're also going to just do a const sb reveal ix, and we're going to reveal that specific randomness off that account. So we have to do that first, otherwise it doesn't know what to do. So let's add that. So this one is going to be add reveal ix, and then add the specific reveal winner. Let's just clean up this code just a little bit so it's a little bit more readable. There we go. So now we have the reveal transaction, and we need to just send it. And one thing to note is you cannot send the reveal transaction so close to the slot that it was committed in. So we need to make sure that going to reveal it too soon. So we're going to set the current slot. And then just like before, we're going to do while current slot. Sorry, we don't want the slot to be before the end slot. So there we go. We're going to just do a const slot equals await get current slot. If slot is greater than current slot, then current slot equals slot. Whoops, there's a lot of extra code there. And then we just need to finally do console.log. I'm going to just log the current slot just because I want to know what's going on. All right, so what this is doing is waiting till the end slot, and it'll just continue on until the end slot is hit. And then once it's hit, we'll be able to do this reveal because we can only do the reveal after the lottery is ended. All right, so let's do const reveal signature equals await anchor.web3 send and confirm provider connection reveal transaction wallet provider. And then let's console log it. Perfect. All right, so we have the console log. Now let's see if it runs. So I'm going to go ahead and kill this. And let's also check, make sure that if my memory serves correctly, we want to make sure that our configuration that we set early on is not going to be too crazy. So this initialize config needs the start end. It looks like that we did the current slot plus 20. So we should be okay. I just wanted to make sure I didn't set the slot too high. Otherwise we'd be waiting forever. All right, so kill the local validator, rerun it, and then we're going to run this test. So let's go ahead and run it. Whoops, that's anchor build. Might as well let it build. All right, let's run the test and see what happens. So you can see it did some work on the slots and then it eventually did a reveal. So let's go look at what that reveal looks like. All right. So if our memory is correct, we can see here, this is the switchboard program and it did a create an account, and this is our program. So we can see that it did the randomness reveal on that switchboard program, and then it revealed the winner on ours. And there you go. We have the winner. Now what we need to do is we need to make sure that we claim the money out of that account. So we have a winner, and let's just add a little bit of code to see who that winner is. Otherwise, we won't be able to see who actually won. So I'm going to go ahead and in here, we're going to add a log real quick. So message, we're going to set that winner, and I want to see who that winner is. So let's go ahead and kill local validator again, restart it, and then run our test and go look at that in signature. All right, so let's grab that signature that we just created, paste it. Let's make sure okay. Let's paste it in, boom. And let's go look at the logs. So our winner was chosen as 3. So the third buy ticket out of all the buy tickets we did up here. So we did a whole bunch of buy tickets right here. The third one, I think we're counting at 0. So the fourth one will be the winner. So there we go. We have a winner and it's within our range of all our tickets. All right. So now we have the winner. It is set. Let's actually write the code to do the claim now. So I'm going to do some cleanup real quick. We revealed. I already revealed. We have this token lottery. Perfect. Bunch of error codes. Okay. So we're going to do the normal thing of we're going to derive the counts pub struct, and we're going to call this claim winnings with the right caps. Winnings. Perfect. And so we know that we're going to need, as usual, we'll need the pair. So pub pair signer info. The next account that we're going to need quite a few accounts, because what we're going to have to make sure that we do is we have to grab the ticket account. We have to check that the ticket belongs to the specific collection that is set within our config. And then we have to actually release the funds. So we have to also account for that account as well. Lots of accounts. So let's start listing them. So the first one that we're going to have to do, so count First one is going to be our token lottery, because that's an easy one. We don't have to really think about it. There we go. So this is pub token lottery, count token lottery. The next one that we're going to have to do is we're going to have to grab the ticket mint. This is a specific ticket that the user has. So let's do mutable. Actually, it's not mutable because we don't need to change it. But the seeds are, we have to make sure that it equals the token lottery winner seeds. So this is the third one that we saw earlier. It's going to be different every time, but in the previous example, it was third. So pub ticket mint. This is an interface account. Info mint. Because we have that mint, we know that we're also going to have the specific, we're going to have token program. So let's go and put that there. So pub token program. This is going to be an interface of token interface. All right, so we have the ticket mint. The ticket mint belongs to a collection that we're going to have to check. So let's do that one as well. There's lots of accounts. So this is going to be the collection mint. So seeds equals, this is going to be that collection mint seed. So B collection underscore mint as ref bump. And this is pub collection mint interface account mint. The next one that we're going to need is we're going to need some accounts from the token metadata program. So before I do all those, I'm going to go ahead and put down here the token metadata program. So pub token metadata program info metadata. Metadata is the type for the program, right? The struct for the program. All right, so let's go ahead and grab those accounts now. So, whoops. Account. We're going to first grab the ticket metadata. So the ticket metadata account. So seeds equals, this is going to be metadata, token metadata program as ref, and then the ticket mint key. So it's specifically the metadata on the ticket mint. So then the seeds come from the program of the token metadata program. There we go. And this is going to be pub ticket metadata. This is not an unchecked account because we know it's already created, so we don't have to do anything special with it. So this is an account of type info, comma, type metadata account. There we go. And then the next one that we have to do is we have to check the winning ticket account. So we need to go check that associated token account real quick. So let's go grab that. So account. This is going to be seeds equals, let's see. Oh, sorry, not seeds. We can just use the special things from associated token. Mint equals the ticket mint. Associated token authority equals the pair. So it's owned by the person who is sending this instruction. And then the token program is of the token program that we expect. This is the ticket account that we expect. We're not just using an account, we're going to use an interface account. There we go. And then finally, we need the collection metadata. And the reason being is we need to make sure that this ticket mint belongs to the collection metadata that we set. So account. And then these are seeds. Let's see. Yep, it knows exactly what I'm going to do. The metadata, token metadata program, and the collection mint. The seeds are from the token metadata program. And collection metadata equals the specific account, info metadata account. All right, so we have everything here. Now we actually have to write the claim instruction. All right, so let's go ahead and write it. So we're going to do pub function claim winnings of context of our claim winnings context. We're going to do the same thing as we usually do. Outputs a result. And we know the end of this code is always the same. There we go. Let's make sure I spell claim right. Otherwise, we're going to run into issues later. Okay, so first thing we need to do is we're going to require that the context.accounts.token lottery winner chosen. So if the winner is not chosen, we want to exit out. So we want to make sure that the winner is chosen before you claim the winnings. Otherwise, you could do something funky. The next thing we're going to require is two things on the metadata, so the collection metadata stuff. So first, we're going to do the accounts.ticket metadata collection. We're going to make sure that the collection is verified, because if it's not verified, that means you can't guarantee that the ticket is part of the specific collection. So we have to make sure that the collection is verified. There we go. If it's not verified, we want to output the error not verified. The next one, we want to make sure that it's actually part of that specific collection. So .ticket underscore metadata .collection as ref. So let's make sure all this is right. This is not right, so let's just get rid of some of this code. Boom. So as ref unwrap .key. So we have to make sure that the key equals the context accounts .collection mint .key. If not, it's the incorrect ticket, so it doesn't belong to this collection. All right. Now we have to, for some work on the front end side, we have to make sure that the ticket name .toOwned. Let's actually check. What is this name? All right, so this name is that ticket name. So we have to make that this ticket name, we have to make sure it matches the name that is expected. So that number 3 needs to be ticket number 3, right? So we have to do some work on concatenation. So we're going to just do ticket name to owned context.accounts.token lottery winner to string. So we have to add them together. Whoops, token lottery winner to string. There we go. And why is it failing? Let's see. Error unexpected semicolon. Oh, I have a semicolon set equals. There we go. And save it. There we go. I'm going to do a couple enters. All right, so let metadata name equals, this is going to be the context.accounts.ticket metadata. We're going to have to do name. We're going to have to remove some of the extra values. Otherwise, we're going to get some weird values in our name. You can go ahead and try this without this code that I'm writing now, and you'll see that it'll give a lot of like extra values that didn't belong. All right, there we go. So we have the ticket name, the metadata name, and now we need to require that the names match. So require, this is going to be the metadata name equals the ticket name. If not, it's the incorrect ticket. And we also have to make sure that the specific winning ticket account is actually there. So they didn't just create a token account and doesn't have any tokens in it. That would be bad, right? Because they didn't buy the ticket. They just created an account to hold the ticket without the ticket. So let's make sure that exists. This is ticket account dot amount is greater than 0. And if it is greater than 0, if it's not greater than 0, we need to say no ticket because they're trying to cheat. So next thing we have to do, we have to just basically transfer the lottery pot amount. So accounts dot token lottery dot to account info. We have to pull out those lamp ports from our account, borrow, let's see, minus equals the context.accounts.token lottery pot amount. There we go. And then we have to transfer it out to the winner. So pair to account info plus equals the lottery pot amount. And then finally, we need to set the lottery pot amount from token lottery so that they don't just keep draining our lottery amount or something. Say we start a new lottery with the same amount or something. We want to make sure that they're not just constantly draining. There we go. All right, we set it to 0. Let's do an anchor build, see what happens. All right, awesome. It built. Now we have to actually write the test for this claim. All right, so let's write this test real quick. So we're going to do const claim ix equals the await program dot methods dot claim winnings. This is going to be used with that specific account. So accounts, we're going to have to make sure that we use the specific token program. So token program equals, we're going to just use the normal token program, not the extension token program. There we go. Hit the instruction. Now we have to do the same thing we've been doing. So const claim block hash with context, and then const claim transaction equals new anchor dot web3 dot transaction. There we go. Create all of our fee pair stuff. Add the specific claim instruction. Let's see, it added an additional thing there. So we have our instruction now. Now we pull the signature. There we go. And finally, we log it. All right, let us restart our validator and run this test and see if it works correctly. So we restarted the validator. Now we just need to run the test. All right, so it failed. Let's figure out why it fails. Failed error BC4. Okay, so what is BC4? So we got a reveal. Transaction simulation failed. This is on the send and confirm of the claim. So let's go see what BC4 is. Hex to decimal. This is what you do all the time when you run into these weird values. 3012. So anchor error 3012. Let's see what it is. Account not initialized. So it's saying some account that we have is not initialized yet. Let's go figure out which account it was. So let's look at this real quick. Let's see. The winner chosen was, is that 3? Let's see. Oh, it didn't tell me. So let us go ahead and skip pre-flight. There we go. And run it again. So we'll just kill these. And then we have to skip pre-flight and make sure that it's all good. Okay, so let's go grab that signature. We grab that and go put it in the Explorer. The reason why we do this is we get a little bit more information. We can see here, oh, the ticket metadata, account not initialized. So this program are expected. So it says that our ticket metadata was not initialized, which is very interesting. We had the token, but the ticket metadata was not initialized. So let's go pull that and double check that I wrote all the code right. So we go over here, we go, there we go. It's just metadata. We misspelled metadata. That's an okay error. I'm okay with that one. So let's go ahead and run it again. And this time, let's see if it completes. All right, so it passed. Let's go look at that claim. Make sure everything worked as expected. So there we go. There's our claim signature. We can check real quick. Oh, there we go. 0.65. So we gained some SOL over from the specific claim, the claimed winnings. It went 0.65. It should be the number. Let's see, how many of our tests did we buy tickets? How many tickets did we buy? 1, 2, 3, 4, 5, 6, 7. Is this 7? This is 7. So 7 times, was it 7 times 5,000? Is 5,000 the amount that we said? No, it was 10,000, right? Let's see, where is our specific initialized instruction? So there's our buy. There we go, it's 10,000. So 7 times 10,000 minus 5,000 for the land ports, for the fee. So because this is our fee. So we can see that the 7, there we go, was transferred from our token lottery account to our account, and we're good. We did the claim. So congratulations, we have created a token lottery. And just to generally recap what we just did, what we did was we created a token lottery where you bought tickets that were tokens in a collection in order to enter the lottery. Those tokens created a fee that went to a lottery pot account. That lottery pot account was then used later to claim the winnings when we claim the winner. To figure out who the winner was, we used switchboard randomness function. So we used some on-chain randomness. Is not truly on-chain, it's off-chain, but we're using a commit reveal function so that it's easily verifiable. And we use that to create our randomness, choose our winner, and then create it in a trustless manner and give the winnings to that winner. So that is a lot of different things or concepts that we've learned throughout this token lottery project. We will be using this in the future in the bootcamp. So look forward to that. If you have any questions or run into any issues, just check the GitHub repository, join the discussions there. But thank you, and let's go to the next one.